taken over Stat Tool 1. Brian is gone.
Yes. He is gone. Brian is no longer teaching the class. We are.
We are your lemurs. Anybody? Nobody here? Nobody in class anymore?
Is anybody in class? I'm just having some fun. Wait.
Okay, I'm back. Okay. I gotta wait more time. On it. Because you guys are like 3-4 seconds behind, and you're just like waking up. You're getting your coffee, and you're like, okay, what's going on today? What's going on? Lemur Nation. I got some Zaboomafoo action going on right here. This is Blu-ray and this is Red Kelly. So named after some YouTubers right there. So some animals. So we are good to go. I was like, how can I was like, I'll do that instead of an intro today. People are like, what's going on? Zaboomafoo Nation. I like her. Oh no. Sorry, I raised. Hopefully, I wasn't too loud. They are cute. There are some cute lemurs. I raised the volume up a little bit when I had them on, and I looked over at my volumes, and that's the really great thing about having that cool device right there. So I can look. You got It's like I like your names right there. So it's after Ray from Equals 3, and maybe his still girlfriend, maybe fiance. I don't know. But I hope they're doing well. I don't know them. Lemur Regression. So how's everyone doing this morning? We have our little bit of fun to start. You guys always know the start. Hopefully it's a little bit wacky. Trying to think of some new stuff. Maybe I'll make some more new stuff this weekend. Oh, and I have some amazing news. And I definitely need to reach out to some students. But we just got I don't have a graphic for this or anything cool. But UT was doing this thing called UT One Grants. And we just got, with what we're kind of doing here, a UT1 grant. And about half of my grant is to hire student workers to get them engaged with it. So I guess I'm putting out the word now that if you know anybody who's big into like developing stuff in Adobe, because we use a lot of Adobe After Effects. I use Photoshop. Like this background here was created in Photoshop. And so if you know someone who's very interested in that, it's not the highest paying thing in the world, but it would be something that they would do on kind of their own time. And they'd be developing stuff for like myself and other educators to kind of expand what we're doing. So if you like, the whole idea is, I'll tell you guys what the grant was for real quick. Imagine you had a cart. Like everything I'm working with right now is actually on a table. So all of this stuff I'm working with right now could be put onto a cart, and then you could wheel it into a classroom. And then a teacher could do what I'm doing across the internet just via any classroom. So they go into the classroom like they normally do. And then it's got the microphone and everything, because this microphone's on like a swivel mount. So it would be a microphone attached to the card and everything. You'd have the tablet that I have so you could draw, but they would just like hook in their computer. So all they'd be like, you'd be like, here, just load up your slides, you're good to go. And then you could have them broadcast online like this. So you'd be getting clear audio, you'd be getting clear video. We'd have a camera set up that'd be pointed at them like this. So you'd be seeing really good like capture of them, capture of their screen. Everything would be top quality. And like a lot of it's the building it out aspect, like the technology aspect's actually not crazy expensive. Thoughts on that? Like it passed, so they said, hey, that's good. So we're calling it like a mobile studio. So I've got a studio right now, but we want to have this idea of a mobile studio. And so it came about like from Twitch streamers and stuff like that. Like, you know, Twitch is already able to set this all up. I think everyone's still here. There's silence. That's sweet. You like it, Ben? Awesome. So yeah, that's and if you know anybody, like I'll be probably having people show me some of their work or something like that. So if you know anyone who's like, oh, I love doing After Effects, like all those cool intro things, like Mega Mondays was created in After Effects. There's Mega Mondays. So that's created in Adobe After Effects. And I'm looking into something this weekend that I think will be even cooler. So I'm putting the word out there. If you know some people who, like, if you know any students or who are like you know, like I'll say this. It's like that kind of work is very like good, high quality work. You need a 10. I know we need some more graphics. I'll be making them this weekend. And so I spend time doing it, and I'm still learning it. But if somebody's had a lot of experience, one, I mean, I just wish I could pay them more. Because it's very yeah, and UT will probably be doing more online stuff. I mean, that's the whole goal of every university as we progress forward. Is like it had always been a big goal of Chancellor Plowman to do more online, and now it's even more present. So I think they're like, okay, we want Brian to keep building out this online stuff and helping other educators, because this grant is not just about what I'm doing. It's about opening the door for other educators. And this is the last thing I guess I'll say on this. I think a lot of people. How did you guys? Let me kind of take a poll of everybody. I want you guys to tell me about your experience, because I put it this way, and I'll think you'll agree with this. A lot of educators, and I'm really proud of them, stepped up their game when we went to. No, I'm not. I'm not cut out for that. A lot of educators stepped up their game when it came to going online. Like, a lot of them figured out new, great ways to be innovative. They figured out, like new things they could do. And I'm lucky. I'm really lucky, because I've been doing this for about 6-7 years. Oh, you guys are too nice. You guys make me blush. But I've been doing this for I found Zoom to be awkward. And what we're creating here and what I've worked towards, and Zoom worked. I don't want anyone to think I'm trashing Zoom. It's just like, that is the last job I would have. I'm like the last sports person ever. Yeah, I've gotten a lot of feedback from students that they really enjoy this a lot more. And you guys pretty much know when I'm reading your text. You guys can see that, like, you say something and I'm pretty instantaneous about it, because the way I have this set up, I can see the slides and I can see the broadcast at all times. So I'm very cognizant of what's going on, and I'm really glad that you guys like this. And I think a lot of students also don't really want to be on camera, and Zoom has a lot of security issues that we found about. So I found that people really like this. And then yeah, office hours are nice like this. Yeah. I think I'll tell you the truth. And here's the thing. I used Zoom for like 3 years. So I don't want anyone to think I'm like, Zoom's so bad, no one should ever use Zoom. I used Zoom for 3 years, and then I started to come up with this idea about 2 years ago, and it took about a year to make this idea. So this idea took a year to build out, and it took $20,000-$30,000 as we were investing in it. And if you add up the work hours, like, of the people who helped me make it, maybe 50,000-60,000. So we spent a lot of time and money investing in this idea. I could show you guys some of the early videos of our prototypes of this, and you would not look like what we have here. So this was not done like, let's do a thing like Twitch. You just do this. It was it took a lot of time, a lot of money, and a lot of investment. Like, you guys always, I always like being like, look at the cool toys. I've got that soundboard right there. We got even more sounds today. You'll check it out. Oh no, I'm so sorry to hear that, Claire. Yeah, but I'm so glad you guys like this. Yeah, like people are saying, Zoom feels super awkward to interact. This is just like a social media experience. Well, here's the thing, and here's something I want you guys to remember. Like, you guys are all the hero of this class. Like, you guys make this class. And don't worry, whenever I ask a question no one answers, what's good about it is when people don't answer a question, I know that I've kind of lost everybody, or like I've gone too fast. I know things like that. So you guys help me understand I gotta. You killed me there. Is that Camden right there? It's our fun portion of the class. We wake up with stats mode. We have some fun. Yeah, so I think I'm really lucky. I'm really lucky that make them like yeah, that's easier. Devin, great advice right there. The chatbots is a lot easier. And you know what's funny? Let me say this, because if you remember Tuesday morning, I was doing something else for the very start of class for the first hour. I was talking to some PhD students about interacting with students, and I was doing it via Zoom, and no one wanted to talk on camera. Everyone wanted to talk in the chat box. And I should have realized that, because what do you guys do here? You guys don't come on camera here. So I don't want anyone to think Brian thinks he's a perfect educator one of my reviews kind of, I don't know, I was reading the reviews yesterday and they're kind of like, he thinks he's a such and such. I was like, no, I'm always critiquing myself. I'm always being like, how do I make this better? Where did this not connect? Yeah, it's really tough. And I think, and I feel for a lot of educators because my first, I think about my first semester teaching online. It was really tough. It was really tough. And Kyle's right. We actually did a lot of training, and a lot of them had never done anything like that. So I give them a lot of credit because they had to learn Zoom way quicker than I had to. Like I had to learn Zoom over the course of like a semester, and people would expect there to be hiccups and things didn't go perfectly. But all of a sudden now they're thrown into it. It was really tough. So, and we did a lot of training sessions, and we had a lot of people at the training sessions. We were doing a lot of one-on-ones with professors too. Yeah, Camden, that's really interesting right there. Camden, great stuff. Don't listen to the haters. Thank you so much. Oh, well, thank you so much, Hannah. I'm so glad, and we're about to get serious here. And you guys, well, thank you. I really, one of the things that really means the most to me is when people say they know that I care, and I, I really do. When I have to put in zeros or something like that, it actually hurts. When I see you guys getting a bunch of extra credit, I'm proud of you guys. It's like, it's like I'm not your parent, but it's like that. It's like when something good happens, you're like, yeah. And when something bad happens, you're like, oh, come on, no, don't do that, no. So I don't blame them. But it was frustrating. Yeah. And everyone's familiar with YouTube. That's why I have a saying, we say it a lot of times, meet the students where they're at. So it's like, hey, just go to this YouTube video and boom, you're on it. Oh my gosh, Nayland gets 50 points right there. What is the name of, I need a name for today. Let's hop over here and let's talk about last night. We're going to jump. We had a little bit of fun here. That was like fun starts to the class always. We kind of just talk about stuff, get our brains going for this 3-hour class. So I do suggest being here at the start. Wait, it's not Wednesdays anymore. We've lost track of time. It was Wacky Wednesday. Please tell me it's Thursday. She's Stash Mayor. Oh, thank you so much, Sarah. So glad to hear that. Here, let's hop over here to the main screen. Open. Okay, we'll do it right here. Oh wait, wrong screen. So when you have two screens, you don't know which screen you're on. Okay. I looked at the scores for last night. And last semester, this is not a joke. Last semester, the average. So this is last. And this is this. Okay. The scores for last night, and I turned on the points today. I made sure they were on. I checked before we even started. And so I like that right there. Andrew, so good to see you, Andrew. So good to see you. And so, and I'm going to be cutting those interviews we did last semester. Last semester, the average for last night's was a 91. Guess what it was this semester? Any ideas? 50 points if you get it. 50 points. Who knows what it was this semester? 50 points. Who knows? Ben's is close. Ben and Ethan got it. Doing the 50 points again today. Ben and Ethan got it. It's basically a 97. That is ridiculous. That is amazing. But do you want to know? Okay, I'm trying to remember. I looked at the next one. Do you know what chapter 7 assignment usually has as an average? I'm trying to remember. I'm going to put a number on here, but I think it's close to that. I think it was this. This is one of the ones that's due tonight. This is what we should try to do better than. Chapter 7's no joke. Now, we'll be doing it after class. We would also doing the Kahoot, but if you couldn't tell, did chapter 6 seem a little bit easier yesterday? Thriving. So something in there, yeah. We got Kahoot, we got stuff. So this is kind of, the weekend's going to be a little bit easier. Obviously, there is some work I think I put on the weekend. We will be doing more lecture tomorrow. I might even do some crazy points tomorrow, who knows? But the homework and the quiz were very easy for last night, I think. But so yesterday was a bit of an easier day, I'd say, but we really kind of built up the material. So don't let, this fool you. Chapter 7 is going to be a little bit tougher. I'll show you how to do all the questions. take the notes. I think we have another note-taking quiz. I'll probably put it due on Friday night. I know the test is due. It's just because we only teach this class for 3 weeks, so there's a lot of due dates. Now, once again, if you are taking your notes during class, you're probably doing the note-taking quiz. I think the next note-taking quiz is to have the definition of the slope, the intercept, and the r-squared. So we did those yesterday. We'll do them again today. And so without further ado, let's hop back to the lecture slides right here. I got to remember, I've got some new stuff today. I was working on some stuff. So I don't think, here's the thing. And so Andrew, you still in the chat? So is the knowledge they learn in Stats 1 for regression, if Andrew's still here, is it useful for classes like regression or just in general? Because we do have a whole class, BAS 320, which maybe Andrew has some experience in, and there's another fire truck outside. Let's see, very useful. Will this be on the exam? It is on the exam. The exam goes all the way to Chapter 8. Now you might say, how in the world are you going to cover those and review today, Brian? We already did yesterday about half of Chapter 7, and Chapter 8 is not much more. And I looked over every single exam question. Oh no, there was like one I was going to say. What was I going to say? Definitely take the practice test. It's got a useful tip in it. And there was one. I'm just going to make sure. I looked over all the exam questions. I think it's very fair. It's just hard to like, the exam, the way it works is it comes out of a pool of like 150 to 200 questions. So I have to make sure I say and phrase everything. Like I say r-squared is the percent of variation in y explained by the variation in x. But you can say percent of variation in y associated with the variation in x. Like I like to say explained by. But explained by and associated with are the same sort of idea. So I tried to look over it and look over all 200 questions yesterday to make sure I'm at least using very similar phrasing and have done it throughout certain points. I think I mean, of course, it's going to be hard to like be like, I said every question the exact way you should know it, but I think I was looking over it. And then the practice has a big hint. Did anyone take the practice and maybe see a hint on it? You can drop what the hint is in the chat if you want. So I'm letting you guys do that right before we start class right here. Did anyone take the practice test and see the hint? Does anyone remember what the hint was? Like, oh, these types of variables are a special kind of this, technically. Like, technically, because that could appear. We'll review here at the end. Identifier is like a special case categorical variable. It's like a category of one. So, yeah, and categoricals are not always identifiers. Like, it's the same idea of like males are humans, but not all humans are male. So an identifier is a special kind of categorical, but it is a unique type of thing. We do like to point them out, and they do serve a unique purpose, but it's a special type of categorical variable. So that would be a true statement. Hints. Like, I want to make that very clear. That's when I look over all the questions and I'm like, maybe I should make sure people know this. That way someone's like, wait a minute, but it's its own thing. Well, it's a special kind of this. Getting our brains ready. Here we go. So, Chapter 7 is on regression. Regression is used throughout. I'm going to put a little mark right here. This is the way I'll remember. Chapter 7 is used throughout BAS 320, which the name of BAS 320 is regression and regression modeling. That class right there. So, this class right here, or this literal class today, leads into so many things. There's not too many tricky ones. Don't worry. When there's something really tricky, I try to either change the question or mention it in class that everyone should know. An identifier, which is now in this part of the video, is a special type of categorical variable. So it is true that identifiers are categorical variables. They're just like a case of one because they're just a category of one that identify. So an identifier is a special type of categorical variable. I've said 3 times now, you should definitely know it. It's a true statement. If you see it, it's true. You're like, I remember that one. There's our exam scores. So what are we trying to do right here? We are trying to fit a line. Now, we're going to call this the line of best fit. There's a key word right here. The line of best fit. You're welcome right there, Alyssa. So this is the line of best fit, and it's going to create a linear model. And there's so much going on right here, like with least squares. You know what's so interesting? I want to show you guys the least squares really quick because it's kind of cool. So when you think about a line of best fit, if you had data like this, how would you fit a line through this? Would you fit a line like, what do you think? This red line, is that the red line I'd fit through it? Or to give visual cues, do you think the green line would be a better line? Do you think red line or green line would be a better line to fit through this data? I think about 40 through 50, about 40 through 50 are on the exam. People are saying the green line, you got it right there. So Valerie, we're throwing Valerie 50 points. I don't mind the follow-up question. When you have a question, ask a question. There's times Brian gets bummed out, and when someone says, I had a question during class, but I didn't want to ask it, I'm like, no, ask it. I'm sure someone else was wondering it too. I want you guys to look at this right here, and I'm kind of building squares. If Andrew's still here, he can tell us about the sum of squared error. And actually, if you notice, don't worry, you're not responsible for this. But this black line I'm drawing down to it, this is first person gets 50 points. These black lines that I'm drawing down to it are basically the what? The black line I'm drawing down to the model is the what? 50 points first person. This is a review question from yesterday. The black line I'm drawing down to it is the what? Ooh, no one knows yet. Good guesses, good guesses. Residual Matthew, nice job, Matthew. Matthew was right. It's residual, and Kate was right there with him. So Kate and Matthew get the 50 points right there. You are right. It is a residual. So what you'll notice is we actually use this. This is what we'll do in 320. This is how much the black right there is how much it misses the model by, the model being the green line. And I'm going a little bit more advanced just to show it. Let me show you the sum of squared error, because this is the error. Does that make sense? That's the error off the red model. And then we're squaring it. That's not a really good square. And then we're going to do this one right here. And then we're going to make it a square. And then this one right here would be this square. And the red one is not as good. If you notice, the red boxes would be bigger, and we would literally find the error of them, and that is called the sum of squared error. And the error term, which is the drop down to it, Jared, amazing equation. Jared gets 50 points. That is the equation for residual, actual minus predicted. Yeah, it's more practical problems, more like true, false, more like matching, some numeric entry, some multiple choice. Great question, Claire. Claire, 50 points. So you might be able to see it visually right here, but the green model has a smaller sum of squared error. It is the least squares. So when you look at this term right here, when we say what is the line of best fit, which line fits better, it would be the line that has the least squares. So the green right here have less squared area than the red, and they actually have the lowest amount of squared error. So I might start saying that. Thirsty Thursdays. Sure. You guys are cracking me up in the chat. That's what that literally means. Whenever I see something on the slides, I want you to know what it means to say this has the least squared error. So the error right here, because it should be like the sum of the squared error. So when you see things like SSE, it is literally the sum of the squared errors. And there's so many like things that just make sense when you think about them. But enough about that. That's a little bit more advanced, but this is how we're fitting the line. We're fitting the line by finding the line that is the best fit that reduces the sums of the squared errors the most. And that's just how big the squares are. Thomas, you see it. It's just, well, how big are those squares? Well, the green squares are smaller when you sum them up, just like this says right here. When you sum up those squared errors, that's all it is. You got it, man. I should do some extra credit for those things. If you know that going into 320, you're going to be ahead of the class. Like, you don't have to take 320, but that's just all that means is the sum of the squared error. This right here is a regression plot. We'll redraw it again because we're going back through this. If you were here yesterday, you know part of this. So our goal right here is to talk about Burger King. We talked about it yesterday, but we can still talk about it. I need another person to tell me, I need something different today. What is this menu item right here? I need something new. I'm going to pick out my favorite menu item. We've talked about Cookout. We've talked about Burger King. What do we got? I'm going to pick my favorite menu item. I'm going to order something. It's about 72. 72 grams of protein for this menu item. And 81. It's definitely bigger than I see a few. Okay, I think Devin wins. Oh, wait, Devin and Skylar win. Devin says triple cheeseburger, and Skylar says triple Whopper. So And Kate says the double meal combo. It just sounds so good. So we got some winners right there. Oh, Hannah, triple cheeseburger with bacon with the Krabby Patty. Oh, we got some winners right there. Sorry, guys. All the bacon in the store. A heart attack, says Gracie. Yeah, that's, if you can see what's going on right here, what should we be noticing about this? We should be noticing instantaneously that it has 72 grams of protein and it has 81 grams of fat. So you should be able to trace in on the plot and see what's going on. Now, what's interesting is large. Oh man, I mean, we left Burger King. We went to Chick-fil-A. I like that right there. So let's look at this. We can fit a model through here. Now, the program's going to do this for us. We don't have to solve these things by hand. That's the really great thing about doing statistics is, once again, you guys know I love showing you guys this, but when I create statistics, we'll hop over here to the main screen real quick. So if I wanted to do statistics, I'm going to keep clearing my throat. I can go here and I can load up some data. Oh, I got to reload. So I got to load up reg class, which is the regression class. Inside of it, it has data. I'm attaching this data, which means I can now not call the data frame. And then I can do model, save into linear model, height, weight, and that, that creates the model. This shows me all the summaries for the model, all the summary statistics. And then I can visualize the model, and there's the visualization of the model. So here it's just a graphical thing. Let me fix that. Do this, and the graphic will look better. There we go. And now we zoom in and we take a look at the model. So here is the linear model right here. So once again, what I'm trying to point out, you don't have to learn jump. You should learn jump or something like that. You don't have to learn R, but if you notice, you don't have to work this by hand. I'm not sitting here solving equations. I'm literally just asking it, make a linear model. So that's what that LM stands for. This is the Y variable. This is the X variable. And then I ask for a summary. Don't like hide and wait chart. We can change it. Let's do it. Let's do somebody's GPA by their height. So now we're doing the GPA by their height. And now we can get a summary of it and we can visualize the model. So what do you notice right here? What kind of relationship is there to somebody's height and their GPA? Oh, that's a really good question, Jared. They're basically 95% confidence and prediction intervals. That goes a good bit beyond the class. I mean, they say what they are right there, but it's for predicting individuals or predicting the mean of the line. And there's a negative correlation right here. Now you can see the negative correlation because the slope is negative. And so with this right here, we kind of understand a little bit about it, that taller people are expected to have lower GPAs. And there might actually be a lurking variable to this. That's a topic we'll talk about here later today. The lurking variable might be what for 50 points? It could be. Oh no, Jared, don't worry. I'm over here too with the low GPAs. Tall people don't. Sorry. Who knows? This is fake news. It could be gender. Who knows? You know what you can do? Watch this. I'm going to do this. We got to do this because here we're going to go. This survey used males and females. So we're going to go subset of survey 10. And we're going to do gender. Was it gender with a capital? I think it has a capital G. We're going to take only the males right here. So you have to do gender equals males. And so that's all the males. And then you just copy paste this line. And guess what I'm going to do? I'm going to go here and go females. And now we can make two separate models. So you can make a model now. So we go here, data equals males. There we go. Oh, it did it not. Error fit line, singular, no cases, GPA. Yeah, we'll do it a separate way. This is way beyond this class right now. Cool. Here's a line for males and females. Ooh. Oh, and then we need the interaction. This is, sorry, I'm going to stop. I just can't. Whoa. Whoa. What's going on right here? Whoa. That's so weird. The interaction's really strong. Last question. Is the interaction statistically significant? And this is something we should know for this class. Here is the interaction term. Is the interaction term statistically significant? Ooh, this is so cool. Oh, wait a minute. It's not, because it's not below 0.05. We brought it back to this class. We have the crazy thing that the interaction term is not statistically significant, but the model itself, the whole model, all the terms in the model except for the intercept, and then the interaction term is likely by random chance. But what the model does is not likely. Statistics is so crazy. This is just a review now. Everyone listening to this review, ready? When is a p-value statistically significant? You see how these are probabilities right here? When is a p-value statistically significant? We should know it like this. A p-value is statistically significant when it is what? Less than 0.05. Nealon got the 50 points right there. You are right. So it's less than 0.05. Have that written down. A p-value is statistically significant when it's less than 0.05. This is the interaction term in the model. Do you see how it's height and gender interaction? You do not need to know this for this class. We have gender male. We have height in the model. These are all not significant. The intercept, which is just a number, we don't really care about it. You'll hear me say a lot in 3 like no one cares about the intercept. But then the model itself is statistically significant, which means it does a reduction. And then R squared is really low, though. That is cool. You know, I can't help myself. Whenever I start making models and stuff, I just want to keep investigating. It's like a mystery, and then I just want to keep looking at it. And so, do you guys think there's a statistically significant relationship here? Yes or no? Do you think this relationship we are viewing is unlikely by random chance? Like, how would it look? Oh, yeah. You guys are cracking me up. How would it look if it was by random chance? People are saying, yes, you are right. If it was by random chance, it'd probably look like it has a correlation close to what? If it looked by random chance, like if this just looked random, it'd probably have a correlation closer to what? And I know I'm talking about correlation here. 0, you're right. Jared gets the 50 points right there. You're right. And Claire is right. Dots would be everywhere, as in like no pattern, just random. So this is what it would look like right here if it was random. And this is kind of what it would look like by random chance. Does that make sense right there? And everyone's on track right there. You understand that. So let's think. We have graphic 1 and graphic 2. I want you to come up with a p-value you think. Kyle, I think this will answer right here. What does it mean that the model is statistically significant? It means that what we see in one of these models is not likely by random chance. Does that make sense? What we see in one of these models is not likely by random chance. Which of these models looks like what you're seeing is not likely by random chance, i.e. statistically significant? Model 1 or model 2 looks like what you're seeing is not likely by random chance. Kelly, you were right for 50 points. Kelly says model number 1, first person to say it right there. You are right. It is model number 1 looks unlikely by random chance. So you guys got to tell me, Jared, you're already on track. You know it. I'm not saying this is the p-value. I'm just saying that is like a plausible p-value. Now, you could be saying, wait, couldn't the p-value just be this? Yeah, if we're saying it's statistically significant, it's less than 0.05. So, and remember, these are not, and good thing right here, clarification, these values are these R or are they something else? Is Brian giving you R right now or is he giving you something else? So are those the value of R or what are they? I'm giving you the value because I'm saying the probability of something happening by random chance, they're the p-value. So they're the p-value. Does that make sense to everybody? These are p-values associated with these. So this one, number 2 over here, what do you think the p-value for number 2 will be? What do you think the p-value for number 2 will be? Here, we'll put this below it. So what do you think the p-value for number 2 will be? Who's got some p-values for number 2? This is the p-value, and this is the R. I like that. Who said 0.7 for the R gets their 50 points today. Now, p-values can only range between 0 and 1 because they're a probability of something happening. I see there Michael said 0.9, so I'm giving the points to Michael. I know and Tyler, too. They both said 0.9, so I'm going to do that. All those answers are pretty decent. Even 1 could be plausible, but we would need something here very high. Because what are we saying? That we think, Jack, you got the points, too. You got it, Jack. So we're saying that we think what we observed here was unlikely, not significant. Yes, exactly. You're getting it. This is not a significant relationship. It's likely by random chance. And the correlation here is closer to 0. The correlation on this one is closer to 0. Because a correlation closer to 0 is probably just, it's just random. Just, I don't know. That probably just happened by random chance. If a normal probability plot looked like graph 1, would it have a p-value that was higher or lower? Great review question right there. So when you look at normal probability plots and how this relates to it, so normal probability plots, just review on that. So let's write this right here. How does this relate to a normal probability plot? So how do these p-values relate to a normal probability plot? They relate to a normal probability plot the following way. If we had a normal probability plot that looked like this, here we go, let's draw one right here. I guess it has the red there. So here's our dots on it. What does that look like? It follows the normal. Oh, that's Kyle. I'll go back to that. I'll mention that after this, Kyle. That's very complex. I'll mention it just very briefly. I'll mention it. Kyle, remind me and I'll tell you that during our 5-minute break because that's a super complex, weird thing in statistics. So what you have to know, and Claire, this might help out a lot. I'm going to put some things on both these slides. The null for this in words, and we'll do the null in notation later, is normal, and the alternative is not normal. Now, there are ways to do it in statistical notation, but and the null for this one is no correlation, and the alternative is correlation. So when you look at, sorry for my handwriting, when you look at the p-value, I want you to look at this p-value. It's the probability that our results occurred. Here's what we observed. Does that make sense? This is our result. Brian's currently highlighting our results. And this right here below it is the probability of our results that we observed, given the null is true. So someone tell me in words what it means for us to observe this and it have the following probability given this was true. Does that make sense? Like, think about it. I know I'm saying think about it a lot, but we observed this and it has this probability below it given this is true. So someone try to word that out for me and think about what it means. Just be thinking about that, like, because p-values are a very important thing. If you understand, people are like, how do you understand what a p-value means? Well, it's the probability of what we observed, and there's the probability below it. The results were likely by random chance given, with the graph had a 90% chance of, kind of, you guys are getting close. You guys are getting very close. If you have a high probability, you would have a correlation close. You guys are getting close. So think about this. It's the probability of us observing this sort of relationship. This relationship has a 90% probability, or a relationship more extreme than that, given, kind of close, given there's no correlation. Assuming that there's no correlation, we would see something like this, or more extreme, 90% of the time. So a result like this seems very what, given there's no correlation. A result like this seems very what, given there's no correlation. You guys are very close. It's not that you guys are very, very close. It's like a very exact thing. I think likely you guys are getting it. Our result that we observed here was very probable, given that there's no correlation, i.e. it's not significant. It's not a very significant result. It was very expected. Yeah, that's a good way of putting it too, Devin. This is something we would expect given there's no correlation. So think about that. Are you going to continue to believe that there's no correlation? You saw something you expected. You saw something you expected given there's no correlation. Would you continue to believe there's no correlation? Would you? Yes, I would too. I'd be like, well, that's kind of what I expected to see given there's no correlation. So that's why we do not reject the null. So when you think about why do we not reject the null? Because what we saw was very probable given the null is true. Does that make sense? What I observed in this graphic was very probable given the null is true. So when you look at the other example right here, this result right here was very what given the null is true. I like that, Claire. This result I observed was very what given the null is true. We're saying if there's no correlation, then this graphic or one more extreme than it, and the one previously, graphic 2, you do not reject the null. Graphic 1, you will. Let me erase where we highlight graphic 2 in here. Go, wait. I don't want the highlight. There we go. Graphic 1 is very improbable or not likely, unlikely given the null is true. This relationship we observe here is unlikely given the null is true. The null is that there's no correlation, and that is unlikely with the results we observed. So since this is unlikely, I'm going to reject that null hypothesis and say I have evidence that there is correlation. Now, I'm not looking at the correlation value to say that. I'm just saying, well, my observation in the graphic was very unlikely given the null hypothesis is true. I reject the null hypothesis and I have evidence for the alternative. Because you either retain the null, not reject, fail to reject. There's a lot of words people use throughout multiple disciplines. A lot of people like fail to reject. I like not reject because you either reject or not reject. Those three sayings, again, that you might hear are retain the null, which means you don't reject, which Brian's favorite is, but then the most classical way is fail to reject. So sometimes you'll hear retain the null, not reject the null, and fail to reject the null. Those three sayings are said with the following. This is when you would say you fail to reject, do not reject, retain. They all mean the same thing. And this one right over here, everyone says reject the null. Now, do not say you accept the null. Accept the null almost means you believe the null is true, because you either reject the null for a low p-value. When the p-value is low, reject the null. When the p-value is high, just let it fly. Yeah, I can tell you more about nonlinear, Sarah, if you want. Fitting polynomial models. We'll mention that during break too. Sarah, if you want to know about polynomial models or interactions or stuff like that, I can tell you. You can email me or I can tell you during break, and I'm always happy to go into those details. So definitely. And you do not have to take another class with me if you don't want. But 320, we go into a lot more detail on these topics. This is like the whole class. We do more models, and there's even a review of 201 at the start. So if you are interested in that, and if you want to take 320, I'll be teaching it first session summer. So if you want to take it. But okay. Let's do it. Sometimes my students take it. I'm super excited. So how does this relate to normal probability plots? Well, knowing the null hypothesis is going to help us out a lot right here. Yay! Have you guys? I think we were talking about Raul yesterday, and he took all the classes in a row, and I was like, well, you just took all my classes in one summer, 3 months, and he's done some great stuff. He's a great student. It's awesome. I get bummed out when I don't get to teach any more classes with people. There's so many students. I'm like, I miss you guys. Oh, you're welcome. No worries. I appreciate it too. So how does this relate to normal probability plots? Which of these looks like it follows the normal probability plot? Which of these looks like it follows the normal probability plot? Graphic 1 or graphic 2? And I reversed the way they work on this one because we did them the other way. Graphic 1 looks to follow it. So is graphic 1 something you would expect or not expect to see if it's normal? Is graphic 1 something you would expect or not expect to see? And look, the null is that it's normal. And I do know the not and the no switches places with these. It's always been one of my problems with it, but it's just the way the tests are set up. It's something we would expect. So the p-value should be high or low. If this is something you expect, given it's normal, you're telling me the p-value is what? If this is something you would expect, given it's normal, the p-value here should be very what? It's something you expect. Oh, let's see. It's something you expect. Uh-oh. If you expect to win the lottery, the probability would be what? So I'm going to give you guys another shot at this. If you expect it to rain today, the probability would be what? Yes, high equals expect, because we're saying it's probable. If I expect this to happen, it's probable. Does that make sense? I'm saying I expect it to rain today, so there should be a high probability that I expect this to happen. This is something I would think would occur. So this right here seems likely given it's normal. Does that make sense too? This graphic right here follows that line, which is the normal line. So this seems likely given it's normal, meaning the p-value here should be very high. So the p-value here could be something like this. 95, sure, why not? Correct. The p-value is the probability of our results or results more extreme happening by random chance variation given the null is true. So the null being that it's normal, this result right here seems likely given the null is true. That result seems likely given the null is true. And that's a good shorthand of it. Like the result I observed right here seems very likely given this null is true. Try doing it with those three methods right here. Look at your results and be like, this result I observe is likely given the null hypothesis is true. That's the big way to remember it. But it's likely, meaning it's not statistically significant. So what do you do to the null right here, Kyle? What do you do to the null? The p-value is high. Just let the null what? And this won't be correlation. Those are not correlation values. This is not correlation. These are normal probability plots, a review topic. You're going to just let the null be. You're going to say, I still believe that this is normal. So we're just going to let the null fly. When the p-value is high, let the null fly. But when the p-value is low, so here the p-value is this. When the p-value is low, reject the null. So now you say this result I observed on my normal probability plot was unlikely given it's normal. I reject that it's normal. I have evidence that it's not normal. Who here feels like this makes a little more sense? This is why we cover things multiple times. This is our second time doing a pretty decent dive into this. Hopefully it makes a little more sense. Good. Can you do a speed run going over p-values and r values and different uses? Yeah, let's do that. Let's do that. Great idea right there. Okay, so this is a speed run on the difference. I got to pull up my timer right here. It's one thing I forgot to load in. So let's do a quick speed run. Remember, this will be quicker. Can you explain the null hypothesis again? Yeah, let's do that. We're going to include that in the speed run here. Let me bring the speed run timer over to the speed run screen. Whee! Okay, let's do this. Let's get a speed run going right here. Here we are, hopping into our screen. We got to pull up some Word documents right here. We got the speed run going. Okay, let's do this. Okay. I don't know why this timer. What chapter? This is basically just understanding null hypothesis and understanding the difference between correlation and p-values. This will be like a 2 to 3 minute speed run. So do remember these are quicker and they're a quick review. So hopefully I don't lose everybody, but this is just a quick review of what we've been talking about. So let me get my pens going. How did we not have pens one day? How did that happen? So let's do this, a speed run over how we use correlation, p-values, and the null hypothesis. So let's go. So when it comes to p-values, every p-value is associated with a null hypothesis, abbreviated H subscript O. That's a subscript down there. Now, when you think about a p-value, the following statement applies. It's the probability of our results or results happening by random... Oh my gosh. The p-value is the probability of our results or results happening... Oh my gosh. One more try. The p-value is the probability of our results or results from our stream happening by random chance variation, given that the null is true. Third time's the charm right there. So let's break it down. When we talk about a p-value, it's a probability. All p-values are contained between the values of 0 and 1. All p-values are probabilities. They're within the set. I think I need to use a different notation right there. But all p-values are contained within the set. That might be the right mathematical notation. But they're all contained between 0 and 1. How does this automatically differ from R? R is a completely different concept, which is correlation. R is contained within the set of -1 to 1. Now, looking at these two things right here, all p-values are associated with the null hypothesis. Now, this means, and this is a huge note that you should know, that we use p-values in many different areas of statistics. P-value is whenever you're looking at any results. You could look at a mosaic plot and say, which of these two mosaic plots, mosaic plot A or mosaic plot B, looks likely by random chance, given that there's no association between the two variables. Which of these looks likely by random chance? We should be seeing it in the chat right now. We'll give 50 points to the first person who knows. Which of these two mosaic plots here, the first one will be A and the second one will be B, which of these two looks likely by random chance? It's A. Kyle got it. It's A. Secret one right here. A looks likely by random chance because there's no differences. It's like, well, there's no differences. That looks likely by random chance. Where B does not look likely by random chance, we're seeing a bigger difference. That means A right here would have a very high p-value. We're just making up a p-value right there. And B would have a very low p-value because it looks unlikely by random chance that we would see those differences between the groups. Notice that the null here would be something like there is no difference between the groups, or we would say that they're independent of each other, last chapter of the class. And the alternative would be that they're not independent of each other. So the p-value is dependent on the null hypothesis. Anytime you have a p-value, you must ask what? Anytime you have a p-value, you must ask what? You must say, what is my what? Whenever you have a p-value, you must say, well, what was the blank? What was the blank? Who knows? I know I'm not speedrunning super quick. I'm not getting world records on this one. Whenever there's a p-value, you must say, well, what was the what? Because it's associated. I might go back to that check in a second. What was my null? Kyle, you're right. Whenever you have a p-value, you must know the null it's associated with. What are we investigating? What was our null hypothesis to start? What am I assuming is true? So in this instance right here, you assume that there's no relationship, and that result was likely given there is no relationship. The result I observed highlighted right there was very likely given there is no relationship. This result right here was very unlikely given there's no relationship. So I reject that there's no relationship. I have evidence of a relationship between the two variables. How does this differ once again from correlation? Correlation, and this goes into today's topic even more, is only between two quantitative variables. Correlation is only between two quantitative variables. So whenever you're doing correlation, you will only get graphics like this, which we can do p-values with this, and I got to be careful because I'm going to put the graphics below it that have the proper p-values. We can get graphics like this for correlation, and this correlation looks what? By random chance. The first one underneath A looks very what by random chance? Very likely that that correlation happened by random chance, and the one under B looks very unlikely happening by random chance. So the p-values I have associated with these both groups right here are very similar. So you'll notice that p-values can be used for correlation because the result we see, and these are two separate topics kind of blended together, but the p-value we see for that graphic right there is very high, and the correlation for this would be very what? The correlation would be very low because the null for this assumes that there is no correlation. Now that's not. These are p-values. And these are correlations. Be careful, because the correlation is not a p-value. It tells you the strength, direction, and I guess it should have a linear form, but that's got it. Who here had heard of p-values before this class, but now it's really starting to set in? That's always one of my goals. I want whenever your friends mention a p-value, it's like, well, it's just like we look at what we saw, and then we look at the null, and we say, is it likely this would occur given the null is true? So hopefully it's starting to make more sense. All p-values are connected to null hypothesis. Yep, Cam, you're pretty much right. That's good. QQ straight enough. No outliers. Plot doesn't thicken. Confused on how you can make a mosaic likely by random chance. So here, I'll just mention that really briefly right there. Great question, Claire. Think about this. The null for this, and it'll help if I draw the null. The null hypothesis for mosaic plots is, I'll write it correctly. This is last chapter of the class. So these are the null. And if x and y are independent of each other, then if we were to change x from like A to B, then it would not change the levels of y. So let's say it's like pass, fail, and versions of test. But if they are not independent of each other, then you'll see this bigger difference right here. Like all of a sudden, version A, everyone's passing, and version B, everyone's failing. So in this instance right here, we have this very quick sketch because I'm going to hop back to the lecture. But the null is that x and y are independent of each other in the mosaic plot. So this relationship shows something that is likely to happen if they are independent. Like if they're independent, it wouldn't matter if you took version A or B of the test. You kind of pass and fail the same way. And this graphic right there looks very likely given they are independent. But if we saw that all of a sudden everybody is failing version B and passing version A for the most part, then this relationship we see here looks very unlikely by random chance. We would reject the null that x and y are independent, meaning they have no impact on each other. And we'd say we have evidence that the version of test you take is not independent of passing and failing it. Does that make sense? Yep, and that's how it works with mosaic plots, right? You have to know the null hypothesis. You have to say, well, we are assuming that they are independent, and this looks likely given that they're independent. How are those mosaic plots different from the segmented? They're just better. Segmented bar charts don't show you the, the marginal distributions. So we strive for a low p-value. Generally, it depends. Great question. You guys give the best questions because you kind of want, let me switch screens. It depends because a low p-value means the results you're seeing are not likely by random chance. And there's instances where you want it to be by random chance. Like if you want like your model to have no unexplained variation, then your residuals should be likely by random chance. But that's a really, like usually, a lot of times in research, you want lower p-values. So, and that's why they do a thing called p-hacking. It's cheating. So they shouldn't do that. There's bad statistics out there. What is the official definition of the null? It is your starting hypothesis for any test, which some people will be like, this is the null. And be like, the null can be any starting hypothesis. And then you look at your results and see if what you saw was likely given the null is true. So the null is your starting or initial hypothesis for any test. So to think about craziness, like a flat earther, sorry, don't be a flat earther. A flat earther would have the null hypothesis that the Earth is flat. And then when you show them how a pendulum works, hopefully that would help them reject their null hypothesis. Or when you show them the Coriolis effect, hopefully that would help them reject the null hypothesis. Then they would have evidence that the Earth is not flat. And that's probably the best. Like, the Earth is either flat or not flat. So, don't you have to say that you omitted data? Oh, yeah, you should always do that. You can remove, here's a good note. I looked over the test questions. You can remove outliers if you have a very good reason. But you have to have a good reason. There is justification for sometimes removing outliers. You have to have a very good reason. You can't just remove them willy-nilly. You have to have a good reason, like the data was incorrectly entered or it's from another subset. But there can be reasons. So there's a lot of flat earthers out there. Okay. Strength, direction, form, unusual features. So what do we got going on right here? We've got the 4 ways to describe correlation. We've got, yeah, exactly. You could remove that, Camden. So we've got strength, direction, form, unusual features. Once again, know how to do this. We reviewed it yesterday, so I'm going a little bit quicker through this right here. And we had an amazing talk on p-values just now. Alyssa, you're right. Great answers in the chat. Statistical significance right here is only when it's below 0.05, so we know what's going on right there with that. We've got QQ straighten up. No outliers. Plot doesn't thicken. First 3 people in the chat get their 50 points. You should know QQ straighten up. No outliers. Plot doesn't thicken. I'm going to throw 100 points to the first person who says all 3. Jared got his 50. Devin got the 50. Last hour of the class, you can give away points. That's the rule. Oh, Devin got 100 right there. You got it. And Needy got her 50 right there. So, or make sure someone correct me if I'm wrong on stuff. So, we have right there, people know QQ straight enough. No outliers, plot does not thicken. That'll come up a little bit later, and we'll talk more in depth on it. So, right here, we're talking about residuals. Let's review this again. We're about to the definitions again. So, when you look at this, this is a positive linear relationship right here, but it does have an issue with plot thickening. Plot thickening does appear to be an issue right here, which I know we have not covered in the notes yet, but why not mention it? There does seem to be an issue with plot thickening because we don't want the plot to get thicker in any sort of way. Now, look for things that jump out to you. Probably I want to remove this. We always say don't, like, if you take 320 with me, we're like, everything's going to have problems. But I do see that this one has a little more problems than I like. So you're forgiving a little bit. So you're like, then you're like, okay, this one has bigger problems. You don't want to look at one thing and be like, okay, there's a big problem. So you kind of give it a benefit of a doubt type thing, but this one does seem to have a pretty big problem right here. Next time I might remember to use new notes because I keep erasing the stuff I wrote from yesterday. So once again, we talked about this yesterday. Make sure to stay till the end of class because it is important to hear these things twice. So I look at the numbers and people are staying till the end. Great job. So what do we have right here? We have how we do it in statistics versus how we do it in algebra. Take a note that the B right here is B0, where the MX right here is the B1X. First person in the chat who can tell me B0. Why do we say B0? Because this is when X is equal to what? You got to say the full thing. B0 is when X is equal to, you got to say the full thing. B0 is when X is equal to what? Devin right there, you got the points. Devin, 30 points. So you've already got points. Give the points. I know I said last hour. I break the rules all the time. But B0 is when X is equal to 0. We're going to see right here. Camden, you haven't gotten your points today. You got it. B0 is when X is equal to 0. Almost had to sneeze. And next, we see that B1. Who can describe to me what B1 is? It's for each what? You got to do a full sentence right here. B1 is for each. Exactly, Jack. B1 is for each what? B1 is for each what? What is B1 for? B1 is for each. What is it for? For each 1 unit increase in X, we expect. Oh my gosh, Morgan is dropping the full definition in the chat. So is Erica. Nice job, Morgan, Erica, and Neelan. They all get the points right there, dropping the full definition in the chat. So everyone take a look at what Morgan wrote right there. For each 1 unit increase in X, we expect Y to increase or decrease by B1 on average. Great work, Morgan. Amazing job right there. That's exactly what we want. And then B0 is When x is equal to 0, we expect y to equal b0. Now, I want you guys to start copying from the chat right here. Who can put in the chat for 50 points? B0, and I did this yesterday, so if you want to see in the video, I want you guys to be writing it out. B0 is when x is equal to 0, we expect y to equal b0. Who can put it in the chat first? When x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. When x is 0, we expect, there we go, Devin right there, nice job. And the expect is a key word, and I want to make that very clear because we're not saying it will equal that. We're just saying what we expect or predict. That's why we're saying we expect this. So for like the other definition, for each 1 unit increase, and I messed up yesterday on the increase decrease on x. Sorry about that. I changed it after I wrote it. For each 1 unit increase in x, we expect y to increase or decrease by b1. Now make sure to pick increase or decrease. Would you say that we would expect y to increase or decrease here? Do you expect, as x increases, do you expect y to increase or decrease? What do you guys think? Do you expect y to increase? You're right. We expect y to increase. So I would say for each 1 unit increase in protein, I expect fat to increase by what? For each 1 unit increase in protein, I expect fat to increase by what? How many grams? For each 1 unit increase, 9.1, you got it right there. So make sure you notice that this right here is B1 because it's for each 1 unit increase in X. Let me highlight the words as I say them. For each 1 unit increase in protein, I expect fat to increase by 0.91. Does everyone see how I'm substituting it in as I say it? So I'm going to say the words this time, but I'm going to highlight what should be input into them. For each 1 unit increase in X, I expect Y to increase, or decrease, but increase, by B1. So for each 1 unit increase in protein, I expect fat to increase by B1. Does that make sense right there? I'll do it one more time. Just watch it as I say it. For each 1 unit increase in protein, I expect fat to increase by B1. Just make sure you can do it right there. There's other ways of saying it, but just be careful. Well, you don't have to write it out this semester, but it makes things a lot easier if you use that format. Don't even look at my Pearson. They'll try to trick you. Just write it out. Think about it. You got it. So when you look at the intercept right here, so it's when x is equal to 0, we expect y to equal b0. So when, when protein is equal to 0, we expect fat to equal 8.4 grams. When protein is equal to 0, we expect fat to equal 8.4 grams. You're right, Camden. Great answer right there. Camden, you're right. It would be decrease. If there's a negative sign for the slope, then we would expect y to decrease. Great answers, Camden. Keep it up. Great. That means you know exactly what's going on when you put that in the chat. Camden, you definitely got your 50. Throw someone else 50 points, Camden, because I think you have yours. Tag someone in the chat. Give them some points. When protein is equal to fat. And so make sure to be very specific. It's not when protein is equal to 0, fat will equal this. We expect it. It's what the model predicts. So we're saying, and there we go. I think Thomas got it right there. Oh, wait. Thomas, you got points. Still, Camden can throw it to someone else. And then you can say increase, decrease by the type of the line as well. Yep, you can look at the line. And so we expect is key right there. Usually during the semester when you have to write this out, I take off points for when people write that it will decrease or that it will equal this. It's what we expect. The line is predicting this. Nice job right there. You got it. Thomas got some points, and it looks like Carly got some points. Nice job. When protein is equal to 0, we expect fat to... Kate's got her points right there. 50 points, Kate. Great work. Great work. We see right here what a residual is. A residual is how much our model misses by. When you talk about a residual, and I've always hated this graphic because it almost looks like they're saying this and this, but you can't see that. It almost looks like they're talking about these 2 points. I'd rather talk about the residual right here because how many of these points have a residual? Who can tell me for 50 points? How many of these points you got in Matthew right there? How many of these points have a residual? How many of these points have a residual? They all do. Every single point has a residual. Now that residual could be close to 0 or it could be 0. Interestingly enough, this point right here looks to have a residual close to 0, as do these points here. Anything on the line has a residual close to 0. Every single point, because it's just how much that point misses by. every single point on here has an actual, like what's its actual value, and then every single point has a predicted value. The line gives predicteds. So everything on the line is a y hat. That's why down here, if this is 0 for the x, that's what we would predict if something has 0 protein. And that's the value of y hat when x is equal to 0. Like when you literally solve the equation, you would get that we would predict this is the fat that a menu item would have when protein is equal to 0. Like you would expect this. You're not saying it will have this. You're just saying this is what my model predicts or I expect when protein is equal to 0. And if you notice, I changed the wording. I didn't use when x is equal to 0, I expect y to equal b0. I use, so what exactly is a residual? People are given the notation in the chat, residual wrap, because a residual is basically how much the model misses by. In just more expanding the language, it is the actual minus the predicted. Residual equals actual minus predicted. But we can look at what the thing actually had for its fat. So here's the actual fat for that one. Let me highlight it. There's the actual fat. Here's the predicted fat. Making this its respect. It's not that point. I don't want anyone to think I'm highlighting that point. It would be right here because you would trace and make a prediction based on the model. So this is the y hat. It's also right there, but that's the y hat. That is, I didn't trace a vertical. Kind of like a margin. It's not really quite a margin of error. It's a literal error. It is literally an error. So the residual is literally an error. So the residual is literally the error. There we go. Let me try. Yes, got more headroom now. Got more headroom. So the residual is literally an error. So this right here is the residual. It's how far we miss by. And the residual here is positive, and all the residuals below the line are negative, and all the residuals on the line are 0, or close to 0 if they're basically near the line. Does that make more sense what a residual is? It's how much the model misses by when making a prediction. And you can literally make the square of it and find the sum of the squared errors of the residuals. So you can call it residual squared error and stuff like that too. So residual is literally the error. Good job. And you understand what a residual is. It's just how much the model misses by. It's like I make a prediction here. Exactly. Carly, Claire, you're right. Claire, you're totally right. Great job, Claire. Here's showing a visualization of it. Can anyone compute the residual right here? Who can compute? First person to compute the residual, because here's your numbers. And be very careful. Hint, hint, hint. It's in this region. We're talking about this point right here. Close, close, close. You guys are super close. It's in that region. Who knows? No one's gotten it yet. You're close. Josh, you got it. Nice job, Josh. It's negative 14.6. And think about by saying it's negative, you're saying it's below the line. So it's below the predicted line. I've highlighted the point right there. Don't worry. I know that when I say, yeah, you see it now. Don't worry. I understand that when I'm like, this is a tough one. I've done these questions a lot. And then I'll see people say 14.6 because your mind automatically goes to the difference between these two. Your mind's like, oh, we missed by this much, but it's negative because it's below the line. How do you calculate that? Let's do it. Residual, great question right there. Residual equals the actual minus the predicted. So if you look right here, this is the actual point. It's below the line, and here's the prediction of it. So we would do negative. I almost, see, I was writing 14. I was doing it. I make these errors too. I think I realized where the errors might occur. The actual is 22, and the predicted is this. I realize where the errors might occur because I make them too. I make them too. Your brain just does the difference. And it's like, yeah, that has a residual of absolute value of 14.6. Also, sum of squared error doesn't care about above or below the line. So you do, it's the same thing. Great question right there, Camden. I like to write it as residual equals actual minus predicted. The notation for the actual is y. So the actual value is y, and the predicted value from the line is y hat. And then residual in notation is e. So residual is actual minus predicted, and that's the mathematical notation for it right there. Like that's the mathematical notation, just to kind of compare the two. So that's what it means in words. Good questions. Good questions. Oh, this is important. Hint, hint, hint. So if you were to add up all the residuals, what would they add up to? I want you to kind of imagine these positive and negative residuals going like this. They're going to go. If you were to add up all of them, who knows for 50 points? You got it, Hannah. Hannah's got the 50 points right there. If you were to add them all up, they would add up to 0. That's how the line of best fit works. All of the points would just go like that. You will be given small formulas on the test, and I will mention those. So you'll be given the formulas. Please, like it says, you can have the approved Stats 1 formula sheet. There's only 2 formulas. The 2 formulas on your formula sheet are the following. You can write them down right now and use just these 2 formulas on your test. Your 2 formulas are this. No other notes. Don't put other notes on it. These are the only 2 formulas. So if you want to write these down, actual minus predicted. Those are the only 2 formulas on the first Stat 1 test. So if you want to write them down right now, that y hat equals b0 plus b1x, and then the residual equals y minus y hat, which is the actual minus predicted. And you don't put additional things. Those are the 2 things you can have written down on a sheet of paper to know how to do regression and know how to find residuals. And then you should just know what those means. You're allowed to have scratch paper, boop, and then just show the formula sheet. Shouldn't have anything else written on it. Just be like, formula sheet, good stuff, calculator. I'd be like, what are you doing? That's bad, calculator. So don't use that calculator. So, I think care. Oh, I mean, I guess I guess you could write that. I mean, yeah. Line of best fit is the best line through the day. We've talked about that a lot today. So here is the B1 and the B0. You're allowed to use your own calculator. Yes. You definitely are, Thomas. So you're definitely allowed to use your own calculator. Just don't use a phone calculator or anything like that. Don't be like, my calculator is my phone. So don't do that. So no, Nayland. Oh, you guys crack me up. Okay, so here we see the interpretations. We've been doing these a lot today. They're in the notes right here. Please, if you're watching this part of the lecture, go back to where people about 10 minutes ago were putting it in the chat. They put in the blanket interpretation. I was saying it, so I'm going to go a little quickly through this part here because it just shows you these. So it is in the notes right here if you're looking to just read the notes, if you want to read the slides. So we do have meaningless intercepts. This is a thing we kind of mentioned yesterday with our height and weight examples, where if we were to say, let's think about what these are right here. We want to predict the total hours that people spend on Facebook by their Facebook friends. So here, I want people to interpret. We have hours right here. And then let's do the following. Let's say this is equal to 4 plus 0.01 Facebook friends. Okay, so I want someone to first interpret for me the intercept right here. We are predicting, this is a tougher question. I would focus a lot more on this if you guys had to write this out. But you should know the format of this, and you should be able to use, I said intercept, so like I'm telling the slides what to do. You're saying 4, but that is tell me the intercept. Don't worry, that happens all the time during the semester too, because usually people, when they say interpret the intercept, people hear like, what is the intercept? But interpret means give me the full, what is the intercept? Nice job, Neelan. When Facebook friends is equal to 0, the hours spent on Facebook or the hours spent on the internet is expected to be 4. Amazing job right there, Neelan. Neelan, I'm giving you 100 points because you jumped out and you got it. That was a tough one right there. And Zulon gets 50 right there. When Facebook friends is equal to 0, and they even gave the full context. I like that they're right there. When Facebook friends is 0, be careful. You are expected to spend 4 hours on the internet per month. Does that make sense? You are expected. So we always want to say, like, this is what the model predicts or what we expect. So there we go, William. Nice job right there. William, Sam, and Kyle, you definitely got the 50 points right there. And so we expect it to be this. Makes sense? That's what I like to hear. So now I'm going to change this. And we do get models like this. You do get models like this. So slightly change what you have and tell me what it is. I'm going to rewrite it a little bit better here. I want you to think about this. And this is how the math could work out. The math doesn't care about the logic. So what would this one say? And would this be logical? What does this one say? When Facebook friends... You got it, Zulon, right there. When Facebook friends is equal to 0, the hours spent is expected to be -4. Exactly. And now it doesn't make sense. But the math doesn't care. The math is just like, you want me to fit a line? Sure. And you oftentimes see things like this when your data is maybe like, here's how much time people spend. And then if you fit the model, I gotta bring it this way. Gotta go. There we go. Okay, that'll work. So now when you fit the model through it, maybe the model goes something like this, because we'll talk about it in a moment, but that would be an extrapolation of the model. You're going outside of the X values. Now, you can still mention what the intercept is, but you would probably say that the intercept is illogical. There really is no data down here because you can't spend negative 4 hours on the internet, or maybe the model just does not have a good linear fit at that point. Like the model could have people down here that do this, and the line, if you notice the residuals for it, if you kind of zoom in on it, the residuals for those are getting bigger because the model's not fitting that data so well. So whenever you say what the intercept is, you have to think about it. You have to think what you're saying. You have to say, when somebody has 0 Facebook friends, oh, and we can't have points behind 0 Facebook friends. Go away points. We can't have negative Facebook friends. So when someone has 0 Facebook friends, we expect them to spend negative 4 hours on the internet per month. And that just doesn't make sense. That's what I would append to that. I would just say that doesn't make sense. So in a logical intercept is just when you say the definition of it, it doesn't make sense. I agree with that, Zulon. So we would say you would say your intercept is illogical. There's no the interpretation is illogical. Does that make sense, Neeland? You would say the intercept is illogical. There is no logical way to understand the intercept. It doesn't make sense. This is like, it's a meaningless. That's the key right there. It's like meaningless, illogical, doesn't make sense. It's like, nah, who cares about it? More examples. This right here, I'm 99% certain is not on the test. And I'll show you how to do this on the homework right here without having to do it. You will not solve these equations for me. You will not solve these. I know they're not big equations. Let me mention what the notation is on these, just so you can know the notation. This is the standard deviation of the y variable. This is the standard deviation of the x variable. This is the slope of the regression equation, and this, as we should know, is the correlation. I have a solver for this. It's online, and you'll use it for the SAT problem. Go to the solver, Devin. Go to the solver, and you can just input the values. I have a new solver. I think I have updated it. But the solver is so helpful for these, and I made it because I don't want you solving math. I want you interpreting and understanding regression. Yeah, go to the solver. Let me show where that's at right now. Let's put it in the video. So Devin, great job. And following along, asking, and Devin, you've been participating. Amazing job. Let's do it. I can't really go to my Pearson. Wait, not my Pearson. Don't go to my Pearson. Go to Canvas. Where's my buttons? Right, we got this. We're doing it today. I checked to see if the music's playing. Is it this one? Okay, we got this. Good music, good volume. We might need more music. Oh, we did it. Cool. Okay, now we're getting better music. Okay, so where is this? I'm trying to down a little bit here. Where is this going to be? You can go real quick. You can get me up. Oh man, we got some Mega Man right here. Got some new music. So where is this? It's right here. Regression Solver Pro 2.1. If you guys make some music suggestions, as long as I think I can play it, I might. Obviously, we're not playing copyright music. I mean, it's Nintendo, and people play Nintendo on YouTube. So that's where it's at right here. So go ahead and get this. You just input the values into it, and we'll probably just see a small preview of it here. But this right here takes all the values, and I think I even set it up to do your regression for you. So this will play Zelda. You got it. Look at it. We got the Zelda right here. I should have done it when I clicked the button. I need to get some more Nintendo music I think I can play until Nintendo copyright claims me. We Pokemon Battle. I like that right there, Zulon. So yeah, we'll get that. Remind me of these things. Put it in emails. I've got some memes we need to look at too. Thank you for sending me memes. A few people have. So this right here, download it. I'll probably be using it a little bit later. But this, if you notice, has the things you can input into it, and it'll solve it for you. So this just makes life a little bit easier, and you don't have to use jump. I think it works for everything. There might be ways to break it, but I would keep updating it every time people broke it. Like in a good way. Like they figured out a way that it doesn't work. Because I created this. So this was all me writing stuff right here. The Kahoot theme. Yeah, that's classic now. Kahoot has become like a classic. Like everyone hearing that Kahoot theme. I want to do like, I should do like the Wii Music Shop. That's a meme. So that has it right there. So thank you guys. Yeah. So Devin, check it out. So you shouldn't have to worry about, you won't be solving regression like by typing in, you can do it on the calculator, but I should make a video on how to do regression on the calculator. I don't know if it's in my TI list. I don't know if it is. I don't think it is because I don't remember making the video. I made those videos like 4 years ago over Thanksgiving. Here's how to do it in Jump. Not too hard to do it in Jump. You put in 2 quantitative variables. So you got here. Let's hop back to the lecture screen. I played all my music. I just kind of wanted to hear it too. That's why I put in the headphones so I can hear the music. It's like the first one was Mike Tyson's Punch Out, and then the second one was Mega Man 2 opening. So that's some classic. We'll get some more music on here. Have some fun. So this is how you do it in Jump. Cool. I did it yesterday also. You'll probably see me do it towards the end of lecture right here, and we'll be reviewing for the last 40 or so. It's the running music. If you've ever seen it, it's classic. Everyone's played Mike Tyson Punch Out knows that one. So shout outs to Summoning Salt right there. He's really good at Mike Tyson's Punch Out speedruns. He's not going to watch this. Quantitative variables, conditions, straight enough condition. QQ straight enough, no outliers. Plot doesn't thicken. We know what's going on. QQ straight enough, no outliers. Plot doesn't thicken. We have here that we have an X variable and a Y variable. It's most important to know that your X's do what? First person, we're back on track now. Your X's do what? Your X's do what? What do those X's do? Your X's what? Your X's what? They explain why something is happening, like the Y is the response. You might hear in other disciplines that your X is your independent variable. I always have to think. And your Y is your dependent variable. That's because the equation solves for Y. It depends on X. I hate those answers. I don't like that. I just like saying your X is your explanatories. And, you know, as I said, explanatories there because you can have multiple X's. Think about a car. What explains the price of a car? If you're going to go buy a car, what explains the price of a car? Like, is there one explanatory variable? Is it like how old the car is? And that tells you, okay, if this car is this years old, that explains the price. We now know the price. So we got make and model right there. So there's 3. The age of a car, the make of the model is, and how nice it is. Like, does it have features, the type, the brand, the engine. Oh, so we now need to know what engine it is, the condition the car is in. Oh my gosh, there's so many explanatory variables in how much a car costs, years, mileage, brand, trim, all this, the damage, how old the car is, damages, accidents. All these things are explanatory variables. I should highlight explanatory if we're looking into the response of why does a car cost a certain amount. So you can make advanced regression. And if I didn't sell you on B0 plus B1x, watch this. If you have here the y hat being we are predicting the price of a car, B0 is the what? B0 is the what? B0 is the what for the model. B0 in notation is the what? We should know this pretty instantaneously. B0 is when x is equal to 0. B0 is what? No one knows what B0 is? The intercept. Zulon, you're right there. It's the intercept. B0 is the intercept. You're right. Nice job. B1 is the slope for variable x1. And wait a minute. What is... Brian, stop. Stop going outside the class. Don't do it. We need, like, the Stop the Brian music. I don't know if there is the Stop the Brian music. It's this music right here. That's the Stop the Brian music. So we have right here that we have the intercept and we have the first variable in the music, the first variable in the model, the second variable in the model. So this right here is variable 1 with the coefficient for variable 1, variable 2 with coefficient for variable 2, variable 3 for coefficient of variable 3. So it worked, yes. And if it doesn't work, Devin, tell me immediately and I'll try to fix it, especially during mini term. I need to fix it really quick if it doesn't work. So I'm glad that makes those problems a lot easier. So if you know how to do these ones, so much easier. And so I just went a little bit outside this class, but that's why we use the B0, B1, B2 notation right there. Oh, I'm so glad to hear that, Devin. Thank you, Devin. You're at 100 points because I needed to mention that today. Thank you for asking that question. You just helped a lot of your classmates by being like, where's that at? And then it's a little easier to use. Huge help right there. Thank you, Devin. I appreciate that. So, and is it pronounced, it's Devin or, because it's like Evan, Devin? Got it, hopefully. Make sure I get everyone's names right. I'd be so bummed if like all semester I've mispronounced a name. Well, thank you. That's why, like, it's like, yeah, awesome, good, good, good. Okay, so which of these do you put as your X and your Y? Well, kind of makes sense that you would say somebody's SAT score explains their college GPA. Either of these could be X or Y, like someone's height explains their weight, someone's weight explains their height. How long you work at a company probably explains your salary. How big a house is probably explains the selling price. You can flip them. Yeah, I mean, the equation doesn't care, but it makes more logical sense. So what is X and Y like? How many people visit your site would explain your sales. So why do we have certain sales? You think about a company, they probably care. And yeah, like you want the one that like the company wants to understand their sales, their customers would explain that. Because the company probably cares about profits. Like they do care about their customers going to their site, but the customers going to the sites would explain their profits. It is true that your profits explain how many customers go to your sites, but what is the company looking to increase? And when you get to multiple regression, you would say like, well, our sales are a function of the customers that go to our site, how long they spend on our site, like what region they're coming from, all these different things. So all these good things right here. That's why we talk about multiple regression. We talk about more X's than just one, because the real world usually functions from more than just one X. Like what explains our sales? A bunch of different variables. So multiple regression is very important. 320. Cool. We have here mortgage rates and interest rates increasing, and they're going up by a certain percentage. There's the data. Cool. X and Y. And what do we notice right here? We see that there's a negative relationship right here. I see a little bit of QQ straight enough, no outliers, but the last, so we got QQ. Quantitative. Looks pretty straight enough. There is a little bit of a bend there, but we're going to forgive that. The outlier issue does not seem to be too big of an issue. This one looks to have an issue with plot thickening, where the model looks to get better down here towards the end of it. The model looks to have a little bit different of strengths to me, and maybe there's a little issue with straight enough. Maybe. We do have more advanced ways of looking into this. I don't want to go into real great detail on it, because it'd be a big topic. But for right now in Stats 1, we just look at it. And I will say this, exactly. Now, if I give you something that's not straight enough, Zulon's right. If I give you something that's not straight enough on the test, I'm going to give you something that looks something like this. That's not straight enough. If I give you something that's straight enough, it might look something like this right here. That's straight enough. Notice that the condition is not, it's a perfect line condition. It's straight enough. So this one right here is not straight enough. This one right here is straight enough. And so the top one right there is good and the bottom one is bad. This one right here is, I could see someone saying it's not straight enough. I'd probably say it's straight enough. There's a little bit of subjectivity, but there is a way to do a test on it, which we don't do in this class. There is a way to do a test to see if the line is the right model. It's called, can't remember the name of it. You'll have a p-value. The null is that the linear model is a good fit. I can't remember the name of the test. Doesn't matter. So we see right here that the correlation is statistically significant. The correlation for this model right here is negative 0.84, which is very statistically significant. Usually stronger correlations are more statistically significant, but once again, please don't think because the correlation is strong, and what do I mean by strong? Closer to negative or positive 1. Will the question on the exam be, yeah, kind of like that. What are the conditions? Stuff like that. I think it'll be very, very fair. I won't try to trick you on those. If it looks like it's one way, it'll be very clear. I won't try to be tricky. I won't be like, let me do something that's so close that it's like, no, don't worry. Good question, Kyle. So we see right here, how do you resolve the regression problems? I'll probably get into that soon here, Thomas. Great question. And you notice right here on this slide specifically, we see here a statistically significant regression. What we see in this graphic highlighted is unlikely by random chance, and the correlation is strong. Now be careful. This was our speed run earlier, that the correlation here was this is the correlation, was unlikely by random chance. It is statistically significant because the p-value is less than 0.05, meaning that this relationship highlighted is unlikely by random chance. There's the line. We see here for each 1 unit increase in interest rate, we see that we expect the mortgage and, that's right, actually. For each 1 unit increase in interest rate, we expect the mortgage in billions of dollars to decrease by 7.775. When interest rate is equal to 0, hear that again. When interest rate is equal to 0, we expect the mortgage in billions of dollars to equal 220. Now, would the government ever put out an interest rate of 0? That'd be amazing. If there was an interest rate of 0, how much money should you take out? If the interest rate from the government was 0, you should take all the money they'd possibly give you. Now, don't go and spend that money. Just go put that money in the bank and get like 1% interest on it, or 0.1, or anything. Because if you have an interest rate of 0 on the money you take out, and you put the money in the bank, you will just, just like, I'll never spend that money. I'll just spend the interest it makes. So the government would never put out an interest rate of 0. Be careful. I sometimes think that people think that this is the intercept. No, that's just, we didn't extend the graphic out. So if you notice, it doesn't even go to 220 because the line would have to extend out further because 220 is back below there. So, and that's why it's, economically speaking, there's so much crazy stuff. Jeff Bezos is, yeah, it's like, I will say this, like, my parents are so much better with money than I am, because they'll be like, oh, we've got this like low interest thing. We can take the money out and invest. Like, they were able to get like a second mortgage on their house for like, it was prime -1 or something, and prime was like at 3.5. So I think the interest rate was at like 2.5. So don't worry, this wasn't anything crazy. But they took out like the second. Why am I saying this personal information? But it's something you should know, is like, it's just, it's kind of a bummer, because my parents are obviously more well off than I am. And like, they always say like money makes money. And so please try to, if I can give you one bit of life advice right now, here's my life advice. Watch Dave Ramsey. Big proponent of Dave Ramsey. So all those baby steps right there. Watch Dave Ramsey. Start watching Dave Ramsey now. Brian's personal life advice. This is like personal life advice. Brian's personal opinions. But listen to him, not me. And I think he gives some good life advice on how to manage money. All about Dave Ramsey. What do you think, Hannah? What do you think, Hannah? Did it help you out? Do you feel like you, holy, that'd be insane right there, Ben. So, yeah, and it's tough, Camden. Like, that's why I really feel for people. That's really tough. And I'll tell you this much: I've worked through a lot of it too, and that's why I respect my parents, because they understand it a lot better than me. Yeah. So and here's the thing, Camden, is like, Brian's life advice time. Like, just start working on it. Like, think about, like, get some good advice. You know, I believe Dave Ramsey's good advice. And so, yeah. And he's an alumni of UTK. That's why he's awesome right there. So, start just, like, look for good advice, take the good advice, make it a part of your life. Vol for life right there. So that's Brian's life advice time. Because I strive to be more like my parents are with their choices and stuff like that. Because I'm like, Dad, why are you taking out a second mortgage? And he's like, well, because, I've got this and this, and I can do this and this. And I'm like, sure. I don't understand this stuff. I hope I said everything he did correctly, because I was like, okay, Dad, I don't understand it, but he's doing better than me. Yeah, exactly. So no, and well, there you go. Life advice time with Brian. Okay, cool. Let's do this. My parents don't watch these videos, I hope. Okay. We've got the intercept. We did the intercept interpretation. It didn't make sense because the government's not going to give you free money. Interpretations here. Examining those residuals. We're almost done with all the material. So I know I don't understand my health insurance. And I found out very quickly when I had to have my dental thing done that I have the wrong dental insurance. And that was had to grow up moment. And I was like, oh, got to change that over to the other one when we have open enrollment. Brian's life story. Make sure to section off that video. I should do that. I should do that. Okay, here we go with the last topic. And we're pretty much almost done with all the material. I know I say chapter 8, and you're like, how in the world chapter 8? Chapter 8 is so short. You'll be like, wow. And then we'll start doing assignments for the last like 50 minutes of class, and then we're going to hop into doing review. So a residual is an actual minus predicted. All of a sudden now we're reviewing. I hate that it changes this. Nope. Residual is your actual, which is found from the model, and it's predicted. That's the better way to understand it right there. We change it right there. I don't know what that means. So we go right here. The residual is the actual minus the predicted, and there's the notation below it. Cool stuff. What do you want to see in a residual plot? This is so big for 320. Nothing. Nothing. Nothing, 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 nothing. What is Brian saying? Here is how a residual plot will look. A residual plot will have a flat line through it, as best as Brian can draw. And you want to see this. This is no longer a regression. Here's the keynotes you should know. All residual plots have a flat line. Note number 1. All residual plots will have a flat line through them. All residual plots have a flat line through them that is centered at 0. Oh, is that order of operations? Oh my gosh. So all residual plots. Well, what it is when you think about what a residual plot is, great question right there, Camden. Why is the most amazing question ever? Camden, you're at 100 points. Because a residual plot takes this line from the regression, and that is 0. Does this make sense right here? I love the big questions are when you ask something that makes Brian super think. And you're like, yes. So all residual plots have a flat line centered at 0. And think about this. It's a plot of your residuals. So anything on the line or close to the line would have a residual that's basically what? Anything on the line or close to the line would have, and sometimes it zooms in a little bit so the aspect ratio changes. But anything on the line would have a residual close to 0. So it takes that line, just makes that line flat. Anything above the line would have a positive residual, and it just turns it into the vertical distance. It just makes all of these the vertical distance right here. So if that were to be that point, it would just be the vertical distance. There it just is. And then it could have been a negative relationship. It doesn't matter if it's positive or negative. Like this line could have went down like this. And you would still have a similar residual plot because now you just take the line and make it flat. Because anything on the line would still have a residual of 0. What you don't want to see is you don't want to see things like the plot thickening in a residual plot. Q, straight enough, no outliers, plot doesn't thicken. A residual plot is quantitative, but what do we analyze a residual plot for? To be very in-depth, we analyze a residual plot for any abnormalities in the residuals. Now, if you notice this residual plot right here, I usually add the line to it. This one didn't. But the residual plot, because this is your model, like this is the statistical model. So a residual plot or a horizontal line at 0 because is all the data. It's a horizontal line at 0 because this is your model. This model right here, I'll have to delete all the slides, but then I'll remember to put them back in because if I don't, you won't be able to see it. Okay. Doop. This line right here is that model right here. So does it make sense that this line right here is that line right there, as best I can draw it? Does everyone see how the line is the same line? So hopefully that makes sense. That line I'm highlighting right there is that line that went through the model. And it's just the line flat. So all we did was just take this model and make it flat. So now all you're viewing is all the residuals. You got it. That's why I like showing things like that. I hope it makes sense. Like to be like, okay, it's just that line flat. That's all we're doing. Boom, residuals. So now, is it just shifted? Yep, you take the line, flat, boom. Now everything's a residual. And so you can see the residuals a lot easier by just being like, oh, this residual right here is this much below. It's negative 30. So you literally right here, these are all the residuals. You can just tell like, oh, this has a residual of 33 or so. Boom, residuals. Now what you want to see in the residual, I want to see in the chat, what do you want to see in the residuals? In the residuals, you want to see this. What do you want to see in your residuals? Do you want to see like a correlation? This is when high p-values are good. Nothing, Claire got it right there. You got it. Claire and Camden, throw some people some points. Find someone in the chat who doesn't have their points, tag them. You want to see nothing. And luckily, we almost see nothing. We do see plot thickening, though. We do see an element of plot thickening. And I think I'm not overlooking at it because this is an area of thickness where this is thin. And that looks to be good job. Kate got some points right there. So Hunter, you get some points too. So we got this right here. That there is thickening in this. We don't want to see that. This one is definitely plot thickening. Oof. This is that is. I need that sound effect. And actually, we might even have a little bit of non-linearity because the linear model looks too. It's probably too few points. Like, you don't want that above the line. There's definitely plot thickening here, and remember, it could get thinner or thicker either side. Plot thickening means it changes. I don't want anyone to think that plot thickening. I don't want anyone to think that plot thickening is like it has to get thicker. It could get thinner or thicker in any direction. So both of these suffer from plot thickening or heteroskedasticity. My favorite word right there, heteroskedasticity. What's so cool about this? All of these things we're talking about can be done so easily with a command right here called check regression. And you just put your regression in, and it'll check the regression as long as the figures aren't too large. So look, residual plot centered at 0. What do we got right here? Ooh, the residuals don't look what? The residuals don't look to follow that's a histogram with a normal curve on top of it. This is a normal quantile plot. It almost looks like it's trying to tell me that the residuals are not normal. So when I check the normality of the residuals, which is going to be right here, it looks like I reject that the residuals are normal, but the equal spread is right here, and I don't reject the equal spread, and then we've got some linearity conditions right here. So don't worry, I just went way outside this class, but if you notice, I have a p-value right here to test to see if they have equal spread, the null being equal spread. Visually, it does look like there's equal spreads. We have two groups, that's why we look like that. And then we have evidence, or we don't have evidence of non-equal spread. We have evidence of non-normality, and that really shows up in both the histogram, you've got this down here, and the normal quantile plot or normal probability plot. Lots of names for it. But this p-value is associated with this, and once again, we see a review topic from way earlier where we talked about this earlier on. So hopefully that kind of ties it together, that I reject that there is normality in the residuals, but I do not reject that the residuals have equal spread. It looks like we would believe that the residuals here have equal spread. 5-minute break coming up very soon. So we're almost at 5-minute break. We almost got it. We're almost there. Almost there. We got it. R squared is our last topic for before the 5-minute break, and then we're going to come back, talk just a tiny bit more about chapter 8. It'll be over like that, and then we're going to start up review, and we will do assignments today. It's a big day today. That's why I said don't take the test today. If you can, take the test tomorrow. Today's a very big day. P-value was first introduced in chapter 5. Chapter 5, I think. I think I marked it in the video, so double check that. What is R squared? I want to see some definite. Morgan, amazing. Morgan, you're at 100. You definitely earned it. Percent of the variation in Y is explained by the variation in X. Amazing job, Morgan. Blank percent of the variation in Y is explained by the variation in X. What happened? Blank percent of the variation in Y is explained by the variation in X. Give me 2 seconds here. What did I do? Blank percent of the variation in Y is explained by the variation in X. Really? Well, this is going to be interesting. 2 seconds. This thing likes to troll me. One of these days I'll make it not break every day. Sorry. Okay, cool. Blank percent of the variation in Y is explained by the variation in X. He has so much tech trouble. Sorry. So what we see right here is we have how much our model is explaining, and we have how much the residuals are explaining. This slide goes way too much in depth. What? Is it really just this slide? It's just that slide. Okay, sorry. Wow. Can I undo? I can't undo in this. I have to redo. Let me go to this slide. What in the world? That was so weird. I know, right? I think I can just rechange this. I was like, I didn't do anything. I didn't. It was just that one slide. Cool. Cool. All right. Gotta remember to fix that slide. So, set it up so nice and neat. F, definitely F right there. So, pay respect. We see the model. I do know that meme, luckily. Not that old yet. So, we see at the model we have with the residuals, fun stuff. Let's get to the meat and potatoes of this, the real deal. So, what is R squared? I take it after class tomorrow. We'll probably do a little bit more review tomorrow. I would take it, if I was you guys, I would take it at about 4 or 5 p.m. tomorrow. That's when I would take it. I would take it at 4 or 5 p.m. So the most important thing we need to know is a few things. We were talking about this yesterday, that to find R squared, you literally just square R. To find R squared, you literally just square R. Now, I know it's capital R. Sorry, stats is mean. But R squared is correlation squared. And now you might say, well, why don't we just call it correlation squared? It's used in other areas of statistics too. R squared is used throughout multiple areas of statistics. Yeah, it's Camden, definitely study up. Study up. This is a big chapter. So we have right here correlation squared is R squared. Big stuff. And so, Camden, if you're taking big notes on this today, you should be all right. There's a lot of conceptual on this test. I think you'll be all right. So it's just this chapter is a bigger one. So next, what do we see right here? This was our protein and fat model. So since the R squared here is this, who's going to get 100 points and interpret this for me? This is almost literally a test question. Brian was looking at the test, and if you know how to interpret this, it says on the test, associated with, I like to say explained. We saw some people put the answers in the chat earlier on how to do this. Check it out. Jump calls it R square. It does, Terry. I'm dropping a lot of hints because they'll be taking the test later today. 58% of the variation Y is explained. Close. Zulon, you're so close on this. You're so close. You're so close. Remember, give it in context. So you guys are so close. 58% of the variation in something. 58% of the variation in something. Now, remember going way back. We got to go way back in time right here. Way back in time. 58% of the variation in what? Fat. Well, I think I see it. Devin, nice job right there, is explained by the variation in protein. And technically, you could do it the other way. Now, the equation would change if you flip it around. If you change around the equation the way it works, it's going to be a totally different, like, mathematical equation. You guys are getting in the chat right there. Nice job. 58% of the variation in fat can be explained. Why are we saying this? Because this is the X and this is the Y right here. So we've got 58% of the variation in fat, almost made a mistake, can be explained by protein, as Terry points out right there. So good to have you here, Terry. Terry, you should check your points, Terry. You can do the exclamation mark points to see where you're at. Terry jumps in every once in a while. I can see it if you want. You don't know how to do it. But people love checking their points. So wait, is R squared the same as Y hat? Interestingly enough, R squared is associated with Y hat. Now, when you think about this, I want you guys to think about this model for a second right here. If we had a model that looked like this, model A, or we have a model that looks like this. Here's our two models, and here's the data. We've got model A and model B. Here's model A, here's model B. Can anyone tell me what R squared would be for these models? Can anyone tell me what R squared would be for these models? Can anyone tell me what R squared would be? Everyone's checking their points now. Model A would have an R squared of what? And remember, it's correlation squared. It's correlation squared. Which in other classes would go above and beyond. What would A be? You guys are right, and so I think you know. Ooh, careful. We see a flip right here. A would have what? I want to see A equals this. I want to see A equals this. R squared would be 1 for A. You are correct. Because correlation is 1. Let's do another example for A. Graphic A could have also looked like this. And I'm putting these points right on it. I know they're big points. But that line, I want you to think about when you say that 100% of the variation in Y is explained by the variation in X. 100% of y's variation is explained by the variation in x. Does that make sense? Because if you know x, you know y. You know all the variation in y from that line. But when you look at b, how much of the variation in y do you know from b? Think that, what is the correlation here and what does it mean? B has a correlation equal to 0, so r squared equal to 0. So you understand none of the variation in B due to this line. That line explains none of the variation in Y. Does this make sense, what we call r squared? It's the percent of variation. Now I want to see this first person in the chat to write. This is one of my favorite sayings right here. R squared is not correlation. R squared is not correlation. Who's going to get the 50 points on that? R squared is not correlation. It's not the same thing. It's correlation squared. You got it right there, Devin, right there. And I think Coleman hasn't gotten his points yet, so Coleman got some points because we know r squared is not correlation. It's correlation squared, at least in this instance, but r squared is not correlation. It's not. It's not. It's r squared can have a value between what and what? R squared, I get so excited right here. R squared has a value between what and what? What values can r squared take on? I hate that slide. R squared, 0 and 1, you're right. Correlation is between -1 and 1. Correlation can go from -1, perfect negative, to 1, perfect positive. And r squared, think if you square -1, you'll get 1. So r squared takes on values between 0 and 1. 0 means that none of the variation is explained. 1 means that all the variation is explained. And so, cool. That's how much variation is explained. So remember, correlation is -1 because of the squaring. You got it. And it's a percent of variation explained. You can't explain negative variation. R squared holdout. Didn't say that word. Don't look into that. So intercept, give it context. Cool, cool, cool. Cool. We've done it. We are going to take a 5-minute break right here. Going to take a 5-minute break. So check it out. Set the timer for 5 minutes. I love it, Tara. I love it. We got some. We could do it now if you want. What would you like? What would you like a speedrun on, Camden? And then I think Sarah also had questions about nonlinear. So I'm gonna do Sarah's question real quick and show how we can do nonlinear. So let me hop over here to this and show a little bit of nonlinear. So, and I'll see if this answers it. So, when we do nonlinear models, so I'm going to go back to here to the original, and you can do it inside of Jump too, but since we're talking the advanced stuff, I might show coding. Well, actually, you know what? Height and weight are a really good one to look at right here. So we can look at the relationship between height and weight, and let's visualize it real quick. So it's going to show me the relationship between height and weight visually. And let me switch them because I like the graphic better switched around. Okay. So here's the relationship between height and weight. Do you see the issue over here? Okay, cool, Camden. We got that. Could you do a speedrun? I could try. That'd be a harder speedrun. That's a lot of topics. Oh, thank you, Terry. Slide number... Thank you so much, Terry. Terry, thank you for updating the slides. The orientation of this slide right here, do you see, look at the small change of where it's at. So when I'm showing it, I don't know why it's off center. All these slides stay in the same position except for that slide right there. So all of a sudden, as I was going through the slides and I do a screen capture, this slide was shifted over. So this is slide number 43 on chapter 7. Thank you, Terry, right there. You're awesome. Yeah, and then Thomas, we'll be doing it at the end of class, and then we'll be reviewing. I don't think we'll review during class time. We'll do the chapters, because that's a big thing, and then we'll do review after that. So, and then I think we'll do even a little bit of Kahoot stuff. So stay tuned. We got a lot to do today. Today's a very big day, and the test is through today and tomorrow. And I've dropped some huge hints. I've probably helped out on 2 or 3 questions pretty big. Now, there's a lot of questions, so good stuff right there. Question. No, you won't need to know those formulas. The formulas you will have to have, you can have written down as y hat b0 plus b1x, and e equals actual minus predicted right there. It's so weird. Yeah, you won't have to. You will, and so just to be very clear, you will have to calculate some stuff, but you won't have to calculate the formulas. Just to be very, very clear, because someone will be like, Brian, you had to solve equations. You will definitely not be using on the test the following formulas. Where are they at? I don't know where they're at. Wait, there we go. You won't be using these formulas on the test. You won't be using these formulas on the test. I highly suggest using the applet right here. So this applet, or this thing I made right here, is found under modules, just if anyone missed it before. When you go to modules, this is the Regression Solver 2.0. Just because this is not so much a math class, we use mathematics. So you can see right here, Regression Solver 2.0, 2.1. Please tell me if there's problems with it. I will update it due to students telling me you can make this better. You can change this right here. It's become this thing right here. Yeah, and we'll be doing that towards the end, Neelan. Great question. I'll show you how to do it. I'll do a few of the problems. You got it. And we'll hop back to Sarah's question. We're taking our 5-minute break. It's probably almost over. Oh my gosh, time flies. So does everyone see right here that there's a little bit of non-linearity to this? Do you see the line has a little bit of problem? We got some outliers down here. We've got outliers. We've got non-linear. Maybe a little bit of unequal spread right here. Like if I looked at this QQ, height, weight, both quantitative, straight enough, little bit of a problem here at the end. Like usually go into detail when you talk about these things. There's a little bit of non-linearity. And then QQ straight enough, no outliers. There's outliers down here, so I'm going to say there's problems with outliers with this plot. Plot doesn't thicken. I'm going to say that there's a little bit of plot thickening, as in it's thicker here than it is in here. So I'm going to say there's problems. Yes, there's review sheets. I'll show you that here in a moment, Christina. You got it. It's on Stat 201. Can someone drop the link in the chat for Christina for exam 1 where the stuff is at? You get 100 points first person to do it. Remember, you can only get up to 100, and that's like the super help thing. A lot of people are getting 50 points a day, and I put 100 out for the people who are going to do these big things. So drop the link in the chat for the exam 1. And so there we go. Boom, right there. It looks like it. So Neeland and Carly, first people right there. So that should bring you over to the page. Thank you so much. You guys are awesome. Helping each other out. Watch this. Now this model. 5 minutes is over. Oh, it won't visualize it. Will it not? Well, I can do it this way. Let me do this. Choose polynomial. So if I want to see, choose order, that's what it is, not choose polynomial. I can take this model I created, and I can use polynomial models through it. So Sarah was asking about nonlinear relationships. We can fit polynomial models. And so you can see here, using polynomial models, what we get. And I always think it looks so cool. So hopefully, Sarah, this helps explain that we can look at a second. So this is fitting a parabola through it. This is fitting a third order, fourth order, fifth order. And you think each polynomial allows another bend throughout the model. So, Thinking Thursdays, Camden, you're at the 100 points because that was some thinking right there. So it's Thinking Thursdays. I like that. Thinking Thursdays. I got to write down all these themes. I know Mega Mondays. Everyone knows Mega Mondays. Thinking Thursdays. Yeah, Camden, that's such a good idea. Yeah, no, and you can do this. And so now you get a really interesting output right here. You get R squared adjusted. So, so when you look at R squared adjusted right here, this is an R squared adjusted for how many variables are in the model. Because what do X's... Freaky Friday. That'd be too funny, Andrew. Like, yeah. We'll just switch minds, Andrew. You'll actually be teaching the class. It is actually that. Andrew has probably seen R squared adjusted, because what do X's like to do? This is my last little talk on this before we do chapter 8, which is a very quick chapter. What do X's like to do? What do X's like to do? What do X's like to do? X's like to explain. So since X's like to explain, the more X's you put in a model, what will happen to R squared? When you put in more X's, what would happen to R squared? Because R squared is the percent of variation in Y explained by X, or X's. So if you put more X's in, R squared will generally do what? R squared would go up. I should make that. I'm going to use that, Terry. So R squared will generally go up. So what can you do? You can adjust R squared for how many variables are in your model. Now, this is not within this class, but that's why it's called R squared adjusted. It's just an R squared adjusted for how many variables in the model. So if we do something right here, which I think I can put in 20, will it work? Yes. If you notice, this goes up to 20 polynomial degrees, which is ridiculous. So this lets me see up to like 20 polynomial degrees, which makes it bend all crazy like. And that'll explain more and more because it'll get closer and closer to the data. But when you do this, you're going to always have an R squared that's going up, but R squared adjusted might not always go up. If you notice, sometimes it's going down. And then we have Akaike's information criteria, which is a totally different thing. We're not talking about that. So you notice that R squared right here is a concept we learned in 201, which is used in multiple disciplines. R squared is a very important concept. And then we have R squared adjusted. We have press R squared. Oh my gosh, R squared is used so much. So what you're learning right now is used in multiple things. But you notice right here, it's just the percent of variation adjusted for how many variables are in the model. That's how you would interpret this. Hannah, you get your 100 points right there. Mega Monday, 10-point Tuesdays, Wacky Wednesdays, Thinking Thursdays, and Freaky Fridays. Hannah, you have to send me that in an email, though, so I remember it. And I'll start trying to make screens for those so we can have some fun transition screens. So, okay, let's hop back in. Okay, we got to put some thinking music here on. While Brian hops back in, I'm going to probably need another song right here. Brian's getting the notes as we talk about this right here. I can do it this way. I don't know why. So Brian's getting the notes. I can't see the sounds anymore. I'll probably overlap music here in a second. Let's put on some Mega Man. Oh, it's still playing. Put on some Mega Man here. So we're getting Chapter 8 notes. Chapter 8 notes. Here, we'll play Mega Man now. Regression wisdom. We need some wisdom for our regression right now. Chapter 8 notes. Chapter 8 is appearing on screen. Enable editing. Let's see if it's formatted the way. This is how it should work every time. Expand to that. Let's hop back to our main screen right here. Go back and let's see if it looks good. Does it all? Let's change this to 114 down here. Where's my zoom? This should be 114. I didn't change that. There we go. Look at that. It's got a tiny bit of an edge, but that's what I do. That's my format I've been using. There we go. We got this. That's what it is in the background, Needy. That's what everyone truly knows it is. It's Thinking Thursdays, or if you know the secret name for it, that's the secret name for it. It's got the secret name. I like that right there. Okay. Our last chapter today, then we're going to start working on assignments, and then we're going to review, so stay tuned. We're going to go do these things through office hours. And remember, I do suggest waiting till tomorrow to take the test. I'll even probably do a little bit of review tomorrow. So stay tuned for that. Test 2 has less material on it. Test 2 will probably be Wednesday to Thursday next week. And then I might do Wednesday, Thursday the following week because our class does end on Wednesday. But I will allow people to take it on Thursday because I know it's a lot to say, like, we're going to do class and then take a test. So we have to learn something new tomorrow. It's mini-term. Every day in mini-term is a whole week of class. Yeah, no, tomorrow won't be on the test. Tomorrow, no, Claire, great question, Claire. Tomorrow is not material on the test. This is the last of the test material right here. Tomorrow is not test material. Tomorrow is not, and I will do some review tomorrow. So I highly suggest, if you can, sorry people who can't, waiting to take the test till tomorrow. How long after the stream does it available? I think it's been posting at about 4 or 5. It usually takes about 2 or 3 hours. Sometimes it's taken up till 5, but yeah. And it posts the first 2 hours normally. Yeah, we've covered a lot. So in every day is like a week. So it's mini-term is so fast. Regression. Wait, we got to do it. You know, I'm going to start putting a note on here when I start so I can see. Because when I put the tags in, if I put like this in, I think that'll let me know that I'm starting the chapter. Here we go. So I'm going to try to remember that for myself for visual cues when I put the notes in. And let me ask this last question. Have people been using where it marks in the chapters when you go back and review? Have you guys been using that? Has that been helpful? So because you can like go over the video and show you. So if you didn't know that, hover over the video. Yes, I like that. How long do we have for the test? You have 90 minutes. Good stuff right there. Awesome. Well, I like that. That helps a lot. Good deal. Awesome. So let's put in this check mark right here. That'll help me know. I'll try to remember to keep doing that. That just means I'm starting it up. Time. Yours doesn't mark it? Cool. Oh, and it might be because I didn't put it in because I have to wait to put it in. And sometimes I put it in a little late in the day and I know we're so quick, but we got this. Let's do this. Regression wisdom. I would say it doesn't take the 90 minutes. I would say most people take about 50 to 80 minutes. I'd say pretty much everyone has enough time. It's like 50 minutes is a good amount of time to take it in, but take as much time as you want. I've never heard anyone say I didn't have enough time. Examining the residual plot, which is what we've done a lot of. So this will go a little bit quickly because it's a big review right here. We'll probably get it done in about 30 minutes, and you can navigate backwards. So examining your residuals. What do you want to see in the residuals? What do you want to see in the residuals? You want to see what in your residuals? Huge review right here. We've done this. What do you want? Nothing. So let's take a look at the plot right here. Here is the regression plot. How do I know that the one on the right is a residual plot? How do I know that the one on the right is a residual plot? It doesn't have it, but it should, I think. It's centered at 0. I mean, that's a good indication. It should say residuals on the side, because they usually do. And it would usually have a line going through it, indicating that this line right here, we shouldn't use the same color, that line right here is this line, and what do you notice? Do you notice how, at this point, the residuals are above the line, below the line, centered around the line? It's the same plot, but the line is flat. QQ straight enough. Problem with the straight enough right here. So this bent relationship that we see throughout the plot right here shows up in the residual plot. You want to see nothing. Now, who can tell me the other condition? What do we use residual plots for? To visualize the residuals and see if there's anything odd with them. Like this. The residuals look to have some sort of plot thickening. So there's some sort, and outliers too. You can see outliers in residual plots pretty clearly. There's some sort of plot thickening right here, which is a problem. You got it right there. I love the chat. There's some sort of plot thickening right here. Major problems. We don't do this too much, but if you notice when I showed you an R, you can look at your residuals in a histogram. You don't want extreme values. So these are residuals here that are very high and very low. So we don't want extreme values. Don't worry about this slide too much. This would literally just be outliers, which are most likely... The outliers are things like that and like that. But this one more is symptomatic of plot thickening. And I wouldn't have you analyze the residuals this way. If you want to look, it means change. Plot thickening means change. So it means it's going to change in strength. And the proper term for it, sometimes people call it unequal variance. And it's also called heteroskedasticity. I wonder if it'll even register that as a word. Heteroskedasticity. So let's write that right here. Not there. Where we go? Right here. Heteroskedasticity. Did I seriously spell it correctly? Oh, no. Right then, literally, it was thinking. Or did I? It does not literally. Yeah, that's what I thought. There we go. I don't know how to spell it. Is it just that I there? It takes so long to register it. 50 points for Brian. What? Oh, there we go. Heteroskedasticity. No suggestions. Okay, cool. There we go. There it is. Heteroskedasticity. Coleman, 50 points. That's a mouthful. Well, and you know what's interesting? Well, what do you think? We either have heteroskedasticity or we have what? We either have heteroskedasticity or what for 100 points. Who knows what the other one is? So we either have heteroskedasticity or what? You got it, homoskedasticity. So what does homo mean? Homo means same and hetero means different. So we either have the same spread throughout or we have a different spread throughout. So either you see the same spread throughout your plot, and it would look like this. This is the same kind of equal spread, homoskedastic. It's homoskedastic as is homoskedasticity. And then you would see you can see a heteroskedastic relationship. Why is this relationship heteroskedastic right here? Why is this plot here heteroskedastic? And you could make it a residual plot by doing the following. Here's the associated residual plots with them. That's the residual plot for the one to the left of it. And the residual plot for this one would just be the line flat. So we draw the bow tie again, and we see a heteroskedastic relationship right here. So these are the residual plots. I'll put a 0 there to indicate that. So you'll notice right there that the heteroskedastic plot has a differing spread. So the plot does thicken. That's a bad thing. We don't want the plot to thicken. where the homoscedastic one down below has the same thickness throughout. Homo meaning same, hetero meaning different. So you want homoscedasticity, where this plot right here does not show homoscedastic relationship. It shows a heteroscedastic, which means there's a difference in the spread. So we want the same spread throughout, which is sometimes called the equal variance. I've heard it called that in other disciplines. But we call it plot does not thicken here. Just a thing you should know. QQ straight enough. No outliers. Plot doesn't thicken. Make sure you know that. So, different groups, fun, plot the residuals. What do we see here? We've talked about this a lot, same plot from before. If I'm going a little quickly, it's because this is review. If you can't tell, Chapter 8's review material almost. We see a difference in the spread right here. This plot right here, is this plot heteroscedastic or homoscedastic? Here's the big hint. Is this plot right here hetero or homoscedastic? Which one is it? Do the spreads, it is hetero, which means it has plot thickening. So I don't want you to think for plot thickening, the plot needs to get thicker. This is why I maybe do an advanced topic here. We don't want to think, okay, it means the plot must get thicker. It means there's differences in the spread throughout this. Very evident differences in the spread. So this is a heteroscedastic relationship. Are these things outliers? I mean, maybe. It's more problematic for the heteroscedastic than it is the plot than it is for the outliers. Data. We've never put this on the test because I'm not going to even mention. Not going to mention. So don't worry about those slides. Skip those slides. So I tell people. We've done a lot of slides today, and those slides you should skip. Okay. So we understand residual plots should have nothing in them. This is one of our last. We only have 2 more topics for this. And this is extrapolation. Are you ready for your definition of extrapolation? First person to put it in that Thinking Thursdays, you know the secret term for it. So in Thinking Thursdays, first person to put in the chat. Coleman's kind of right. Coleman, you get the 100 points for today. He's thinking right there. Extrapolation is what? You might say it before I do it. I'm giving Claire 100 points. That's what it kind of means. Here we go. Claire and Coleman are at 100, but here's the definition I want to hear in the chat. You ready? Extrapolation, Jack got it. Extrapolation is going outside of the X bounds of the data. Jack got some great answer right there. Extrapolation is going outside the X bounds of the data. Extrapolation is going outside. Who's going to be the first person? Extrapolation is going outside the X bounds of the data. Brooke, nice job. You're right at 100. Nice job. Extrapolation is going outside the X bounds of the data. So it's kind of good and it's kind of bad. We're venturing into new X territory right here. Extrapolation is going outside the X bounds of the data. It's predicting things that your model has to extrapolate to predict. So we understand what's going on right here. Maya, you're at some 50 points. Nice job right there. And Jose, 50 points if I haven't given you them today. So we see right here, extrapolations, they can be useful, but we have to be careful. You have right here models predicting the price of oil in 2016 dollars. That holds the value constant because we want to compare like dollars today to dollars yesterday. So let's use, some sort of standard, like how much is it worth right now? Now, if you notice, the model is not so bad when it extrapolates from this point forward, and it's not so bad when it extrapolates here, because in the short term, extrapolation is pretty all right. Imagine you found out that Apple made, let's say, $200 billion this year. And then Apple has a model that says next year they're going to make $210 billion. Would you believe the model that says next year Apple's going to make $210 billion? Yeah, I would. I think it's reasonable. But then Apple has a model that says 1,000 years from now they'll be making $10 trillion. Would you believe the model that says 1,000 years from now Apple will be making $10 trillion? If you notice in the first model, you are extrapolating, you're predicting the future because you don't have that data. You're going outside the X bounds of the model. And then the next one, you can make a mathematical model that predicts 1,000 years in the future, but that's such a big extrapolation of your model that you're like, okay, this is a horrible idea. And so you notice that this model generally does pretty well at predicting short term, and it's almost by random chance, that it predicts, exactly. I like that right there, Zelon. So we try not to extrapolate. We use it in things like forecasting. But, it's like extrapolating and saying, imagine this. Do you think that studying increases your grade? Like, let's say, studying. Let's go hours you study. So we've got the hours you study, and we've got your grade in the class. And then we would say, okay, when you study more, your grade goes up, and here's like 100. And we got like 0 through, let's say this is 2 hours a day. This is mini term. 0 through 2 hours a day. Well, someone says, I'm going to study for, I look at Brian's model. I'm going to study all day, every day. I'm going to study, and I should draw where the model exists first. I'm going to study 24 hours a day, never sleep. What do you think if someone never slept for mini term and they literally studied 24 hours a day? They somehow pulled it off. Every time they started to get sleepy, they just drank more coffee. Like they're falling asleep just drinking coffee. And they're just like, I gotta keep studying, can't keep studying. And automatically Kelly sees something right there that the scores can't even go beyond 100. They would fail. Because we probably, outside of this model, the relationship might actually start to do something like this. Who knows? I don't know. You're extrapolating. I'm kind of guessing right now, but the model itself would do this. Here, let's draw it this way. The model itself would predict this. The model's just going to keep making predictions out in the future outside the X bounds of the model. Extrapolation, outside the X bounds of the model. But the truth, let's say we know the truth. That's a big thing for 320, but we don't. We never know the truth. All models are wrong. So the truth, if it were to exist, might be something like this right here. So the truth might be people who overstudy maybe aren't doing the quizzes. I think about myself. When I do that, I'm like, I remember not doing the work and then pulling. Just because you pull an all-nighter doesn't mean you don't study. But Brian Stevens in college maybe didn't do some assignments. And then the night before the test was like, you know what? I'm going to stay up all night. And then I'm taking the test. I'm like, I just want to go home and sleep. I just want to sleep. I take the test at like 10 a.m. and just pass out. I wake up at like 8 p.m. the night. Yeah. So a lot of experience here. A lot of experience. And I do agree. That's the biggest thing is like, who has had this experience? Because when I took linear algebra, here's Brian's life advice again. Brian's life advice. Just needs to, I need the button for that. I need it to appear above my head. I could do that. Ideas for the weekend. Who's ever had a test where when you went to study for the test, you're looking over your notes and you're like, I know this. Like you keep thinking to yourself, wait a minute. You keep thinking, why am I reading this? Why am I reading this? I know this. You keep looking and you're like, I know this, I know this, I know this. Okay, I know that. Why am I looking at this? I know all this. When I took linear algebra, I literally was like, every time I'm reading this, I'm like, yeah, I know this. I know this. I could read this without even looking at it. Those are the tests you want. When you look at your notes and it says extrapolation, and you're like, well, extrapolation is when you're making predictions outside the X bounds of the model. Devin's right. Yeah, exactly. And so keep writing these things down, keep listening in. Like, even if you say these things out loud, here's a tip too. In class, one of my teaching styles is I have people say things out loud. So if you even say to yourself, if you're alone right now and you just say these things or you don't mind people thinking you're crazy, I don't mind. My neighbors think I'm crazy probably. But if you're like, extrapolation is when we are making predictions outside the X bounds of our model. They are extremely unreliable, especially the further we extrapolate. So it is a matter of degree. Extrapolation is generally frowned upon, but extrapolation is when we are making predictions outside the X bounds of our model. You can see it right here. And generally speaking, they get worse the further you go out because our model is not meant to predict them. Our model doesn't have data there to anchor it to truth, or at least to values we know. Yeah, try to explain to someone, say it out loud. Those are good test practices. You got it. Great stuff. Yes, you're right. That's why we say QQ straight enough. No outliers. Plot doesn't thicken. And I'd make the class say it out loud. You should know this. You should know those like that. Okay, what do we got going on right here? Does anyone see the problem? 100 points for that person who's thinking Thursday and knows the immediate problem for this. You should see this and know that it's not QQ straight enough. No outliers. Who knows this? Yeah, Gracie knows that one. Nice job. I'll give it to Matthew right there. Matthew alluded to it. He's right. Matthew, you were quick right there and you got it. Matthew got the 100 points for thinking Thursdays. What do we see right here? We see that we have a problem with the plot thickening. Please remember, though, that plot thickening can take many different forms. Plot thickening means that it just does not stay a constant thickness. So as we pointed out in this example right here, this one does have an issue with plot thickening, and you see it there in the residual plot. This one does not have an issue with plot thickening, and that's the residual plot showing a homoscedastic. You don't need to know heteroscedastic, homoscedastic. It just makes sense to me. That one's got a little plot thickening. A little bit. This one right here is worse. That one there's worse. Interpretations, plot thickens, we're good. We know what that means. You know what? We're on to, then we just got outliers and we're done. So I want in the chat right now, these are review questions, and we'll have time for homework. Last 30 minutes is going to be homework of class today, and then we're going to review after it. And then we got a lot of time. So I want you to look at this right here, and I want you to first interpret the intercept. First interpret the intercept. I want you to first interpret the intercept. Don't worry if it's illogical. So remember, and I'm going to give you hints while I do this. You ready? I'm going to give some hints for people in the chat. This is review questions. For each 1 unit increase in, we expect to, I'm doing slope, sorry. When x is equal to 0, we expect to equal, let me repeat that and fill in the blanks, put it in the chat, 100 points for Thinking Thursdays. When is equal to 0, we expect to equal, when there is no winning, got it, nice right there, home attendance would be, close, and Zulon, you're at 100, keep that 100 right there. We need the full thing. I need the full thing as a sentence. If we were writing this out on the test, I'd be like, when wins is equal to 0, Neelan, I'm putting you at 100, but that's so close, but I think, yes, and Zulon, you're at 100. When wins is equal to 0, we expect home attendance to equal, Maya, you're at 100. You got it. These are Thinking Thursday questions. Towards the end, we bumped the points up on Thinking Thursday. You can only get Thinking Thursday 100 points when you get them. You can't transfer someone your points on You can't transfer the 100. You can transfer the 50, but the 100 is you earned it. So when wins is equal to 0, we expect home attendance to equal negative this. Can you have negative home attendance? You can't. This is an illogical intercept because it's an extrapolation of the model because no teams have ever won 0 games. So if you think about it, no teams have ever won 0 games. So if you look back at this model, you don't have teams down here winning 0 games. The model would actually go negative, and it's an extrapolation of the model. Like it would eventually go the Mariners tried. They tried, but they didn't achieve it. Let's go here, and let's look at who can do the slope for the Thinking Thursday 100 points. The slope is for each 1 unit increase in this, we expect this to increase or decrease by this. Remember as I highlight them. Oh, no, you don't add them. Great question right there, Jared. You don't add them. Good question, Jared. Jared, I'm throwing you 100 points for the Thinking Thursdays. I'm glad you said that. You would not add them. Good question on the Thinking Thursdays. You were thinking right there. Good question. When I don't see it yet, we got the slope in the chat, but I don't see the full interpretation of the slope. Be thinking those Thursday questions. So when for each 1 unit increase in that, for each 1 unit increase in wins, we expect home attendance to increase by this. Neeland, you got it. Let me throw another person in the Thinking Thursday 100 points. There should be similar question at the bottom. Down here at the bottom, you should see similar question. Click it, and you'll redo the question. You have to complete the question, then you can click similar question. For each 1 unit increase in wins, we expect home attendance to increase by this. William, you got it. Nice job, William, right there. You got it. So especially if you're really quick, you could like copy what the person says. So great job, William, right there. And Nicole, you got it also. You guys get it. That's it. For each 1 unit increase in X, we expect Y. So let me highlight it as I do it. For each 1 unit increase in X, we expect Y to increase by B1. It is increased because it's positive. So it's for each 1 unit increase in win. You could say for each additional win, you could change the unit to the problem. So you could say for each additional win, we expect home attendance to increase by this right here, by that number. Good stuff right there. Great stuff. And Valerie, is it Val? I hope I'm saying right. Valerie, I've seen you answer a ton of stuff. 100 points. And SpongeBob, you got 50 right there. But Valerie, just by you've been answering tons of stuff today. 100 points. And I hope to notice everyone doing that. But great job right there. So I appreciate that. And SpongeBob, and you got 50 right there because I said first. Got it. You got it. SpongeBob, you got 100. I feel bad saying you got. I can't feel 100. Okay, let's continue on. Beginning these Thinking Thursday points. Okay, outliers and their impact. I don't want people to think just because I stop giving points, you should stop answering. Might be a stupid question, but if we got the 100 points, do you automatically put it in? You need to email me. You need to email me for these points during class. Make sure to email me. Make sure to email me for these points during class. And I might have I might have an even better way. But so I'll think. Email me. Gotta email me. Yep. I know, right? You guys are doing such a great job. Like, I don't mind giving extra credit when you guys are working super hard on this because you guys are, your day's been made. That's awesome. So let's talk about outliers. What do we know from outliers with correlation? Yep, still email the points from yesterday. And remember, so many of you are doing so good at this. So my email would be something like this. That right there. You can, the title can be EC, Thinking Thursday, stuff like this. You can remove outliers if you have a good reason. Claire, amazing job right there. You can remove them if you have a good reason. And what can they do? What can outliers do to it? They can do anything. They can do anything. Get that 3,000 right there. You got it, William. Outliers can do anything. They can do anything to correlation. They can do anything to regression. So when you have outliers, you ruin it. Yeah, they can ruin it. They can make it. They can do anything. It's an outlier. Makes it, ruins it. You got it. So we usually say that outliers need special attention. We draw our attention to them. We see what's going on with them. We've got Bozo the Clown. Wait, that's Nader. So Bozo the Clown's coming up here. There's the Bozo because of the shoes. So this is actual real data. A lot of people always want to know what's going on. And we're not trying to get political here. We're just pointing out real data. If you look at, this is what the book uses, so I'm using it. But when you look at this model right here, what do you notice about something? Brian's trying to draw your attention to this right here. What's Brian trying to draw your attention to right here? This is a very, 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 very large residual. You are right. There is a very large residual on this, and Buchanan got way more votes than we would have expected. Both Buchanan, both Buchanan and Nader are third-party candidates in the 2000 election, and this is Palm Beach right here, and they had what was called the butterfly ballot, and so it's way more than we expected. Now, here's the thing. Okay, wait a minute. We got a famous saying. Who here can get the 100 points for Thinking Thursdays for the 100-point sayings that we say? It's not all models are wrong, some are useful. We say something, the blank, 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 the blank, blank, blank. Who knows the Thinking Thursday right here? Who knows the Thinking Thursday? You guys are killing me in the chat. The stats don't lie. The statistician does. Jack, Kate, and Camden, and Skylar, you got your 100 points. Sure, Skylar, you got them too. Thinking Thursday. You can tell it's the end of class. Oh my god, you guys are killing me in the chat. So, okay. The stats don't lie, the statistician does. And I'm not saying people lie. These are just the numbers. These are the numbers. Why did it happen? We can all come up with theories. And no one, some theories might be better or worse, but the numbers just are. There's a very high residual here. It's a very, very large residual. That means that Buchanan got way more votes than we would have expected him to get via Nader getting certain votes. And you can see that Nader's votes do kind of explain the amount of votes we would expect Buchanan to get. I don't have it on this. Wait a minute here. I do. I have it on the screen. I must have set that up on a day and forgot about it. I don't have it as a button though. So the residual tells us how much our model missed by. You guys can start throwing that chat when you have the crab rave. The residual tells us how much the model misses by. And you can see how much it impacts the model. Think of it as a planet with like a gravitational pull. It's going to pull the model towards it. The blue line is without the residual, or without the outlier, and the red line is with the outlier. So imagine if Brian were to take this and move it up here, way off the screen, then the model would follow it. Do you want that? Do you want 1 point dictating your model? Do you want where there's no relationship in the data, but then 1 point gets to decide You don't want that? No one wants that? Okay, we won't do that. We'll keep the no outlier condition because outliers can do anything. They can make a correlation strong, weak, positive, negative. They can make R squared strong, weak, positive, negative. I like that there, Coleman. They can do anything. Outliers can do anything. They can do anything to correlation. They can do anything to regression. So it's just showing impacts, as long as you know it's anything. Last topic. This is the last topic. It can be done in 5 minutes. We got this. And then we're going to start doing the homework and the quizzes for these because they are a little bit difficult. And then we'll review after. So we'll have homeworks and quizzes during this. Okay. Lurking variables. I've already mentioned lurking variables one time today. But here's a big thing we should know instantaneously, and we learned it last class. Thinking Thursday points right here. Something is not something, which also would apply to regression. Because regression is built off of correlation. I kind of said it. So correlation for the 100-point Thinking Thursday is not causation right there. Sarah B. and Devin, you both are at your 100 points. Remember, you only get up to 100, but you got them right there. Correlation is not, and Christina and Nicole, you guys got it. Gallies and gals and everybody. So we have correlation is not causation. So if you're telling me correlation is not causation, I want you to think about this. If correlation is not causation, don't we build R squared off of R? Like, don't we use R squared to make R? Which R is not correlation. But don't we square R to get R squared? So wait, if correlation is not causation, then when we do regression models, they don't show causation either because we're doing kind of an extension of correlation. So don't think that regression is causation. You can't say because this variable has this relationship with the other variable, it causes it. Like, do you think your shoe size would cause your IQ to go up? No. It's just data making a line. It's a line that explains what we see in data. It doesn't say anything causes anything. So there is no causal relationship. When X and Y change, there's no causal relationship. We talked about this in chapter 6. But here's something true. I want to go to the next one. I like the next one better. The more TVs you own, the longer you live. So, man, I own a bunch of TVs. I only own 2 right now. You count these screens. I own like 4 screens. So the more TVs you own, the longer you live. It's a very true statement. No, it's totally true. But does owning more TVs cause you to live longer? Why would owning more TVs... I like Sarah's answer right there. Richer country. And these are for countries, technically. Great answer right there. Thomas, 100-point Thinking Thursday. You're reading the slide as I'm doing this. It is for countries, like the amount of TVs per person, square root, so they're doing a transformation on the variable. Don't worry about that. But it's signs of wealth. Signs of wealth show signs of affluency. Signs of affluency show access to healthcare. So we just see that. And once again, here's the thing, though. That might not be true. Brian is a statistician, kind of. He's a business analyst. Coming up with his own. My dad hates it when I say I'm a statistician. He was like, "No, you're not." It's like, okay, I do business analytics. He's like, oh yeah, that's what you do. There is a correlation, though. There is a correlation. This is very, 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 very correlated, but it's probably got a correlation of like 0.8 or so. That's probably a correlation of 0.8. And the linear model is pretty straight. There's a small bend at the end of it. I'd say it's straight enough. It's really just that one point. It's straight enough. But we can't say because people own TVs, they live longer. We can say that they're correlated, but it's not because you own TVs that you live longer. It might be a lurking variable. And the lurking, what lurking variable did we identify? What did we propose as a lurking variable? I like all the answers in the chat. What variables did we propose as lurking variables that are actually doing this? And we talked about this yesterday too. Wealthy nations, exactly. Do you remember yesterday when we talked about things like, we talked about we have ice cream and we have sharks. And it is true that the more ice cream is sold, the more people are attacked by sharks. But we have lurking variables here. And what's the lurking variables? The lurking variable is Z. And it's probably just summer. Now, we can't say we know it's summer, but we can say there's reasonable evidence, or like, and then someone say, I don't believe you. But like, okay, well, show me something else. And you can actually do this. I'm not going to show you how. You can control for lurking variables, and if you control for the lurking variable, it will remove the variation. it'll show that the lurking variable accounts for the variation. So Andrew's probably seen this. Andrew, have you ever seen in a multiple regression how we can control for lurking variables because multiple regressions deal with all the variation, the variables, and it sees where the variation is attributed. If you include a lurking variable in a multiple regression, if it's accounting for the variation, it's Nicolas Cage. Sharks like ice cream. Yeah, they do. They might. Maybe there is something. Because if you controlled for summer and you control for like ice cream sales summer and shark attacks, like if you predict shark attacks by ice cream sales in summer and all of a sudden ice cream sales, like more ice cream sales when you control for summer. So you can control for a lurking variable. That's kind of what I'm saying. I don't want to go too much in depth. I got to stand try. We got to get to the homework and the quizzes. So free time, warmer weather, instincts of sharks. Yep. Sound like, oh, thank you. I appreciate that right there. We have the last thing right here. This is I know I keep saying last thing. I keep forgetting there's one more thing. I think everyone's going to get this because we did a whole big talk on p-values earlier. You ready? You understand this if you can tell me the answer to this question. You ready? When you look at the slope, which of these slopes, slope A or slope B, looks unlikely by random chance? Which of these slopes, don't answer yet, I'm going to put a vote in the chat. Which of these slopes looks unlikely by random chance? Which of these looks unlikely by random chance? Let's go to our voting screen. I got to hop over to the votes. The votes will be up here in a second, so get ready to get to vote. Be thinking of your answer right now as I go over here and get the poll ready for answer A or answer B. I need to keep very similar things so I can easily edit these. So the question is going to be which choice, and we're asking which of these looks unlikely by random chance, option A or option B. And I should remember to do it this way, and then I can always do option A or option B. I'll remember I have this set up this way. So which of these looks unlikely by random chance? So which of these looks unlikely by random chance? Be voting with your vote B or vote A. Who knows what the answer is? I don't know. Which of these looks unlikely by random chance? You're getting it. Nice job. You guys got it. Awesome work. It is option B. Great work. Don't worry if you got it wrong. There is still time. We are going to talk about this just briefly here, and then we're going to start doing the assignments. Great work. When you think about what is unlikely by random chance, it does help to kind of know what the null is. Remember, every test, we talked about this way earlier, has a null. Do you think the null is that there's no slope or there is a slope? What do you think the null hypothesis is? Be a good one, right? It's a decent question. What do you think the null hypothesis is? That there's no slope? Be careful. The null is actually that there is no slope. The alternative is that there is a slope. And I didn't do it in statistical notation. I just kind of wrote in words. Tell me, does this look likely if there is no slope? Does this result here look likely if there is no slope? I want you to look at the line and be like, does that look like a likely result given there is no slope? I'd say yes. I'd say it looks very likely given there is no slope. And this right here looks what given there is no slope? That graphic right there, if there is no slope, looks very what? So yeah, this might help Camden keep asking. This one right here, this graphic I'm highlighting, looks very not likely. So what am I going to do? I'm going to reject the null and say that it has a slope. So if I'm rejecting the null, the p-value for this one must be what? The p-value for graphic B must be what? The p-value for graphic B must be what? I'm rejecting the null. The p-value is low. You got it. Less than 0.05. Nice answers in the chat. And this one, I don't reject the null. I let it fly. I let this null just be. I say, sure, null, you do your thing. I'm going to keep believing you at this moment. I'm from New York. I am from New York, but I don't know how to do New York accent. What you do? I'm walking here. Is that Jersey? So we're just going to let it fly. You can walk here. You can walk here too. You can fly. No, you're good. Worst New York accent ever. I actually do have a New York accent sometimes when I say things like water or straight off of Jersey. I like my northern accents. I say water or something or dwat. It's like my W's and O's are sometimes like what and water. I think I have a little bit of Canadian like yogurt or something. So I want you to look at this. Is that same one? Really? I don't like that example. Okay, let's hop to the screen. I'm gonna do my own example. I don't like it. Where's my screen at? Okay. This is the last thing. We've got 20 minutes for quizzes. We went very in-depth on lecture today. Here, let me open up some new data right here. And let's make some data that looks random right here. So this is how you do regression inside a jump, and then we're gonna start doing assignments. Oh, did you grow up like in Niagara Falls area? Do you know Bath, New York? I lived in Bath, New York for a little bit. So if you know like the Adirondacks or Finger Lakes area, then you might know that. Yeah, you know what I'm talking about right there. So you have a Canadian accent? Cool. Like sometimes I get that Canadian. Maybe it's because I went to high school there a little bit. Ontario. My dad was actually born in Canada. I don't know where he was born. I mean, I know he was born in Canada. I don't know where. I'm trying to put in random numbers right here. I'm trying my best to put in random numbers. I am trying, but humans are not very random. I'm trying to put... Oh, we don't want that. We want this. I'm trying to put in random numbers. Trying my best. Humans, that's not random. Okay. I guess I could use jump generate and run random numbers. I forgot how to do that because I don't use jump nearly enough. You can generate random numbers. No. Okay. Brian tried to do random numbers. If Brian put in random numbers, how should this look? Should it look like a line? Should it look like a parabola? Or should it look like a... How should it look? How should it look? If these are random, it should look like a blob, a circle, a random. That's what it should look like. And the p-value should be very high for correlation. The correlation should be very low. To do correlation inside of JUMP, you go here and you go to multivariate methods, multivariate. You double-click the variables you want. It makes a correlation matrix. And yes, I did it. Now, this is not regression. The correlation is very low, and the correlation will not be statistically significant because this correlation is likely by random chance. Here's the p-value telling us that this very low correlation was unlikely by random chance. Now let's go and let's look at the regression for this. And when we go to the regression right here, we want to predict y. It's just called y. And we want to use x. Now, if you notice we fit the line, do you think the line will have a big slope to it, or do you think the line will be pretty flat? Flat or sloped? Flat or slope? What do you guys think? Look at the data and be like, I say flat too. You guys got it. Let's fit that line. And boom, the line looks pretty flat. Now, when you look at the p-value, will the p-value be high or low? Uh-oh. We've got some interesting stuff right here. Will the p-value be high or low? Remember, the correlation was not significant, and it sounds to me like regression and correlation are very similar. Great job, Hannah, right there saying it. Hannah, you're at your 100 points. And Jack says very specifically the p-value will be very high because what we're observing here was likely by random chance given, to look at the slides again, there is no slope. So we were talking about the null for this being there is no slope. So remember, we said the null is that there is no slope, so the p-value would be very high right here. So going back to our data, we see a very high p-value right here for the slope. Please note, this is a huge note, one of our last big learning objectives. We're right about going to do the assignments right here. But you'll notice here that the x is your slope. Watch right now as we go and we change the data and we look at it changing. Don't snap. Good. And we're going to change our data right here. So we're going to click the auto recalc and we're going to make a slope appear. So auto recalc has been initiated, and we're going to make a slope appear. Oh, that got a little more sloped. Cool. This should help out. Do you guys see the slope appearing? And what is happening? Watch this p-value down here. Rewind the tape if you need to, and watch that p-value. Do you see the p-value? It should be going down a little bit each time. And you see the slope start to get a little bit stronger. And you notice the r squared is also going up. Does everyone see this line is doing better at explaining it? I wish I could click. Do you see that it's getting stronger? The slope is getting more significant. Watch the x, not the intercept. The intercept is, no one cares about the intercept. Go put a 20 here. That'll help it a lot. We've got a lot of outliers now, but if you notice, as I do this, it's getting more and more significant. Oh, wow, that's ridiculously... Look at this. That doesn't look by random chance anymore. That's definitely not by random chance. And you'll notice here that the r squared is getting very close to what? You should be watching this and thinking what's happening. The r squared is getting super close to 1. At this point, 100% of the variation in these points is explained by this line. And it actually can't even calculate them now because it's basically like, I don't know, just math. Now it can still calculate. That's a ridiculous outlier, but still ridiculously significant. It's 73.1% of the variation in y is explained by the variation in x. We can go back in time right here, and you can see it get less significant as the points get further and further away. You're noticing it get less significant, and r squared is also going down. So that's a rewind of time right here. So all of a sudden now it's like super insignificant. Now this line explains like nothing. And here's the p-value we look at. This p-value right here tells us if what we're seeing, the relationship between y and x is statistically significant. And it's based on the slope. Now do not look at the value of the slope. How do we know if the slope is significant? Not by the estimate of the slope, which is here. This is the estimate of the slope right here, and it's also here. To know if the model is significant, your last major note, first person, thinking Thursday, the way to know if your model is significant is the p-value of the slope. Neelan got your 100 right there. Who else is going to get it? Who's going to get their 100? The way to know if the model is significant is to look at the p-value. Nicole, you got your 100. One more person. And Kelly right there. Great job. Excellent work. You have to look at the p-value, but I want someone to say the p-value of the slope. Boom, Devin, you got the 100 right there. And Ethan, too. And Thomas, Goon, we got it. The p-value of the slope. This model is not significant because of the intercept. No one cares about the intercept. You'll hear me say it a lot. We care about the slope. The intercept just tells us the intercept is not 0. Cool. Think about that. I just said this tells us that we have good evidence that the intercept is not 0. This, last thinking point Thursdays before we start doing assignments, this gives us good evidence that the slope, currently, we might believe that the slope is equal to what? This gives us, we would probably think that the slope might be equal to, yeah, we'll take a quick break. We'll take a 5-minute for homework. We might think that the slope is not equal to 0. I mean, excuse me, this one would have us think that it's equal to 0. Sorry. Why did I say that we might think the slope is equal to 0? Because the p-value is high. If the p-value was low, I can't bring time forward, can I? No, I can't bring time forward. Went back in time, and now I can't go. Wait, I can't. I got another data set. A strong correlation. I don't know where a good data set is. Oh, wait, sure. Pizza subset. No. Sure, we'll use haircut data. It might be confusing, but you can get this. We'll see if this one's statistically significant. It's not. Line's very flat. Not significant. Don't look at this one. That's intercept. That's your x. This is your x variable right here. So as everyone see, this is not a statistically significant relationship. The line is mostly flat. But the line being flat, don't just look at the line and be like, it's flat, it's not significant. It is true, the flatter it is, the less significant it is. But here's a trick. Last thing I'm going to say. This, if I am correct, we should not be able to even calculate it. I don't think it'll even give me p-values here because you will get a correlation of 1 with these. So we should, if I am correct on what Jump's going to tell me, it won't even give me a p-value. And the line will be perfect. It didn't even give me a p-value. It's just because, yeah, this is what will happen when you have 2 points. So it's not even giving me the p-value. I have to get a third point in here for it to actually calculate p-values because this is just what happens. So when you have 2 points, they do this. But if we get a third point in here, then we should get a p-value of, am I going to get a p-value close to 0? Let's do it this way. Am I going to get a p-value close to 0 or a p-value close to 1? Be careful. That's going to follow the line very well. Am I going to get a p-value close to 0 or a p-value close to 1? Close to 0. Oh, it's not even oh, I thought it'd be significant. Oh, because it's 3 points. Yeah, there it is. But here's I'm showing you so many crazy things right here. If we were to do x equals 100, and we were to do this equals to 1.1, and then this were to equal to 100, and this were to equal to 1.11. Oh, it does look like that. It's the scale. It's definitely, so the slope right here is so tiny. Sorry, I should stop. I wanted it to visually look like a flat line, which you could, if you extended this all the way out, if you made it more proportionate, it would start to look like a flat line. So if you did, don't be tricked, because if you did something like this, Now that looks like a flat line. It's just the scaling on it. So this is still, it's almost statistically significant. Now that is statistically significant, even though I made the line look flat. So it is true that more sloped lines are statistically significant, but how do you know if it's statistically significant? You look at this p-value right here for the x variable, which is the same as the p-value for the model. What is the chapter in? Oh, let's put that due on the weekend, Claire. I think that'd be good. You guys have a lot of stuff. Let's put that due on the weekend, and tomorrow we'll cover that tomorrow, and we'll have some more fun tomorrow. Tomorrow will be easier day. Tomorrow will be a lot of review. So we're going to do a lot of review tomorrow, and it'll be a lot easier. Thank you, Claire, for pointing that out. Randomness is, it's an easy chapter. The homeworks are a little bit tricky. So I've got some really good videos on it. Okay, so 5-minute break. Take a 5-minute break.
I didn't get that.
Set a timer for 5 minutes.
Okay. 5 minutes and counting.
And I will try to... It's just there's a lot of material in this first test. And if you paid attention throughout all of class today, I think you will understand how to do regression pretty well. If you were writing the things in the chat and writing them in your notebook, you should be pretty good. And regression is a harder one. So ask any questions you have right now. Ask the questions. Brian's going to disappear. I'll be right back. I'll be back in 20 seconds. This class is sponsored by Izzy Drinks, Izzy Fruit Drinks. All right. I don't do that. I'll be right back. No, I'm back. I'll drink it later because I'm figuring it might go for another 2 hours. So, all right, here we go. So, what do we got? What do you think? So, are we still doing the Kahoot after you bet? We're gonna do a Kahoot review after this. So, we'll do. What will we do? How will I can send it out via an announcement. That's what I'll do. I'll send out the Kahoot code in an announcement, so you'll know it. Still got a few minutes here. What other questions are there? Let me pull up the homework. Let me get that Mike Tyson's music going. Let's get that Mike Tyson's music going. Let's do. You guys are so. I can make that a command. I can make that. I need to know. Don't tell me what it means. I need to know. Like I want to watch it with someone super awesome. It's like so fun to watch things like that with someone, and then I guess the fun of watching a show is like when you're watching with someone and you're like you get to be like, oh, like afterwards and be like, that was, I don't know, and just kind of experiencing it makes it so much more fun. Oh, you gotta play. Did it end? Gotta play another one. Let's play our Mario music. I think we had Pokemon battle music we needed? So we need some more stuff right here. We need some Pokemon battle music. You guys tell me via email and stuff. I'm gonna try to bring in those memes too. So we got chapter 8 homework. Ah, that's not the homework. Dr. Brown. I cannot see. Okay, there we go. Cool. How's chat doing? Exam 2 Wednesday. I think we're gonna do exam 2 on Wednesday and Thursday. So it'll be like a 2-day event. It'll be a 2-day event. So good questions in the chat right there. A 2-day event, exam 2. A lot of times when I'm playing music, I'm probably not looking at the screen. No, do ask questions. I just wanted to tell people that. Are you Ash Ketchum from Palatine? Nothing like, what is it? When does he get to go out? When is it on his 10th birthday? How old is Ash Ketchum when he leaves a 2-day statistics event? He's like 10 or 11. It's like his 11th birthday or something when he wakes up. He's 10, that's what he is. Yeah, it's like, hey, it's your 10th birthday. How about you go, like, I'm kicking you out of the house and I'm giving you this wild animal. I mean, Pokemon are nice. I mean, it's not all Pokemon are nice. There's some crazy Pokemon that like parasite Pokemon. Like when you talk about like parasect like that. It has a parasite on it. It's a Paris that got a parasite on it. So how about you go and never come back, and you remain a child for decades. They just told a 10-year-old to go out of his town. Kind of, sort of. It's kind of is like that, Joseph. It kind of is. Yeah. They need, Smosh did. You should watch early Smosh. I haven't kept up with Smosh after Ethan, and I think, is Ethan still doing it? Because why can I not remember? I can see his face. I can think of the other guy's face. Like every time I see it, why can't I think of his name? It starts with an A or an R. Oh, why can't I remember it? I think he's dating Glam and Gore. Glam and Gore is a cool channel too. Anthony, yeah, Anthony, yes. Ethan and Anthony, you're right, it's Anthony. Thank you, Scholar. You get the 100 points Thursday right there. We're still having our little fun in between. Yeah, and he's dating Glam and Gore, which she has amazing, like her, like, check out, if you like makeup stuff, check out Glam and Gore and kind of what she does. It's Glam and Gore, so that's what the channel's called, but we give shout out to all the YouTubers, because they need it, because they got, a million plus. Someone was like, he thinks he's a YouTuber. Well, I'm on YouTube, but I'm not like, yeah. I do want to mention this though. You know what's really, really cool? I'm a YouTuber because I'm on YouTube, but we have I don't think I've told you guys about this yet. We do have someone at UT who was and still is a big time YouTuber. I don't think I'm anything special because I'm on YouTube. I'm on YouTube. But this is Fatty right here. I always said Foddy, but he was like, Brian, it's Fatty. So that's Fatty right there. And if you notice, it's 2015. I actually met him when he was a freshman, and I was finishing off my master's degree. Like 2010, 2011, he was a freshman. And Barack's Dubs, there you can see his video editing right there with all the tracks and all the cuts in it. But his channel has over 1 million subs, and he was on like Good Morning America. You see, this is 2015, and he's got right under 3/4 mil and 156 million views. We're still trying to get to our millionth view. Yeah, his videos are great. So you got to watch, subscribe to Brock's Dubs. We'll give a shout out here to Fatty right here. Great guy, torchbearer at UTK. Yeah, really, really super nice. And he's given me advice and stuff like that. So I really felt bad when I read that in my review. Like, he thinks he's a YouTuber. And I wanted to be like, I'm just a person. If you see me on campus, you can say, hey, like, I'm not be like, you can say hey to me. That's all right. I mean, yeah, I'm a person. Be like, hey, Brian, what's up? I think Andrew's been to office hours. Andrew, am I just a person? Is there candy in my office before all the COVID craziness? Is it just Brian's a person? You just say hey to him and you talk to him like a normal person. I mean, don't be mean to me because I'm your teacher. But I know why. I don't think I'm special because I'm on YouTube. I like this though, and if you're on YouTube, you're a YouTube. So there's always candy. It's just chill. It's just like, by definition. So by definition, I am this. By definition, Brian is that. That's like you're on YouTube, you're a YouTuber. I'm not here. You can go on YouTube and be a YouTuber. Cool. We're all YouTubers now. Yeah, exactly. It's like, and usually if someone does something so wrong that it would incur hate, you just say like, I'm just gonna not have that person in my life. I'm just gonna, especially if they're become that problematic, you're like, no, just not letting that in. Gonna stay positive. I agree. I try not to. You gotta do something really, 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 really. It's like, I don't know. So as I get older, I don't know. I don't think I'll do it. Make sure to keep me. What's up, guys? It's Brian back for another video. Give me a like and smash that subscribe button. And don't forget to ring that bell for notifications. Subscribe to my Patreon. All that good stuff right there. What's up, Stat Nation? Okay. I like it right here. Coleman, you got your 100. You ready to do this? We ready to do this? We ready? Let's do this. It's noon. It's office hours time. Some of these days we've been able to do work during class. Other days we have not. And I'm going to always try to do as much problems as we can during class. So here we go. Let's do this. Let's get started on this. I wish I could put a check on the screen. I'll move the thing else so I try to remember where it's at so when I mark the video. For many people, breakfast cereal is an important part of fiber in their diets. Cool. Cereals also contain potassium, a mineral. It's a mineral. Now we see a regression equation. So all I care about, I think it's the first time I've actually read this question. Please note that this is doing what? What does this mean we are doing with this regression equation? Someone explain to me in words, we are doing what right here? We are something potassium. Devin, nice job right there. We are something potassium. Because this is like the predicting, Neelan, nice job. That is the predicted potassium being explained by fiber. Fiber is the X variable and potassium is the Y variable. We're trying to understand the potassium by using fiber to explain it. So it says that something has 9 grams of fiber. That's where it says it right there. Since it has 9 grams of fiber, we're just going to literally, as Devin put in the chat, thank you so much, Devin, put 9 into fiber right here, which means we're going to go 9 times 28. Then we're going to go right here, get to 37, and that is the predicted. Now, this is Y hat. It can be called potassium. Oh, I dismissed it. It's going to do it again. Delete all timers.
I stopped the timer.
Thank you. So we have here that we have the predicted potassium is this. We copy, we paste, we get the answer right. We go on to the next question. Same sort of question going on with potassium and fiber right here. The predicted regression model has yada, yada, yada. What does it mean that a residual is negative? Now, pause. When you hear a residual is negative, you should think of this line, and you should imagine the point is where. Oh, and I'll go back here in a second, Thomas. You got it. So the point is where, if this line, if it has a below, the point is below the line because the residual is negative. If it was 0, it'd be on the point. If it was positive, it'd be above the line. So I want you to think about this. This means we're predicting potassium. This means it's below what we would have expected to be. The potassium content is actually lower than the model predicted it to be. Here's the model. This line right here is the model. So the actual potassium is lower. And we could confirm this. Let's make up a fake example right here. You ready? And then we're going to go back to the Thomas question right here. So when we have this right here, we could confirm this. We said the actual was lower. So we're saying it's actually lower than the model predicts. So let's solve for the residual. Residual equals actual minus predicted. And let's make up some numbers. We said the actual has to be lower than the predicted. This is an example where the residual would be, the actual would be lower than the predicted. So what is the residual now? It's what? The residual is, and a key word when I say the answer, the residual is, can anyone solve the residual? Which is actual minus predicted. It is -5. It's -5. So you're right, it's negative. That's the key word, is that the actual was lower than the predicted. And we see when we go back to the answer to confirm that it's below the model right here. So it has a negative residual. So this is the actual down here, and this is the predicted. This is the actual point. So it's a point. This is just like a point right there. And then this is the model. So it's actually lower than predicted. Did we get it right? We read it correctly. Let's go back to the first question. Just to confirm for this first question here, and Thomas, expand upon if I don't give enough information. But in this question, we are predicting the potassium a cereal will have. Like when you look at the label on a box, it will have potassium. Now, we are going to predict using the fiber in a cereal. So this is saying, like, I tell you a cereal has, let's say here, and I'll make this very clear. If I told you a cereal Brian has, Rice Krispie Treats has 4 grams of fiber. Rice Krispie Treats have 4 grams of fiber. If you're following along, try to predict how much potassium Rice Krispie Treats would have. Rice Krispie Treats has in it 4 grams of fiber. See if you can predict how much potassium it has to practice along. What you would do is you'd go to fiber right here and you'd substitute into fiber 4. Now you mathematically solve the equation. Nice job in the chat. So we're going to go right here and just solve in, and we're predicting the amount of potassium it would have. To predict the potassium, we just go in here. There. And then we go here and go to 4 times 28. And then we say 37. And what is this? This is the predicted. Yeah, good job, Thomas. You solved the full equation. Great job, Thomas. Thomas, you got that 100 points for those Thinking Thursday questions. If you're stuck on something, please ask me to go back. I want to make sure everyone gets hundreds on these. So this is the predicted amount that Rice Krispie will have. But actually, Rice Krispies cereal, love it, but it's very bad on fiber. I mean, potassium, excuse me. This is predicted potassium. It's predicted to have this amount, but it only has this amount. So I want you to tell me, what is the residual? What is the residual? And it would be, yeah. So that'd be, you guys are probably getting in the chat. You got a negative 49 because it actually has 100 and it was predicted to have 149. Notice here how this is the prediction. This is the y hat. And this green one right here is the y. And the distance between them is the residual. So space pen is back, of course. That is the residual. So the residual is negative 49. It's negative 49 below its prediction. So it actually has less. And this leads into the question we just did, question 2. Because something has a negative residual, it is actually, here's its actual. It's actually lower than it predicted. So that's a review of question 2 right there. And it's using the equation and it's showing visually what's going on. Is this helping make more sense to everybody, how a residual and how we find it and how we use the regression equation? That's what these questions are trying to reinforce. How do you solve things with the regression equation? How do you find a residual? What does a residual actually mean? All this good stuff right here. Good stuff, good stuff, good practice. This is what we kind of do, during office hours. We practice, we get the work done, we understand the concepts a little bit more in depth. So good stuff, great work, everyone. The correlation, what is this R squared? So if you look at what it's asking, what fraction of the variability in potassium is accounted for by the variability in the other one? So potassium is what we are predicting. So I would like to say that when we square this, so just take, be careful. We square R to get R squared. Great question right there, Thomas. So we square R to get R squared, and you can square root R squared to get R. So be careful. A lot of people make that mistake. If you take R and square it, you get R squared. If you take R squared and square root it, you get R. That's a good note. This is a good kind of quick hand note. No, it's all right. No. I say this because this is a common error. I'll see people square root R or square R squared. So this note right here is a good help that if you square R, you get, I know it sounds so obvious, but I've seen this mistake. I've seen it. So when you square R, you get R squared. When you square root R squared, you get R. So yep, awesome stuff right there. And so what we need to do is we need to take this correlation and square it, which is the fraction of variability explained in the other one. They're just using slightly different wording. Instead of blank percent of the variation y is explained by the variation x. Andrew to the rescue here. We're going to trust Andrew. Trust in Andrew. And we put our trust wisely. Andrew gets 1 million points extra credit right there. Not usable in 474. So it's only 201. You got an extra 1,201 extra credit points. Got to make sure to be clear on that. Okay. I forget I have that button on the screen. Thank you, Andrew. Keep participating. I like it. So what do we see right here? These are what plots? These are what plots? Does everyone see it? These are residual plots. It's like almost like it's chapter 8. These are residual plots. These are residual plots. So what would they equate to? They are scatter plots. Residual plots are scatter plots. That is true. They're kind of a special case scatter plot. They're residual plot. I like that. Have we given you 100 yet? Jared, you're at 100. I like that. You said something I wasn't thinking of, so you get 100 points. They are scatter plots, but they're kind of special case. Now, these are theoretical plots that they could relate to. These are just theoretical. And the line's not theoretical. It could be a downward line. This one could be, we'll make this line not as sloped. Cool. So the way these would look, is this. These are just theoretical, like what they could have related to. Do you know where I'm going to do? Wait for it. Because that's that point up there. How do we turn something into a residual plot? How does something turn into a residual plot? Take the line and do what and set it to what? Take the line and make it what and set it equal to what? How do we make something a residual plot? How do we? It's good review, Andrew. It's good review. No. Andrew points or Andrew points. We'll call him Andrew points. Flatten set to 0. No, Andrew, we want you here, man. I love it. We had Julio show up yesterday. I think you know Julio, too. We had Julio show up. We've had Nathan show up. These are open things to you guys, and I'm more than happy to have, like, former students. The only people I remove people when it's like if you came in here and you were, like, yelling at me or something, I'd be like, Andrew, don't do that. But you're awesome, Andrew. So you would never do that. So people are always welcome. So I love it. And it's like, and I know you, Andrew, like, everyone's kind of seeing how this question works. I just want to say this. I do miss being in person on campus because there's something special about, like, people. You see people love it too. Kyle loves it. There's something special about being on campus and actually seeing the students in person and I still have an office, but being in the office and actually talking to students, and that, I love teaching online, but man, no, I'm just teaching this one, but I will be teaching first session summer 320 and 474. So once again, if it fits in your major and you want to take 320, sign up for 320, and then in two months, you'll have done some basic and a little bit more advanced statistics. Yeah, I like in person too. There's something special to it. So I like online. I make it as fun as we can. I hope that's my goal. But I like seeing everybody and saying hey, and it's like, oh man, I'll be coming into Knoxville every once in a while to, like, say hey to everybody. I'll be traveling in, saying hey. So what do we see right here? We see issues. That's an outlier. That's a curved relationship. That's another curved relationship. And I don't know that these are the plots, but I'm kind of using guesses. I know that they must look something like this. So we got all this right here. We're good to go. We know what the answer should be. Let's take a look. This curved pattern right here, bad. Was that it? Oh. This one has an outlier. Except for a single point. Yep. Next. This one right here has a curved pattern. Got it. There's many variations of this question. I'm going to do another version of it real quick. Good. Show me. Dang it, that's the one I wanted, but I don't want the answers in there. It's the same one. Really? That one has a few outliers. This one has a curve and an outlier, so that one's really bad. So if you look at the curve pattern, there's curved and outlier in this one, so that one's really bad. This one, is plot A good or bad? Is plot A good or bad? And I wanted to show this one. Is plot A good or bad? The answer is not on the screen right now. I know it does. They did that. I swear the person who coded this must have been like, I'm going to make a smiley face. They should have said it has a curve pattern and outliers. That one's really bad. So is plot A good or bad? Is this plot right here good or bad? It is very, 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 very... Remember what residual plots should show? They should show what? It's very good. It's a very good residual plot. Don't worry, I asked that. I wanted to show this for a reason. It's very good. I knew it'd get everybody. It shows nothing. You might be like, it goes downward a little bit. Well, it's very good because it shows basically nothing, and this is what we want to see in our residual plots. I think we still have some of the notes up from it. We want to see residual plots. Those are not residual plots. Those are actually regressions. Things can look very similar. We want to see residual plots that show basically nothing. Do we do it? Yeah. So there's a good regression with homoscedasticity that shows basically nothing. Here's a good regression right here that shows basically nothing. Here's a bad residual plot with a bow tie pattern. So you want to see this, and this is a good residual plot. And if you look at the question they did, extra credit. Someone got Neil, you're at 100. Someone extra credit. I got to honor the screen. If you look at this right here, it kind of looks like the plots we were just looking at. The only other one it has inside of this question is the fanned pattern, which is a heteroscedastic problem. So no matter which way it fans, but is this model getting stronger or weaker? is this model getting more accurate or less accurate as it goes on? Think about things are getting tighter inside of here. Is it getting more or less accurate? Is it getting more or less accurate? It's the hint down here. It's the answer. It's getting more accurate, which means the model has better predictive power. It's getting closer because those things right there, just to review, the line, if you look at the line, it's getting closer to the line. The line is right here. I'll draw the same pattern. So why not? I'll take their patterns and I'll redraw them again, just so you can see what's going on, because residual plots are very important. Oh, good. Okay. So we can draw theoretical models these could have come from right here. So theoretically speaking, we know that these lines would be at 0 right here. These lines are going to be at 0 because that's where the line goes through. Sure. And want to go through the dots. There we go. And that line's going to cause a bit of an issue. So when you draw these theoretically, and these are not actually what they are, I'm not saying they must be these relationships, but it's a theoretical idea of what they could be. So theoretically speaking, this one could have come from a line that went downward, could have, and the lines would the points would fan out at the start, and the points would get really close. Because when you take that and make it flat, it's going to look like that. And I'll try to make it more clear that the points are out there. Here, we'll add more points. There we go. Now it looks more like it. This one right here could have came from a line that went up or down. Who knows? But we do know that the points around it look like this. The points around it have this nice kind of, like, depending on the zoom, it can change the way it looks, but they're evenly spread out. So the points around it have a nice even spread. Where in this one, it could have came from a line that went up also. But this one's going to have an outlier towards the top of the model. It's going to have a point out here somewhere, this point, which is registered by this. So if you look at the similarities in the plots, you've got the change in strength for the first plot, the good residual pattern for the second, and there's an outlier in the third plot. Hopefully that makes more sense to everybody, but that's the big learning objective with this right here, like understanding how it relates. Yes, I'll send an announcement, say the Kahoot is starting, so watch your announcements. Probably a little bit after 1. Good question right there, Claire. Guess what? Not completed problem. This one right here is so much easier with the solver. Let's get the solver right here just so we can remember where the solver is at. Where's our solver at? The solver is under modules. I'm going to download it here while we're talking modules. Where are you at? We need some music. So we're going to go here to modules. With modules, we're going to go down. I'll show it on the screen here in a second. We're going to go down to chapter 7. We're going to download it. I'm going to open it. So this solver right here that you're seeing right now, the solver, enable editing in the solver. And here we are. Zoom in a little bit on the solver. Where is that solver? Brian, we need to know where it's at. You got it. The solver is here under modules. So click the modules tab and then scroll down. Under the modules tab, you will see. You won't need it on the test. It's like we do more conceptual stuff. It's sometimes you'll do something on an assignment that's like, you know how to like solve this as a resource, but then there's no good way to test you on it. So I'd agree it's a little bit of a disconnect, but it's just like there's no good way to test you on it. So you will not need this for the test, but you will for the assignments. So conceptually, I was covering some really good concepts a moment ago. So like knowing those conceptual things, I was saying how like a residual plot is connected to a scatter plot that we made our regression from, and then we can show like the relationship between the two. These are like big conceptual things. So like knowing that. And then the solver I created because the reason I created this is I didn't want you solving things by hand. I didn't want you to like sit down and work math problems and make a math error, because if you sit down in this class and you solve math equations for like an hour, then you're not learning the concepts. We should know right here that this is the intercept, this is the slope, this is the correlation. It literally says what they are. That's why I put them there. And we have the notation. So what do you see right here? We have the notation for what these are, and then we have the term for what these are, and then this lets us actually solve it. So you can kind of use this to bolster your knowledge, like, oh, correlation is R, and this is the standard deviation of the Y variable, standard deviation of the X variable, the slope coefficient, the intercept coefficient, the mean of the X variable, and the mean of the Y variable. So X bar. I don't think it would let me put the bar in over it. I think Andrew tried maybe to help me out, and I think there was a problem with it. Or maybe help me with the subscript. I just feel like I have a memory of Andrew being like, this is how you do it. And I couldn't get the bar over it. Okay. So let's take a look at our question right here. What's the question say? Might go a little smaller on size. Bigger, sure. We have standardized test scores with math and verbal. We are trying to predict math scores from somebody's verbal score. What do you notice here? What's going on with this person? What you doing up there? What you doing so far away from this line? You shouldn't be up there. You're a what? You have a huge residual. A person's got a residual close to 0. These people got negative residuals. This person's got a positive. They're a what? Thinking Thursdays. They're an outlier, Hannah. You got your 100 points. They're an outlier. You got it. We throw points during office hours too. They are a huge outlier. They'll come into play later on. They're a huge outlier. But we just kind of analyze it and look at what's going on with this data just to think, okay, I understand what's going on with that graphic behind my head. I know what's going on. So the association between math and verbal scores is strongly linear and positive. Students with higher verbal scores typically have higher math scores. So this right here, it's positive. Higher means higher. We're good. As long as I don't click the wrong thing, we're good. So that just wants you to identify that there's a positive, somewhat linear relationship between the two variables. Does anyone not fit the pattern? You bet. Let's go look at that person. This person right here has a verbal in about the 200s and a math about 800. So math 800, I see math of 800, and I see verbal of 250, and that relates to that person right there. So there we go. We got them. We found them. They're good to go. Let's see. Great job, everyone in the chat. Thank you so much. So first person says me gets 100 points. So for so many people following along, you say me, you get your 100 points for the day. Who is it? I'll say your name, or chat might show different. Tyler, you got your 100 points. You got it. Great job. So you guys are following along, working hard right here. This is my least favorite part of this question. Did they change it? They didn't change it. I'll tell you how to solve this question. It's pretty easy. I promise it shows it different to me. I'm so sorry, Alyssa. Alyssa, I'm so sorry. Here, Alyssa, you got the 100 points. Okay. I'll take your word for it. Okay, you ready for this one? This one is computing R squared because it says 35.4% of the variability in math score. So it's taking this value of R right here and it is squaring it and it's getting R squared. So this is R squared. This is how they are interpreting their R squared right here. That is an interpretation. Okay, good. You're on 50. 100 points for your honesty. You got them now. That is the interpretation of R squared. And remember, we're using math. We're using We're using verbal to explain math. Verbal's on the x-axis. We're using verbal to explain mathematics. And so now, we'll be that one in a second. You got it. And so now what you would say right here is, let's be careful. A student who scores one standard deviation above the mean in verbal is expected to score, this says below. Since this says below, it would indicate a negative relationship. You want to pick this one because it indicates a positive relationship. It says that if someone scores above in verbal, they're expected to score above in math. So the difference between, well, this is not R squared. This one is wrong because it has the wrong R squared. And then we want when people score above in verbal, they score above in math. Or like people who expected to score higher in verbal expect to score higher in math. People who score higher in verbal expect to score higher in math. Got it. Okay. Now the one people are stuck on. This is where you need the solver. Please be very, don't worry. People email me all the time. They're like, Brian, your solver is wrong. I'm like, double check your work. So we got here the average for the verbal. Verbal is our what variable. Verbal is the what variable. Verbal, I need people to tell me verbal is my what variable. Verbal is the what variable. X, you got it. So now when I see here the verbal has an average of this with standard deviation of this, I go to my solver, and I remember verbal is X. So verbal has a average of 498.1. Do you see how it's going in the X position? Verbal has a standard deviation of 182. So I'm putting the values in where they go. Independent. Neela, that's good. And now we've got math has a 4884 for the mean. There we go. There's 8, right? And then 162.6. I'm missing one thing right here. I'm missing one thing. What is Brian missing for this to calculate the values for me? What is Brian missing? There's one more thing I must enter in. This is where people get stuck all the time. You got it. Correlation. R, correlation. Uh-oh, my Pearson broke. Uh-oh. No, it's right up here. Wait. Where? It's right up here. The correlation is this. You have to scroll up to that one. Don't worry. I probably tricked me when I started doing it. But you have to scroll up to get the correlation. Correlation is 0.595. Do not use R. You have to use R squared, excuse me. You have to use correlation. Don't use R squared. So you enter that right there, and we've got our values. Here's the value of the intercept. Here's the value of the... Can I copy it? Let's see if it copies it. Here is the value of the intercept. Good. And here is the value of the slope. 3 decimals. Be very careful. Please tell me if you get it wrong because of the decimal rounding. So that should round to that. Check your answer. Please tell me I'm right. It's positive, right? It is positive. Yeah, line goes up. Yep, we got it. Did anyone get this question while we were doing it right here? Did the solver work for everyone? How are we doing? Remember, the solver is found under the modules tab. So this solver right here will solve it for you. You don't need to work the math by hand because you'll get some decimals wrong. I did it all the time. I literally create these things out of frustration because I'll work problems with students and then we'll be off by 1 decimal. And I'll be like, oh, and what's the point of sitting there working the math when you can just solve it like that? It's solved. We're good. So you have to get this part of the equation to actually get the next few questions. You have to get that to then go here and interpret. Well, we have for each additional what? It's for each additional what? Is it X or Y? It's for each additional X. We expect Y, and it's going to be increased because it's positive, and X is verbal. So for each additional verbal, we expect the model predicts an increase of B1. They're switching around the wording a little bit, but it's for each additional X, we expect the Y to increase by B1. So they moved it around a little bit, but it's basically identical to what we repeat in class. They'll change the wording a little bit on you between questions because they want to see if you can understand it in different ways. I can't promise what someone will say to you outside this class. Like, if you go into another discipline, they might say it a little bit differently. So that's why I'm glad they changed it up a little bit. Now, it doesn't hurt to have a kind of standard definition and way of interpreting stuff. That's why I use kind of a form way of saying it. That's why I can get everyone kind of on the same track. And hopefully we kind of understand what it means when we say it. We don't just kind of robotically do it. Robots are cool, though, still. So predict the math score for someone with a 521. So what would I do to this equation right here? I'm going to put what in for X? What would I put in for X? What would I plug in here? Any ideas? What would I plug in? 521. Now, you can do this by hand. You can solve it. But you know what? Guess what I did? Guess what we got here? We go right here. We type 521. And there's the answer. Cool. Answer solved. We're good. Solves it for us. We know the answer now. Answer is this. Whole number? Nearest whole number? That's a pretty big round on it. Sure. Likes it. Now, this is where it gets super tricky. Can I make it so it appears on the screen? Yeah. Every year, some students scores a perfect score. This one's the toughest problem on here. And it's trickier than we think. Here's where we practice for the test with problems like this. You ready? This is what we need to do. We need to take this problem and think through it and see what we have. So every year, someone scores a perfect 1600. What does that mean we know about them if they score a perfect 1600? That means that they're what? What'd they get on their math? There's 2 sections to it, equally weighted. What'd they get on their math? What did they get on their math? Any ideas? They'd definitely be an outlier. I'll take that. They got an 800 on their math. You are right. Nice job. So on their math, they achieved an 800. What'd they get on their verbal? You know it. They got an 800. They're awesome. We're all jealous of them. But what does this want? It wants a residual. And a residual equals their actual minus predicted. And let's put a note right here. The math is the Y, and this is the X. So we have here, and I'm also going to take a rounded version of my problem so I can abbreviate it real quick. Losing my mind. What is it? 225.5. Okay, got it. 225.5. There we go. Okay. So when we look at this right here, we have and trying to improve my handwriting. Trying. Good. My fives just don't look like fives. You only improve things if you consciously try to. And this is my good handwriting. Okay. So what we're going to do is we already know some information. We want to find the residual. What do we need? Someone give me the formula for the residual because I've lost my mind. I don't know the formula for the residual. What is the formula for the residual? What is the formula for the residual? A residual equals what? I'm going to write it two ways just to show us the two ways we can write it. You got it. Nice job, Jared, right there. Amazing work. I'll show you here in 2 seconds. It's under modules and under chapter 7 under modules, Camden. I'll blink to that really quick. Under modules, chapter 7 right here. So check it out right there. Modules, chapter 7 right there under the modules on Canvas. And people are giving some great advice in the chat right here. There's the actual minus the predicted, and residual equals actual minus predicted. You are right. What value do we currently have? Look within the highlighted stuff and tell me what value we currently have. What value do we currently have? Nice job, Camden, right there. What value do we currently have? We currently have the actual. You're right. We currently know someone's actual math score. What value do we need to find to get the residual? Because we want to solve for this. What value do we need to find? We need to find the... We need to find the... predicted. And that's it right there. Nice job right there, Needy. 100 points, Needy. And also, Thomas right there, you're at your 100. Great job. Amazing work today. So we need to find this. And how will we do that? Space Pen to the rescue. Space Pen right here says put in and solve. Solve to make the prediction. So we got Space Pen coming to the rescue right here. So what we're going to do is we're going to take and drop this in here and solve for the predicted. So we put in their value of their... We put in the value of their x, and then we solve for their predicted math. Now, we can do this really easily right here with the solver because we go right here and we just put in 800, and then there's their predicted right there. So 649.107 is what we predict. Yeah, and Jared, don't worry, I rounded it. I rounded mine. That's why our numbers are a bit different. Great job, Jared, right there. Following along, doing the work. What was it? Where was it? 649.107. So because of the way I rounded this, someone's listening to this video on mute, and they're like, what happened? Because of the rounding I did on those numbers, because I just wrote them easier to make life easier on me, because it's easier to look at whole numbers. So when we do this right here, so everything's been solved. We use the solver to solve it. Much easier than doing it by hand, and it'll do it exactly. It'll not make any errors as long as we punch the numbers in correctly, in the right way. So now we want to go to the actual minus the predicted. So what would they actually make? 800. What were they predicted to make? 649.107. That makes the residual right here 150.893. I believe so. 150.893. Let's see if Brian did his math correctly in his head. 150.893. Is that correct? 3 decimals, 3. Go. Oh, I didn't look at the decimals right when I was hitting enter. Oh, I was afraid. I was like, is it 3 or 2? So we got it. Does that make sense? Who got that problem right now? Did anyone get that problem correct? Because that's a tough one. That's where people get stuck on the homework on this. That's the one where people are like, can't do it. Got it. Nice job, Nealon. Remember, rewind the tape if you need. Follow the steps right there. And then understand what's going on. Like, understand how it's working. Great stuff. And then don't solve it by hand. What's the point of solving things by hand when you can just punch it in? Just be like, okay, what would we predict if someone made a 200 on their verbal? There we go. There's the prediction. Cool. Solves it for us. That's what we like, computers and math. Cool. Okay, we've got the age of a car and its price advertised. Be very careful. What do you notice? This is where people make the mistake on this. Slow down. You're about to get it wrong. And someone's like, what do you notice about the price of a car as it gets older? And just think logically. What do you notice about the price of a car as it gets older? Gets what? Decreases. So if it's going down, the correlation must be what? This is a huge trick. I'm glad we're mentioning it now. It's one of those things you could deduce, but I'll tell you. Is when you square root r squared, you wouldn't know if r squared is negative or positive. That's not square rooting it. You wouldn't know if r squared is negative or positive, or r is negative or positive till you look at it. And by looking at it, we can see that price goes down as age goes up. So when you get the correlation here, this one sometimes rounds weird. Please work correct. I knew it. I knew it was going to... Oh my gosh. I forgot the negative. I literally did that was not on purpose. I was telling you guys the trick to it, and then I forgot. It just happens. That was a legitimate mistake right there that you just make when you're doing the assignment. You're like, oh my gosh. I know it's negative. The really great thing about doing stats is that I wonder. Oof, I don't think I can fix this. I made a video. I can do it easily in Jump. The great thing is when you do data like this, you can quickly see the relationship between these by going to fit y by x. We want to predict the price of a car from the age of a car, and then we go here, we fit the model, and you can fit the line. I think there is a way to get correlation in this platform. Maybe not. Summary statistics does, right? Is correlation on? Yeah, there's the correlation. So there's the correlation right here. So you can see the correlation. You can see the r squared. I just don't usually do correlation in this platform, but you can see it's negative correlation, but r squared can't be negative. And it's obvious it's negative when you see it goes a downward trajectory, and also the coefficient of the slope, which can be observed here. There's the coefficient of the slope. Make sure not to forget the negative. And the coefficient of the slope can be seen down here at the very bottom. That's the coefficient of slope. And it is very significant because we have kind of a very sloped line. But more importantly, the p-value for the model is negative. And I can tell you in my head, I'm going to solve what is 11.2 squared. 11.2, I'm going to do it down to the 11.2 squared. That's a tough one. You ready? I'm going to do it down to the fourth decimal. 11.2 squared is, it's going to be like 125.5026. 11.2 squared is 125.5026. So 11.2, let's square that. Oh, they're not showing enough decimals. Dang it. The t squared is the f right there. They're not showing enough decimals. That was Brian's fun for the moment. If it'd shown more decimals, I would have gotten it more correct. Show me the decimals. Or not. Okay. Brian has fun. Explain the meaning of r squared in context. It's the amount of... Someone try a sentence for me. Help me out here. Give me a sentence using like this value right here, because we're trying to explain price of a car. Give me a sentence trying to explain using this 89.3%. Don't look at theirs. Don't look at theirs. Ah. What do you guys think? I'd say something like 89.3. Phil might be back in time. 89.3% of the variation in price is explained by the variation in age. 89.3% of the variation in the price of a car is explained by the variation in age. So age is accounting for. They've reversed it here. Age is the one explaining. Nice job, Neelan. So if you notice, saying something accounts for the variation is to say it explains it. So age is doing the explaining the way they've written it. They're saying that age accounts for the variation, so age explains the variation. So you could say age explains 89.3% of the variation, or I would say the variation in age. There's ways to rephrase it, and then everyone argues in statistics over what's the right way. But these are acceptable ways. I just like to say blank percent of the variation Y is explained by the variation in X. So I'd say 89.3% of the variation in price is explained by the variation in the age of a car. And we got it right. And one more. Oop. Why doesn't this... Oh, they changed this one recently because I didn't like the way it worked, and then they fixed it a little bit. Why... It's going to block. Why does this model... We got to do it the hard way. Why does this model... Why doesn't this model explain 100% of the variation in the price of used Model A? It's not that there's not enough data. I mean, in truth, All models are wrong, but it's that some points are off. Other factors such as options, conditions, mileage contribute to the asking price. That sounds good. It is impossible for real world data to be perfect. No, you can have perfect data. I mean, it might not work for new data though. Holdout models. Andrew, you'll be hearing about that. Different dealers ask different prices for cars of the same age. That is actually a right answer, and this is the question I hate, because B is the right answer, and D is theoretically correct, because if you were to have two cars that had the same age but a different asking price, you would have a model that could not have an R squared of 1. Just visually, and I need to tell my peers, and I keep meaning to tell them that is also a right answer, because if you had two cars, like car A and car B have the same age, but they have different asking price, they both can't have a residual of 0. And so to explain 100% of the variation, all the points must be on the line. But car A and car B here, which I'm just saying like two cars have the same age. So with two cars at the same age with different asking prices, they can't be on the model. So you can't have 100% of the variation explained, which that is like the theoretical answer. I really need to contact my peers and say, you've got two right answers to this question, because that's the proof. If they have different ages, then you got to, one of them has a residual. And if one of them has a residual, R squared can't be 1, because R squared being 1 means everything's explained. So, but then the other one is pretty much true, that there's other factors that explain the variation. So age is not the only thing that explains variation in price of a car. It's like condition, all that stuff we talked about in class today. So I kind of allude to those because I've done a lot of these. Who got 100 on their homework? Who got 100 on their homework? Who got the 100 on their homework? I don't want to see it in the chat. You guys know I love it when you get those hundreds. Who got the hundreds on their homeworks? Who did it? You did. Nice job, Needy, right there. 100 on your homework. That's what we like seeing. Let's do it. Let's go back here. Let's do some more. Great job. Oh my gosh, so many hundreds. Awesome work. Let's go in here. Let's do some of the quiz questions. I'm going to try to do some of the hardest quiz questions. And you know what I'm going to do? I am going to put Chapter 8 due tomorrow night. Now, if you're obviously taking the test, you're hearing this now. Chapter 8 is due tomorrow night, along with your writing of the quick note-taking quiz. Very quick on those. If you're in class, you should have it. You just need to take a picture. Boom, you got it. 300s. I'm going to do Chapter 8 tomorrow night, because I'm going to cover some of the big ones in Chapter 7 here. Chapter 8 is just an extension of Chapter 7. It's very, very consistent. Then we're going to move the randomness to the weekend. So expect that I can do it right now. Here, we'll put on a little Mega Man right here. I think I can get it there on screen. Give me a second. Ask some questions in chat while I change assignments, due dates. Look over here when the music stopped playing. Change dates of assignments. Because if I say I'll do it and then I get doing other stuff today, I'll kind of forget. Like, I'll do it, and then in one day's a lot in mini-term. Okay. So I do not suggest waiting till tomorrow night to do Chapter 8. I suggest go Chapter 10. That'll be due on Sunday. I'm rearranging as we speak. Rearranging the assignment order. My brain's breaking. I'm like, if I move them forward, I don't want to move them back. 17. Where do we have to get to? This is taking more a moment than I wanted it to. I need to fix it now before we do it. What day is that? That's Wednesday. Okay, so that should be Thursday now. So much work. So much. And thank you guys for constantly doing sampling distribution of the mean. That is on test 2. And confidence intervals for proportion. Like, I'm like, oh, is that on test 3? Wait, why is that on this date? Sorry, one more song, and I think I'll have it. Just fixing this. Should have known it'd take me longer than a moment. That should be on the 20th. I try to space things out as evenly as possible. And these should be... Before I hit save on this, I don't want to hit save and then have it wrong, and then people be like, but it was this date. And I'll be like, I changed it. And they'll be like, you, Brian, why'd you do that to us? Please tell me if you ever see error in these types of things. Okay, let me look. 21st, 20th. There, that needs to be changed. 19th. 18th. Good. Wait. 19th, 18th. We've done it. I think we've done it. Today? Today's really? Oh my gosh. 16th. And then that's got it. Okay. Okay, I need a vote in the chat. Would you like... I'm just thinking. Yeah, I think we got to do that on Monday. I think you'd vote it anyways. I was going to ask, should we have one assignment due this weekend or two assignments? We're going to have one because on Monday I can cover it more in depth. It's tough. Main term's fast. So this needs to be due on... Wait a minute. Sorry. One more song. 18th. It's due on Monday. So this is also due on Monday. I think I've done it. This is due on Sunday. Cool, that's not an easy one. That's good. It's not an easy one. Okay, that means we have nothing due on Friday night. Let me update all settings. Hopefully I did it the right way. Okay, sorry about that long interlude right there. Let's see what everyone's saying. I've updated all the stuff right there. Chapter 7 is still due tonight. Number of wildfires, you got it, Jared. Let's do that one next right here. Check out the new updated dates. I just went through and updated. I'm always trying to be as kind of responsive as I can be. Sorry, I'll pull up the chat here in 2 seconds. But I like to kind of react to what people are thinking or doing and like how the pace of class is going. So understand I will always be kind of fluid in what we do. We're going to get through everything. That is correct, Thomas. You got it. Thomas is right. I'm back. Jack, which one, Jack, was that? Which one is C on 5? You might have to put the question in the chat, Jack, so I can see it if it's the homework. Also, you can, you guys know you can rewind time live, right? So maybe check that out. Like, check out Rewinding Time Live. And then I'm going to start answering questions right here. So you can rewind time live and see when I was doing it, and that's really a good thing right there. A lot of people have used that. And you can even talk through time. So, yep. And so I think that one, try rewinding time, Jack. And if you're still stuck, so rewind time and just go to the bottom bar and try rewinding time. And if you're still stuck, tell me and we'll solve it. So give that a shot. Cool. Okay. And let's see. There was a question here about the wildfires. So let's do the wildfires one. If you notice, we got a lot of similar questions you might have. You figured it out. Nice job. Great job, Jack. Here's the one right here. We did that one. So awesome. See you, Andrew. Hope your car is doing well, man. You guys advertise price for cars. Here we'll go here. Wildfires. We're going to do wildfires, then say the question you want next. So we're going to do the wildfires. And then, is it really the last question? I got scared. I was like, where is it? And then we got there. Jose's got the next one. Cool. So, do you think the linear model is appropriate? When I need you guys' help again. When I see a linear model, what am I going to say? When I see a linear model, what do I do to check to see if it's appropriate? How do you know if a linear model is appropriate? Q straight enough, no outliers. Plot doesn't thicken. Q straight enough, no outliers. Plot doesn't thicken. Let's see. Q straight enough. No outliers. Thank you, Jared. I'd say there's no outliers. There's nothing extreme. And the plot, I know it's kind of iffy on this one. It's good enough. I'm going to say it's good enough. Let's see if my Pearson says. Yes, the relationship is straight enough. It passes through pretty much all the points. Good. Interpret the slope in context. So the slope right here, they're kind of giving it to you like they have in the regression output. If you look at the regression output, down here at the bottom of the linear fit, you kind of get this sort of table. Sure. So they're showing you the intercept right here has a value of this. That's the coefficient or the estimate of the intercept. Nice job in the chart right there. So we've got the intercept and the coefficient, this estimate, and then you've got the year right here. Oh, is this the one? Please tell me I didn't leave a standard error question in. We'll see if I did. So when you interpret this intercept, you'd be saying when it is 1982. Now, why am I saying when it is 1982? Because this is the year since 1982 and 0. So in the year 1982, we would expect about 3 acres of land to be burned, or 2.96. The amount of land damaged by this is slope. So it's for each 1 year increase since 1982. We would expect the damage to land, the acres to land to increase by 0.13. So the damaged land will expect it to increase by that amount. Please remember, you should try to interpret these on your own, as in, like, for each additional year since 1982, we would expect the damaged land in acres to increase by 0.13174. Oh, really? Where does it say it's been declining? Huh? Oh, did I click the wrong button? No, it's increasing. I don't see it. Maybe yours does. Maybe yours does, Jared. In the top? Oh, wait. The number of wildfires in the country has been declining. Ooh, that's interesting. A scatter plot of the amount of land. You know what it might be? They might be dealing with the time series nature of this problem. It might be the amount of land they've lost. No. Wow, that's Jared. Email me about that. Jared, I've never noticed that about this question because I oftentimes focus on the statistics. Jared broke all rules and got 150 points. Jared, you're at 150. Please email me. I need to email my Pearson about these things because this seems like an error in their question, and I don't like that. So, Jared, amazing thing right there. I really appreciate it when you guys see things like that and I don't notice them because I'm like, what? The line goes up, the coefficient's positive. I'm like, and then I don't read that. Sorry. To me, it doesn't matter what the question says. I really mean that. Like, if you understand what I'm saying, like, I just see the numbers, but you saw something I didn't see, and it makes no sense. So I'm probably going to contact them, and it says the numbers in the country has been increasing. So I don't know what they did to their thing, but they made a problem that doesn't make sense. You got it, Jared. Nice job. Can we interpret the intercept? Yeah, it's just in 1982. So that's what it would mean. And I might actually remove this question. Yeah. And this question, this part's the part I don't like about it. Now I really don't like this question. It could be, but that's so confusing. Zulon, you might be right. Like, that's so confusing to say, like, the number of wildfires has been decreasing, but maybe the wildfires have just been bigger. Yeah, exactly. It'd be like one of those weird contradictory things, but yet true. Yeah. No, you guys are right. It's just like, why would they say that? They should say, like, the severity of wildfires in the country has been increasing. So, like, or it could say, although the number of wildfires have been in decline, the severity of these wildfires and the land lost to them has been increasing. So great job right there. Zulon, you started that conversation. You're at 150. I'm breaking all the rules. So I really appreciate those. Like, these are the talks you have when you look at data. Jared, you are saying it. You read my mind. Stats don't lie, statistician does. I mean, maybe it's true that the number of wildfires have been decreasing, but then if we're losing more land, that's almost like synonymous with severity. But this data needs more. Ooh, data needs what? This is a hint for the test. Data needs what? All data needs what? All data needs what? You should know this. It's in the slides early on. All data needs CONTEXT. Standardization's good too. Which actually would remove this. It would turn it all to standardized metrics. Context. All data needs context. We need to understand what's going on with it. All data needs context. Very important saying right there for the test. What does the standard error? Didn't tell you guys about that. What does the standard error say about the size of the residuals? What does it say about the effectiveness of the model? The residuals have a standard error of this. That's identical. Compared to the observed values, most of which are between this and this. The amount of error in the is quite small. So I think I remember why I kept this question. I want you to tell me if this looks like a big or small error. Does this look like a big or small error? Like when you look at the residuals, do the residuals... This question can be summed up. I know I didn't tell you what SE is. It's standard error. But it's a big error. So all you have to do is look at the error and you have to say it's quite large and you're good. Should be good, I hope. But you're just looking at standard error is a... Think about what... Wait, break down what standard error is. Standard error is a standardized something. You got some Thinking Thursday points right here for 150. These crazy points. So I gotta not make it crazy. I gotta keep things standardized this semester. Great. Thinking Thursday is insane. A standard error is a what? Boom, Jared. Jared. You got it. Jared. Great job right there. It's a standardized residual. That's what a standard error is. So, well, at least in this context, because it's standard error of the residuals. So it's the standard error of the residuals. So it's a standardized version of the metric for the residuals. So you guys got it. So that's the standard error of the residuals, which I just want to show real quick, and then we'll finish this question. You can find out the standard error of the residuals by going here, and we get the standard error of the residuals. And I'll show it again. So this is the residual standard error right there. So that's the standard error of the residuals. It's a standardized metric by which we can look at the residuals of the model. So there's standard error of the residuals. You see residual, and then you have to know what the standard error means. It's a standardized version of the residuals. But there's also standard error for your model. You've got your standard error in your intercept and your standard error in your weight. So standard errors are standardized metrics, but they don't always go with residuals. This is a residual standard error, and this is the standard error for the intercept, and this is the standard error for the slope coefficient of the model. And then we can do a t-statistic, which is just those divided, and then we get p-values. Yep, fun. I'll tell you more about this output at another time. But so just kind of converging these topics is very important, especially if you do decide to take something like 320. What does R squared mean in context? It's the percent of variation in land burned by the year since 1982. So it's 20.4% of the damage can be accounted for. Well, it's not other factors. Don't tell me other factors in there. 20.4% of the variation in acres burned can be damaged by wildfires is accounted for by the years in the model. Please tell me I got it. Oh my gosh, what did we get wrong? It's not that. Yeah, of course it's not that. What did we do? It's obviously big residuals, right? Yes, obviously big residuals. Can we interpret the intercept? Wait. Yeah, we can. We interpret the intercept. Cool. So we got interpret the slope. The amount of land damage by wildfires increases about by this much. Yeah, it's been increased. Did we get the first one wrong? Yeah, it's increasing. Oh, really? Really? I said it was appropriate. Give me my points back, my Pearson. The answer is yes. We can do regression on this. Is the other yes. When I saw it, I knew it. Yeah. So be careful. If I'm working through these, I'll double check the answers at the end. Obviously, we can do regression. It passes QQ straight enough, no outliers, plot doesn't thicken, which means regression is appropriate. So if you don't have QQ, you can't do a regression. So it's very spread out. Yeah, that's what it wants for this one. It wants you to say it's very spread out. I mean, it just means it's weak regression. We can still do it. It means the regression is not as strong. So is it when it asks, is it appropriate? I only care about the yes, really. Yes, we pass QQ straight enough, no outliers, plot doesn't thicken. So it is appropriate to do it because it is a good regression. So they tricked me. My Pearson tricking me with these questions. What other one did people have? What other question was there? We'll do like 3-4 more and then we'll start doing Kahoot here. Because a lot of these are very similar. This one right here, you need to use the regression solver for. I'll show a different version. Please if you have a question, put it in the chat. Adds in a local paper, you got it. And I think Jose had one too, so I'll try to find Jose's here in a second. Jose, re-put put in the chat. Ads in a local paper. We'll do the ads in local paper. Ads in the local paper. Here we go. Okay. So we get some data. If you notice, this data right here has a downward. This one's actually really tricky too. This one was a trick that catches people. Good deal. We got a lot in the chat. Research collected. You got it. We'll start doing these here next. So we've got here the age right here, and there's a few ways to figure this one out. One, using jump makes this one a lot easier. So if you've seen it a few times, I copy the data to the clipboard. I'm going to go a little slower here so you can pause the tape and watch it. You won't need the regression solver for the exam. Nope. You just need to know. And we're going to go to tab. Sure. They all work, I think. Select the data just to watch again. You go here, copy to clipboard, copy your data, go into jump. Thank you so much. Love you guys answering questions in the chat. And you go open to a new data sheet, file, new data table. I know the quick commands. You paste with column names. I'll show it. Edit, paste with column names for this one because it has column names. You got it. We'll keep doing them. And then you go to analyze fit y by x. Now, please make sure they're both quantitative. If they're not quantitative, you've done something incorrectly. Rewind the tape. You probably pasted without column names. Do a new data table. Restart it. We're going to say here age. We're going to say here age explains the price of a car because age is in the X. Age explains why the price of a car is a certain value. Now, these, when you fit the line, this is where people make a mistake on this one. I've seen this one and people get it wrong before. There's 3 points here, 1 point there, and 1. So 3, 1, 1. Okay, and all these are below the line. 3, 1, 1, then above. Okay, let's check out. Okay. So obviously it doesn't go up. That looks wrong. There's 3, 2, 1. Because there should not be 2 cars at age 11. So ooh, there are. Are those 2 cars just so close? My Pearson, can you not draw your graphics? Those 2 points are so close, aren't they? That's the trick that catches people. My Pearson, you're being so mean today. Oh my gosh. How do they make their visual? It's 2 points. 2 points right there at age 11. We can confirm that by looking at the data right here and seeing there's 2 observations. So wait a minute. It's this one, isn't it? Because there's the 2 points. You have to look really closely to see that crosshair right there is actually 2 points. That's the trick. I know this one has gotten wrong answers before. Let's zoom in on that area only. Let's enhance. It's Jason Bourne. You can see it now. There's Jason Bourne right there. He's hiding right behind that cross right there. That's a point, that's a point, that's a point, that's a point, that's an extra point. And it's very hard to see unless you like super enhance inside of jump, which we did, that there is the second point. So you can see like this is this point here and this is this point here. I know this one has caught many students off guard. So a lot of people get this one wrong, but you're looking at, you're not, let me make it even clearer what you're looking at. Is it Alt? No. Crop the image. Enhance. My God. There you go. What you're looking at right here is the same thing you're looking at right here. So the graphic here and here are the same graphic. Yep. Okay, cool. They can't trick. They tricked us once. They're not doing it again. Not tricking me. That's the right answer. It goes down. This one's the wrong answer. You can kind of deduce it now because that one has the 2 points too far apart. They're so mean. Why they do that? So describe the association between age price. It's negative. It's oh really? It's. I'll use jump to tell me if it's linear or not, and I'll tell you statistically if it's linear. The answer is it's barely linear. Oh, that's fun when it barely passes the goodness of fit. So I did allude in class that there's ways to know mathematically if these things are linear, The goodness of fit test right here will tell, or the lack of fit, excuse me, not lack. It tells you if the linear model is a good fit. We do not reject. This is a p-value testing to see if the linear fit is good. So I'm going to go with jump. I'll tell you the right answer here in a moment. But I'm going to go with jump and say it's linear because jump said it is. And it is very strong. So there's a little bit of a bend, but I'm going to go with it being mainly linear. I think they're not trying to trick me. Do you think the linear model is appropriate? Yeah. Yes, because it's not because randomized. We're not randomizing stuff here. It's because it's QQ straight enough, no outliers. It's straight enough and has no outliers. It seems like they're trying to show us a good regression. Computer says R squared is this. Compute the correlation. They're trying to trick us. We're too smart for them. When we square root R, what should we do? When we square root R, what should we do? When we let's look at the plot. And when we square root R, what should we do? We can outsmart them. We can use jump. I'm going to go over here to jump and say, find me their summary statistics. And oh, look at that. There's the correlation right there. We tricked them. I've seen weird rounding on the. Please tell me if a weird rounding thing happens to you. It happens to me all the time too. So we notice that this is negative. So when you square root this, one thing I will say is take their number, and that's R squared. Cool. So we're going to have to square root it. Take their number and square root it and see what you get. Okay, it does turn out to be what I got. So we're going to take this to 3 decimals. You have to round it. You have to put in the negative, not 2 zeros. You have to put in the negatives, and then you have to round it. On this one, you would square root it. Does that make sense, Thomas? You take R, and we have our note right here that R squared, to get R from R squared, we square root R. Now you need to, we'll add another note right here with space pen. Tells us all the awesome stuff. We don't know if it's negative or positive till we look at it. So once you square root R squared, you need to look at it and see if the line goes up or down. I'm able to identify that it is negative because it goes down. So because this is a negative relationship, I'm able to identify that. Explain the meaning. It's 89.4% of the variation in the price of a car is explained by the age. So age accounts for 89.4% of the variation. Nice job. Great job, Thomas. Oh my gosh, this question is so long. Age accounts for that percent of the variation. Cool. Because age is doing the explaining. Age is on the X variable. It accounts for the variation. Why doesn't this is the same question from before? The age, no. Other factors. See, this is the one they changed. I knew they changed one of these. Because remember that answer I was talking about before? This is Brian rant real quick. The one before that said 2 cars could have a different price. They changed this one. So I thought they had changed it. But they didn't change the other one. Other factors. And then D is just ridiculous. So that someone must have pointed this out to them because D is the different answer and D is ridiculous. 10, you could have 100 points in R squared of 1. It's unlikely, but yeah. My Pearson scares me. Okay. I saw some other ones in the chat. I think Jose's question was next. Thank you, Jose. We got this right here. Da-da-da-da-da-da. What we got? Research. I should not yawn into the mic. I should just mute myself. There, I can yawn when I want. Researchers collected data from the mortality rate. Happy questions. Yep. Okay. So researchers collected data on the annual mortality rate of water hardness in terms of calcium concentrate. So we got calcium concentrate explaining the mortality. So does the calcium in a water explain the mortality? Water. So the display to the right shows a very strong negative. Can we do that? You got it, Thomas. We'll do hamburgers next because hamburgers would be amazing. So I should pull out. I've got hamburgers in the freezer. Friday night hamburgers because I've got cheese and I've got bread. Friday night hamburgers. Oh, and I could like have Saturday morning hamburgers. Okay, with eggs. Oh yes, I'm doing it. Okay, I'm really hungry. The display to the right shows a relationship that's been between the two. You got it. Is it fairly strong? It's fairly strong. Linear towns with harder water tend to have lower. Okay, so more calcium is harder water, right? I have to make sure. Yeah, so harder water means there's more calcium. Does that make sense? So as long as I know that harder water means more calcium. So towns with harder water tend to have lower mortality because when the water is harder, the mortality goes down. Not causes, but tends to. Here it is. Oh, cool. Hey, we got this. What goes here? What goes here? What goes here? B0, B1. I like this question a good bit because it shows you the output like you see it in jump. This is a great way of knowing what jump output looks like, because jump output, to just show you only the jump output, the jump output looks like, really? Oh, because I shouldn't close that. The jump output is at the very bottom of the screen right here with the intercept and then the estimate and then the standard error and then the t and then the p-value. Intercept, standard error, t, and then p-value. You don't need to really know these two things right in here. These two things will not be in this class. They are used later on, but this is the way you see it in output a lot of times, so it's good that you kind of see this. Standard error is your uncertainty in the estimate of the intercept. The t ratio is the ratio between the two of them. You can easily get a t ratio by doing the following. Take 1629.966 divided by the standard error, and it's just a ratio of the two, and there's the t statistic, and then you find the p-value from the t statistic. Done. Okay, now that we talked about those, never we'll need to talk about them again. We just take the coefficient for the slope, the intercept, and this goes right here. There's the coefficient for the intercept, and this is the coefficient for the slope. And the coefficient for the slope is negative. Don't forget the negative, and we've done that one. As long as we typed them in the right way, this is literally right here. This value right here, which I can't highlight, but that value is B0 and that value is B1. I do like in a lot of output, it calls them the estimate, which would make it the estimate of the intercept, but it's the estimate of the coefficient for the intercept. So some output calls it estimate, some output calls it coefficient, and coefficient just means the number. This is the number of the slope. And then standard is uncertainty and t ratio is ratio. Yeah, anyways, got it. Okay. So intercept in the context, well, that would be a town that has a water hardness of 0. So, slope. The slope is for each additional degree of water hardness. So for each additional calcium, the model predicts a decrease in mortality. There we go. Because it goes down, and for each additional calcium, the model is going to see a decrease of this right here. I'll explain the meaning of the y-intercept of the line. It's a town that has 0 calcium. So it's like the softest water town where everyone's dying. That's horrible. But this is the softest possible water. It actually goes off the scale. If you notice, this is not the intercept. It's just where the graphic hits. The intercept is further over at 16,1629. And so this would be, the model predicts, like we would expect, that a town with this much would have there, because they're using the right number here. They switch, that's the slope, that's the intercept. Notice how you have to identify which of these is the slope and which of these is the intercept. So they're switching around the numbers on you on this one. They're saying, wait a minute, which number goes into the, when a town has 0 parts per million calcium, the softest water. The largest residual was this. What does that mean? Well, that would be a town that was up here. Probably one of these has a very large residual. It's above the line. That means more people died than we would have expected. Think we're predicting mortality. That means they're above the expected, just so you can see. Let's zoom in right here. We're going to do a zoom in on this. You know what I do? I like the way the graphic looked originally. We go ahead and we take and we draw our model in. Let's go over here to a Word document. Let's draw our model, or not. And then we zoom in and we exit out the navigation. So when we draw our model right here, we go ahead and we draw our model. Green pen, where are you at? And we can see a point up here that has positive residual, means more people were dying, because that's the actual and predicted is on the line. So predicted right here is the y hat. Let me get it in black so we can see it. So more people in the town were died than were predicted to die. More people in the town died than were predicted to die. So do we have anything that sounds like that? The town had this many more deaths per 1,000 than the model predicts. They had this many more. So they were over their prediction because they have a positive residual, and that's the residual. The hardness of a certain town's municipal's waters is 87. Yeah, this one, good job. Uses equation to predict the mortality in this town. Okay, let's go back to here. Let's use the equation. And let's do 87 times this. Be very careful because you have to go negative. Now, I want to point something out. We're going to slow down here for a second, because when you solve this, what I want you to do is I want you to go here to 87. 87 would be in here somewhere. I want you to trace up and then over. Does it sound reasonable if 87 is here and I trace up and over that this would be about where 1200 something is at? Like here's 87. Yeah, we'll do. And I think the SAT one, check out the video earlier, or which one? There's 2 SAT ones. Tell me the start of it, and I'll take a look at that, Jack, and we'll probably circle back to it. I think Eric has one too. We'll do. Does it make sense that when I trace up here to 12, like this is where 87 would be at because it says we're going to predict for 87. There it is right there. We're going to use 87 in the model to make predictions. So you go here to what 87 would be about at on the number line. You trace up, and you trace over, and that is probably about right there is probably about where that would be at. Oh, yeah, good one, Jack. I think that's a new one. Yes, you got that, Jack. We'll do one next. Great question right there because I think there's multiple SAT ones. Did I change an answer? I have clicked before and changed an answer. Good. Like right there. I didn't want it highlighted. I did that one time, and I was like, I didn't answer that. How dare you, my person? Explain R squared. It's blank percent of the variation Y is explained by the variation X. So R squared is 95.8. So 95.8% of the variation in the mortality of these towns is explained by the hardness of their water. So 95.8% of the variability in the mortality can be explained by the variability in calcium. Great. That's a great answer, my Pearson. You get 100. Did I get 100? Of course I got 100. I say of course, and I don't. And we got hamburgers too. Yes. Okay, so let's see. We got Erica's, then we got Thomas's, and we got Jack's. I was thinking, I remember the hamburger one from earlier. So let's go ahead and do this right here. Get hair out of the eye. Erica says the accompanying. I think the first year ones we've done. We did that one. Oh, hamburgers. Oh, man. The accompanying Sarah plot. Cool. This is what happens when you have long hair. Or longish. So the accompanying scatter plot, yada, yada, yada. Teenagers using drugs. Fun stuff from 11 countries. That's how many points we'll have. Summary statistics calculated showed the mean of marijuana usage. So now we know that we're predicting, this is your Y variable. You got it, Jared. And this is Y and this is X. So are we going to have to do the model? We are. Okay, so this is a regression solver problem. This is a regression solver problem with my regression solver app. If anyone's watching the video and hasn't seen it, it is here found under modules. It is this link. This one makes your life a lot easier on this problem. As soon as I read this problem, I'm going to identify that marijuana is the X variable. Marijuana is the X variable. So these are going to be percentages in here now. I think everything will work properly. How does it want me to enter them? It's predicting a percent. It wants me to enter it in as whole numbers. We might have, Camden. Double check. We did one similar to that. I think we have, Camden. Good question. So please note that this is the X variable. How do I know that marijuana is the X variable? That's how I know right there. Marijuana is on the X-axis. It's definitely the X variable. So I need these two numbers right here, and I have the mean, and I have the standard deviation. Going over the... Oh, no worries, Camden. Good question. Ask at any time. So we need to look at this right here. It's 24.3 and 15.3. If I enter something in wrong, I get the whole thing wrong, so be careful. And then the other variable is 12 and 10.9. 12. And 10.9. And now I need the correlation. So now I need the correlation right here. The correlation is, did you tell me the correlation? Where's correlation? There's R squared. Do you really have to you have to really square root of R to get? Sure, okay. Let's go ahead and take and find the... I entered them in backwards? Oh no! Wait, let's check. Did I really? I bet I did. Morgan, I bet you're gonna get 150 points for that. Just even questioning me, you get 100. You're at your 150 for today. Here's my X. So that should be... Did I enter them in backwards? 24.3 and 15.3. And then... Oh, you're right. I entered these in backwards. You're right. Those were entered in backwards. You're right. Great job, Morgan. Because I think that's right now. Is that what you were correcting, Morgan? Great job on that. Thank you. You definitely earned. You're at the 150, and I really appreciate that. I would have gotten it wrong. because I put the mean in the standard deviation spot. Just happens. Nice job, Morgan. Thank you so much. You've following along, seeing, wait a minute, dude, don't you put the thing where it goes. Don't do that. So, I make so many mistakes. 824, square root this. I'm square rooting r squared. Brian just found what? Brian just found what? Is it positive or it's positive? And I was checking because I wanted to see if it was positive or negative. I just found what fraction of variability is associated. Good question, Camden. So if that is going to be, remember, what do you do to correlation to get r? You square it. Correlation squared is r squared, which is the fraction of variability. And then we can take r squared. So you were leading into this question. Great job there, Camden. You see the r squared right here? If I square root it, I get r. So if you square this, you get r. If you square root r squared, you get r. So this is the correlation right here. I'm going to put in all the decimals and hope that they don't get mad at me for doing the things that I should. And now we have the equation. So I am jumping a little bit in this question, but since it gave me that information to start, I'm just going to use this to solve the equation right here. So this is the intercept, 3 decimals. This is the slope right here, 2, 3 decimals. Makes sense right there. And let's take a look. Do you think the linear model is appropriate? What do you guys think? QQ straight enough, no outliers, plot doesn't thicken? Yes or no? QQ straight enough, no outliers, plot doesn't thicken? QQ straight enough, no outliers, plot does not thicken. I say good too. You guys got it. It's QQ straight enough, no outliers, plot doesn't thicken. It doesn't look weak. It looks fairly strong. I mean, the r squared is this. That's a really big r squared, and the correlation is this. So it's definitely not weak, because you'd be like, well, how close are those points are really good. Yeah, it's pretty good, strong relationship there. The percent of marijuana accounts for 82.4% of the percent of marijuana usage accounts for 82.4% of the variation in other drug usage, because marijuana is explaining the variation in other drug usage. They reversed it a little bit. I would say 82.4% of the variation in other drug usage is explained by marijuana usage, but they changed it. Include in context what the slope means for each additional percent in marijuana usage. We expect other drug usage to increase by 0.647%. That marijuana, this will indicate that marijuana use increases on other drug uses increases on average by this. For each percent increase in marijuana. So for each additional percent increase in marijuana, we expect other drug usage to increase by this. They've totally reversed the order of this, because I would say for each additional increase in marijuana usage, we expect other drug usage to increase by this. Does everyone see that, how they switched it on you? I usually say for each increase in marijuana usage by this, we would expect other drug usage to increase. So they've changed the complete ordering of the way I would say it, which is all right. Just another way of saying it. Do these results confirm? Does this prove? Does this say it causes it? You got Josh. We can do that one. I think so. Let's find it. I think that's the one people want me to do. We got hamburgers coming up soon. Does this prove? Does this cause? There's an association, but not causation. 90, really? Of course it's that one. Is it a decimal? Is it a decimal? It's not weak. It's not weak. It's obviously not weak. This is right. Wait. It should. Ooh, it wants that 0.4. 3 decimals. Did it seriously not like my equation? I've got another way of solving it. No, I'd like that number. What was that? Might be this number. It is this number. What did it not like about the intercept? Well, let's see. Let me look at my intercept. Negative 3.714. Is it really going to be that picky? Does it want me to round down? It says it's wrong. What I can do, does it give me the answers here? Sometimes it'll give you the answers. Let me solve it in jump. That's ridiculous. Please tell me if you get this one wrong by that. I can't imagine why this is wrong. I'm really not happy with this problem. Problem why you do this. Okay, we're predicting other drug usage from marijuana. Oh, wait, is it not negative? Yeah, why did I put a negative in there? Oh, the intercept is negative. And why is it turning out like this? Is their data messed up? Yeah, I'm wondering, Jared. And I'm wondering, oh, you know what? Why did it give me the other answer if I got this? Did I enter the things in incorrectly? Let me look at the values again. I might have mistyped, and I'm surprised it gave me as much as it did. It says correlation here is 0.90756. What should I enter in? 0.907. Okay, that's the was it but then other things are wrong. Let me double check. Okay, this should be other drug standard deviation. Other drug standard deviation is what? Other drugs is 10.9, and that's why I created these. So other drugs have a standard deviation of this. That's good. And then other drugs have a mean of this. Cool. And then marijuana has a mean of this. And marijuana has a standard deviation of this. I'm gonna like write my Pearson. Is it? You think it's the 5 maybe? No. Let's look at what Jump said, because Jump gave a completely different answer. It's almost like they didn't connect their data to it. My Pearson's not perfect. That'd be 3.70. But then the other number should be wrong. Wait. Can't think. So the answer here it's saying should be negative 3.670. That's not right. Unless I entered in another... Please tell me if you get this one wrong. I'll fix that. But then the other number inside jump is... It's just close enough. It accepts it. It would accept... Because this would go to 6 right here. That's within its margin of error. The correlation shouldn't be 0. The correlation shouldn't be 0. Double check. This is a tough quiz. Please tell me if you make errors like this. I will correct that instantaneously. I don't know why the solver... I think I know why. I'm really mad at my Pearson. I think what they're doing is they're not carrying out enough decimals with these. So they're not... You guys can do it. You guys can do it. This is one of the hardest ones. You see, it's even given me a little bit of trouble with my Pearson with the rounding. If you had a rounding issue with this, if you're within decimals of this, I'll give it to you. Also, the more you do this quiz, you might get some easy versions of it. There'll be a lot more explaining, Keen. There'll be a lot more explaining. So there'll be a lot more kind of conceptual stuff. So don't worry, the test is probably easier than my Pearson, but you should know the conceptual stuff. Don't just be like, if I can just plug numbers in, I'll get the test right. Hamburgers, you got it. We've been talking about those hamburgers for so long that we need those hamburgers. Yes. Watch this. You ready? It's time for... Not bad. Time for a speed run. I'll slow down, but just to show you, just to give you some confidence, you say, Brian, how can we do this if you can't do this? It's impossible. I'll save you right here. I'll save you with a speed run right here. We're going world record time right here. We're going to get this question right here. World record time. Sorry, it's a little small. I'll come back in and zoom at it right here. So world record speed run right here. We're going to get this one done in under 2 minutes. Let's hope I get this right. Here we go. We're going to take the data right here. We're going to take it. We're going to copy it to the clipboard. We got it. We copy the data. We bring over here. We go over here to jump. And then, we go to jump again. We bring a new data table inside of jump. We drop the data in jump, but we didn't paste the right way. We paste the data into jump. So now that we've got our data into jump, we bring it here on the screen. We take a look at our data, and we go to analyze fit y by x. Now, a very important thing for this problem is we need to see how we're predicting. A data shows that fat and calories, the model was created to estimate the number of calories. Since we're estimating calories, calories will be the y variable. So we know that calories is the y variable here. So the regression model was made to predict calories and not fat. And let's go right here. We're going to then go back to jump. Hello, jump. We need to go to this right here. So we're predicting calories from fat. Remember, calories is the y variable. So now that we have our scatter plot right here, we're going to fit a line to it. And we get our regression equation. It's right here. We're just going to take this whole thing. And we're going to go right here. We're going to drop it in. This is ridiculous, but we're going to pare it down to this. And hopefully it doesn't... Oh, it's going to get mad at me. It's probably not going to like that. So we're taking the whole thing right here and using jump to make this nice and easier. So we've got it inside of there. Let's go back and delete this. 3 decimals. Was there? Oh, was that not it? Wait, gotta look. 11.331. I'm gonna make a mistake if I try to do this. 11.331. So it's not too much like the exam. Don't worry, it's not too much like the exam. Not too much like it. I mean, it's not a horrible example. The fat content of a burger with 600 calories. So now you can actually do this inside of jump. What's cool about jump is we can go here and we go to save predicteds. And under save predicteds, it now saved them into the data table. Here, I'll show you guys. We'll quit the speedrun. Speedrun aborted. Let's go back. What I'm doing right here is I went to the red arrow and I go to save predicteds. I'm going to show you another way to do this. This actually saves the predicteds in the data sheet. And I'll show you how to do it outside of jump. You can go here and put 600 calories in, and it'll make... Am I predicting fat? Oh, I got to save predicteds again, I guess. Jump, why do you change things? So, save predicteds. Did they change how this works? It might be easier to do it not in jump anymore. Take your data that you've copied, copy the data, and go over here to Excel. Click on the top of the Y's, and I think this will work, and paste the data in, not that data. So go to your data. So I'm slowing it down now. Go here and copy to clipboard the data. Copy your data and paste this in. Now, I think I pasted over here because calories is the Y variable. Calories is what we want to understand, and fat is the X variable. Now, you have to undo this when you do this. So as everyone see here, I've pasted, and just so you can see, I pasted over where the X is. Does not let me rewind time. So I pasted, there we go. I pasted over the X, and it's now computing all of this for me. So does everyone see that this data right here, be very careful the way you paste. If you want, type in the values, but you can put them inside of here, and now we get the intercept, which we saw inside of jump a moment ago. It's probably easier to do this. That's why I created this. But do you see the intercept and the slope are right here? Does that make sense to everybody? Stop doing that jump. But you have the intercept and the slope right here with these values. You have the intercept right here, and you have the slope value right here, which you also see in the output down at the very bottom of the screen. The intercept and the slope. Does that make sense to everybody? Now, I say it's easier when you have to solve for a burger with a certain amount of calories because I can just type 600 right there, and it solves it for me. So now it solves for how many calories would be in this burger, just like that. Does that make sense? So this problem right here with the solver is way easier. Who feels better about this problem right now with the solver? I should have just used the solver. Are they not... I think I have them correct. Let me rewind time here a whole bunch. This is the Y variable, and it says we are predicting calories because it's asking for fat. Let me double check. Good catch. 150 points for correcting me. The data below, the fat content of a burger with 600 calories it is asking for fat, isn't it? Let me double check. A model is created that can estimate the number of calories in a burger when, oh my gosh. Wait. Yeah. Man, this problem. You earned the points right there. So they're switching it. I forgot. So many tracks. So with this problem right here, this is now predicting fat. They switch it. It starts out saying we made a model predict calories. Then they suddenly switch it to say down here, now we're going to make a model predicting fat. So you guys stopped me from getting another one wrong. Lack of food. We're blaming it on that. So this model is now predicting fat right here. Amazing. You definitely earned the points right there. I think, Jared, you're at 150, so why not you're at 200? Thank you for correcting me. Fat goes there. This goes here. And now we get a totally different equation. Now the equation, Alyssa, are you doing the following method? Go here and go to copy to clipboard. And then when you copy to clipboard, hit Command-C or Control-C. Is that working for you, Alyssa, right there? Which step do you get to? And is this making sense? I'm sorry, I just made some mistakes right here. I was like, I'll speed run and I just... good stuff, good stuff. Got it fixed. Make sure you put the right things in the right spots. Also, you need to cover up, like when you paste fat into here, you need to click on the Y and paste over the Y. So I'm going to try to deselect things for a moment. Sure. I'm going to copy this. There we go. And I'm going to paste this over the Y. Do not paste it like right there. That'll mess it up. That's not how it's supposed to be pasted there. And now we have the right answers. Negative 13.65. So negative 13.65, and then 0.08149. There we go. And that's right. Oh, wait, 0.08. 0.081. It rounds down. 0.081. 0.081. There we go. Be very careful. Very small decimals. Make mistakes. And then we have here, we make a prediction for 600. And there it is, 35.24. How many decimals? 1 decimal. 35.2. That's got it. Did we do it correctly? I'm scared. The regression model was predicting... Explain why you cannot use this model to estimate fat. The regression model was predicting calories from fat, not the other way around. So we can't use it to estimate fat right now. The regression model was estimating calories from fat, so we can't use it to predict fat. But then we make a model that does. Double check my answers. 100, got it. Almost didn't change that top answer. So it's saying, why can we not use this model to predict fat? Originally, the model was made to predict calories from fat. Then we decided to make a model using an appropriate model. Let's do it. Does that make sense? Was everyone able to figure this one out right here? Yeah, Jared, I got you. Email me, Jared, I'll fix it. I got you, Jared. That's a fix. So suppose the entering... Yeah, let's do this next one right here. We got it. Suppose... I told you guys this would be a tough chapter. It is. It's a tough chapter. Here we go. Okay. Cool. Big question right here. Let's do it. So, let's see. Write the regression equation. As soon as you see that you have this stuff up here in any of these questions, you're going to go to the regression solver, and you're going to turn your brain on and enter them in the right way, not like Brian. So we have here that we are predicting GPA of people from their score. So GPA is the Y variable, and SAT score is the X variable. So we have that. We have correlation there. Cool. Let's enter in the correlation. So the correlation right here was, that was it? What was it? What was the correlation? Correlation is 0.44. Microphone. So there's the correlation. Standard deviation of the Y, which is GPA. So I need the standard deviation of GPA. Standard deviation of G is 0.53. So now I need the standard deviation of score is 130. So standard deviation of score, which is the X variable, is 130. Please tell me if I enter something in the wrong way. We need the mean of X. X is score. If you can't see X right here is score, so I need the mean of their score. The mean of their score is 1215. So that's 1215. And then we need the mean of Y, which is their mean of their GPA. And the mean of the GPA is 2.69. It's a low GPA. I mean, it's my GPA, but it's kind of low for the mean of their GPAs. It's a low mean GPA. So what did we get right here? We have the equation to predict. We have now done it. 5 decimals, because it's a decimal thing. And so that one rounds to 8 right there. I guess that's where you maybe had your error. Fun question. Now we get the slope right here. The slope is positive. We drop this in, and now we've done it. We've done it. There we go. Nice job, Morgan, on those points. And so we should have it. Check to see if you have 5 decimals. If for some reason you have this, I don't care. I'll fix that for you because probably I made a mistake. Who knows? Explain what the y-intercept means. The y-intercept is when people have a score equal to 0, which is illogical. We would expect them to have a GPA of 0.51 on average. So the y-intercept represents the predicted the y-intercept represents the predicted GPA score when somebody has an the GPA when someone has it has no practical. Yep, got it. The slope right here is for each additional point someone gets on the SAT, we would expect their GPA to be blank points higher. For each additional increase on the SAT, for each additional point on the SAT, the model predicts that the reference GPA will increase by a value of this. And this one says 1. They don't want to give away the value of the slope to you right here, so they're just saying this, but you would input the value of the slope right here. But they're just doing that to not tell you what it is in the problem. Predict the GPA for a freshman who had a 1400. Well, that's nice and easy. Let's hop back over here. Now what this is going to do is it's going to put it into the value right here for score. So it's just putting 1400 into that value and solving it out for you. So the value is this. We're going to copy paste. That way we don't mistype. And it wants it to 2 decimals, and it rounds like that. Based upon these statistics, how effective do you think SAT scores would be in predicting academic success during the first semester of college? Well, this is a tricky one. Well, the correlation... You gotta hate these interpretation ones. The correlation right here is 0.44. So it's like a moderate correlation. This is wrong because they have some. I'm going to say somewhat. Oh, wait, look, the correlation is positive and near 0.5. If it was closer to 1, I would say it's very effective. But not very effective because the values of correlation is low. It's not really low. I don't think they're going for very effective. I mean, there's some sort of correlation association between the two of these. Remember, all correlations are associations. As a student, would you prefer to have a positive or negative residual? Okay, let's take a look. Let's look at student A or student B, and let's look at the residuals. And we see here's your SAT, and here's your GPA. Here is student A, and here is student, we'll give some color coding help. What would you guys rather be? Would you rather be student A or student B? Would you rather be student A or student B? They both have the same SAT score. And A has a positive residual. Who would you rather be? Color coding help. I'd rather be A. Because A has a much higher GPA, and they have a positive residual. Student C with space pen just chilling out on the line has a 0 residual. The model predicted them accurately. So student A was much higher, and they would have a higher GPA. I'd rather have a positive residual because it represents having a higher GPA than... No, model predicts GPA. Dude. What? Tell me my numbers are not wrong. Tell me the numbers are wrong. What in the world happened? Yes, that number was right. I can't reverse it now. Both of these numbers are right. I'm about to go mad right here. That number was wrong. That number was wrong. And that was the... Wait, that number was right. I've lost my mind. I need to eat. These numbers... I rounded that, right? Okay. And then if I change this to something ridiculous, let me copy this. Okay, it went down. That means that number's right because I changed it. But this number might have been wrong. It might have been the only thing that was wrong. Really? Okay, that number's right now. Or at least we think it's right. It's the slope. And what is it not liking about it? Is this the one Jared also got wrong? I want to see that answer. If I do complete a problem, I think it changes it. Oh, wait, I have too many decimals. Really? Oh, that's right now. I'm losing my mind, everyone. I think 2 decimals. 3.02. The answer is now 1. Okay, so that one's right. Oh, it's this one. Is it really? SAT scores are not very effective. So the 2 things we got wrong were, what did we enter in? I'll have to rewatch the tape. What did we originally enter in for this? How far does anyone remember? Can anyone rewind the tape? 150 points. If you can tell me what I originally entered in for that value. And it was the only other one I feared because of the interpretation, because they see it subtly different than I do. So please make a note of this when you're doing this problem here. And once again, if you got this one wrong on your quiz like I did, I'll fix that. I don't like this part of the question. I think it's bogus because it's like subjective at that point. Like they're saying, I said somewhat effective. And they also give the value right here, but they want to say it's not very effective. I'm like, somewhat effective. And they're like, not very effective. Well, no, I didn't enter 0.02 to start. Did I? Did I really? I really entered it? I did. Does it round to that? Does it round to that? We're going to confirm via software. It doesn't, does it? Ah! Hannah, Alyssa, Neelan, and Claire, and Elizabeth are at 150. Thank you guys for staying through the madness. There. That's why we use software. I don't know how to round. It'll do it for me. Just round this number. Do it. Round it to 5 decimal places. Here, round it to 56 decimal places. There you go. There's 6 decimal places. Yeah, it's so exact. That's ridiculous. Both of those I disagree. Please tell me if you got those wrong for those reasons, because that's I don't like the subjective nature of it. Sorry, not a favorite problem. Sorry, I got stuff. I know you guys are like, well, Brian can't get them right. Sorry, I will give you those points back. Remember, once again, I won't make you guys say it in the chat, but if you do email me and it's one of these things, I do give the points back. If you're like, hey, Brian, I got that one wrong that you got wrong, can I get my points back? It shows you're following along, and it just shows how much I hate subjective questions where it's like, this is not very effective. This is somewhat effective. Well, guess what, my Pearson? Did you know what, my Pearson? That right now we could say that, let's look at our R right here. Right now, we times this by itself. And about 20% of the variation in somebody's, about 20%. 20% of the variation in someone's GPA would be explained by their SAT score, more like 19.36%. You're like, well, that's not much of the variation. That means it plays a component. It has some sort of role in it. It tells us a little bit. Scholastic question. You got it, Josh. Scholastic question. I think, am I making an executive decision? Scholastic. If the videos go really long, they take longer to upload, and I'm afraid I've done most of this. Scholastic aptitude test. This is our revenge on my Pearson here. Revenge on my Pearson. You ready? A group of high school seniors took a scholastic aptitude test. The resulting math scores had a mean of this and a standard deviation of this. Once I hear these numbers, guess what I'm doing? I'm going back to the regression solver. We are going to use this. What are we predicting? What are we predicting? Write an equation that predicts verbal. Verbal is now the Y. So, and then we got that one next to Alyssa right here. So verbals had a mean of this. That's the mean of verbal, mean of Y. So the mean of Y, that number is going to go right here, and that's 496.3. And then the mean of the other one, the mean of math, is 476 points. There we go. There we go. And now verbal has a standard deviation of 175.3. How does Brian know this is the Y? It says we are predicting verbal. That means this is the Y. Predicted value is the Y value. So verbal has to be the Y. And please tell me if I type things in the wrong way. And then we need the mean of X, which is math. And we see here math had a, is it mean we need? I hope we got them all in. 189.8. My eyes are not good. And then we need the correlation between the two, which is 0.82. And then we can make predictions if we want. Not yet, yo. We got them. So this is the intercept. Goes in this spot, round to 3 decimals. Don't mind if I do. Sure, you get the 9 today, my Pearson. I'll change it later. And then we go right here and we put in the slope. The slope is positive, round to 3 decimals. There's your 3 right there, my Pearson. Don't tell me I'm wrong. What is the correlation? Are you trying to trick me, my Pearson? Is that what you're trying to do? You told me the correlation. Oh, you're trying to see. What is my Pearson having you recognize right here? Why is my Pearson asking you what the correlation is? They want you to see that R is correlation. To me, I'm like, well, R is correlation. You just told me that. You said R. And so I know that that's correlation. Since they're just trying to have you recognize that R is correlation. So it's a notation thing. In general, what would a 0 residual mean? Model predicts it perfectly. We've seen this in a lot of examples today. That something like this point C right here has a 0 residual. The model predicts it perfectly. So the model made a 0 residual means it exactly predicted it. It's not higher or lower. Positive residual is higher than the predicted. Lower negative residual is lower. A person tells you their math score was 313. Well, that is the X variable. They want me to predict their verbal. So we go back here, and they tell me their math is 313, and solver tells me this is their prediction. All the solver is doing is going in and plugging in 313 right here. So if you have to solve this by hand, which some of them you do, you plug in 313, and you would get that, and we round to 3 decimals. And this rounds to 1. Using the predicted score from D. Predict the... Oh, this is so weird. How is it exact? Because if something has a residual of 0, that means it's exactly on the line. The only way to have a residual of 0 is to land exactly on the prediction line. If you land below, good question right there, Josh. If you land below the predicted line, you would have a negative residual, and above, you'd have a positive residual. Exactly on it is a residual of 0 because the model missed by nothing. It perfectly predicted that individual. So remember, this is a line, and we get points around it. So all the points can either have positive, negative, or residuals close to or at 0. It's possible to have 0, but a lot of times they're close to 0. Like something close to 0 was almost perfectly predicted by the model. Does that make more sense there, Josh? Does that help out with that kind of concept of a residual and positive, negative nature of it? We'll see if it works. So now, this is a bit ridiculous. Good job, Josh. Great work right there. We're going to use this predicted value right here and plug it back in. So this is ridiculous. There's like parts of problems. I want to talk to the person who wrote this, my person question. We're going to take this, plug it in, and then we solve back out from this, and we get this. So you literally take this value here and plug it here. And we get this, and there it is. Why doesn't your result equal it? It's because we're using a predicted to resolve for an actual. So the line found in... So the line found in B minimizes the squared residuals in the verbal direction. We're predicting verbal. Okay, that's correct. The first line minimized the residuals in the verbal direction. Okay. So this one should be right. Okay. And I'm trying to see the difference between these. The line found in B minimizes the math where the line found... Oh, wait. The line... Yes, okay. We were given the line in E. So we were given the line in E. So they're saying here... Yeah. Did they just reverse the way these were written? I think these are the... Yeah, the way you can tell is that answers B and C, I think, are the same answer, but they just reversed the way they wrote it because they couldn't think of another way to write a wrong answer. So B and C say the same thing. They just say, while the line given in E minimizes the verbal direction, the line given in E minimizes the verbal direction, the line found in B minimizes the math, the line found in B. So they're the same answer, they're just reversed. So we got that 100. That's our revenge on my Pearson right there. You know we got that 100. We love those hundreds. So these are wrong answers. They're the same wrong answer because when we talk about the residuals, you don't have to realize like squared residuals. We did lightly mention that at the start class. Won't be on the test like a squared residual, which is the sums of squares. But yes, I think there was another one. Advertised prices, Alyssa. Advertised prices. I'm going to send out, we're going to take a break and then we'll come back and do the Kahoot. How does it sound to do the Kahoot at 4? Do you guys want to do that? Because I probably need this video to upload and I probably need to eat or take a break. Do you guys want to do the Kahoot at 4? I'll send out a reminder and I'll send out a code Kahoot at 4 so I can take a short break because my brain is like fading, and I'll need to take a break and eat or something. So Kahoot at 4 I think will work. So that way, and then this video can do its upload thing. I need a break too. Me too. We've done a lot of stats today. It's a big day. Use the advertised price for used cars, a particular model. We get some data right here. So we go here, we take our data, we copy the data to the clipboard. Revenge on my Pearson. Guess what we're going to do? We're going to take this data right here. We're predicting the price of a car. We're going to go over to that regression solver. We're going to reverse time so that way we don't have stuff put into there. We're going to paste the data. Bah! We're going to reverse time again. We're going to go back to our data on my Pearson. And on our data, we go right here and we go to copy to clipboard, copy the data to clipboard, bring the data back over here. There's the data. So when we take this data, good, I think this data will work. We're going to take the age of a car. And the age of a car is going to explain the price of a car. And guess what? Answers are now here. We'll be live on YouTube at 4 with the Kahoot. I'll send out a reminder. So we'll be live, and I'll probably do like... we'll be doing 3 Kahoots. So it'll be 50, 100, and 200 for the Kahoot winners. 50, 100, and 200 for the Kahoot winners. You'll have to email me a screenshot of you winning the Kahoot. So it'll be 50, 100, and all Kahoots will be 50, 100, 200 for the winners. So be here for the Kahoot. Be here for the Kahoot. And yeah, I think we can get the Kahoot done like an hour and a half. So yeah, you're not required to watch all these things. I know it's a lot. It's just review. So this is me helping you review. And there are other review videos if you want to watch them. We've basically solved this question right now because we have the intercept. And we go back to here. We put in the intercept. We got the intercept. We delete down to nearest integer. Why don't you want those decimals? I worked so hard for them. And now we go back here. We take the slope. The slope is negative. We put in, and it says to the nearest integer. Okay. If you don't want those decimals. Explain the meaning of the slope right here. This means for each additional year the car is older, we would expect the price of the car to decrease by a certain amount. So for each additional year, the price of the car will decrease by the coefficient right here. And it doesn't want the negative, I don't think. There. Explain the meaning of the y-intercept of the line. The y-intercept is going to be when a car is equal to 0 years of age. We would expect its price to be equal to this. So that means a new car. So the car is a new car, and we would expect, because it has 0 years of age. There we go right there. If you want to sell an 8-year-old car, what price does the model say it'll be? Well, we go right here, and we go into 8, and we plug it in, and that's the price of an 8-year-old car. What is this doing once again to nearest dollar? As long as you say so. It's putting age of 8 right here. Please note that if you do solve this by hand, that is something you could do on the test. You could put 8 right here, and it would solve for that. So you would just put 8, you would mathematically solve it, and you're good. You have a choice to buy 2 cars. They are identical, let's say. They did finally add that. They appear to be in equally good condition. I think they change these questions every once in a while, and I'm glad they wrote that. Would you rather buy a positive or negative residual? What would you guys want, positive or negative? Positive or negative residual? Let's change this so it makes sense right here. Well, we need a negative line. Would you want to buy a car? They're identical cars. Literally, someone has duplicated a car, and one of them has a positive or negative residual. It's price. Positive or negative? Positive or negative? Which one would you want? Positive or negative? What do people say in the chat? We know it's a car, so here's car A and car B. They are identical cars. Which one would you want, car A or car B? They are identical. They have the same age, same everything. Someone's literally duplicated a car. For some reason, they've listed it twice. Both 2 different prices. It's pretty obvious when I say it that way, right? If it's the same car, the one with the negative residual costs less. Now, let's not always say like a negative residual is a good thing. It just means the model predicts this car would be worth more than the actual price we're showing. Like this is its actual Y value right here. And then this is its, for both these cars, this is the Y hats for these. That's the predicted for both of these cars due to their age. So the negative residual for car A would tell us that it's a better deal. I mean, if they're both the same type of car. I mean, be like, well, maybe they're trying to trick us. That problem doesn't say that. My Pearson's trying to trick us. The car with the negative residual would be better because its actual price is below the predicted price. That's good right there. The car with the negative residual would be better because its actual price is above. Nope, that doesn't make sense. You see a for sale sign on a 10-year-old car. This is a tough question. Stating that its asking price is this. What is its residual? Okay, let's slow this question down just a tiny bit here. When you're presented with a question like this, you need to identify the notation. And I'm going a little quick. I hear myself talking quickly. When you're presented with a question like this, you need the notation on it. The notation for this question would be as follows. I need someone in the chat to tell me any one of these things. We're almost done. I think this will be one of our last problems because we almost done them all. I need someone to tell me what one of these values are. This is a tough problem, probably one of the toughest ones of this, because you're presented with a lot of information, and then the what do you do with this information part of it is tough. We've got a hint for what we wrote down earlier. When you look at this, age is over there, price is over there. It's a key hint. And you've got this, you've got this, and you've got this. I don't know how many people are watching, but does anyone know? If you're watching this video now and you're doing this, I want you to try to figure out what these notations are. Like, what are these things? Because, yeah, I'll check that. I'll probably eat some lunch and relax for a moment. I'll check that. You got that, Neelan. I'll be doing that from 2 to 4, and then 4 o'clock Kahoot. So if you're here watching right now, 4 o'clock Kahoot. I got you, Neelan. So this right here, this 10-year-old car, is the age of a car. That makes this X. This asking price of a car is Y. And this residual right here is E. What are we missing? What are we missing to figure out the residual? We're missing something. Right now, if we want to figure out the residual, which is what it asks for, residual is equal to actual minus predicted. But we can, so we don't have this right now. We don't have the predicted. But we can go down here and solve the predicted from so we need to plug in the X to get the predicted and then use that to solve for the residual. So we're going to use the X way up there in the equation, which will solve the predicted. Once we get the predicted, we can solve for the residual. So knowing what this notation is and knowing how to utilize it is important because we can take the 10-year-old car and we plug that right into here, and that's now the predicted. Now that we have the predicted of 467.699, we're going to go back to here. And so this solved out to 467.699. And then we go to here, and we know that the actual is this. Is that right? I'll have to look at it. I want to double check that because that seems really off. 467.699. That's a very low. That's a huge, and I'm going to make errors in here. That car has a very, very large residual. So, I feel like that's too large of a residual. Could be. That's what they could be doing to us. 9,600. That's what it's saying. Let me look at the problem again. Does it give me a graphic of it? Something seems off. Oops. Whoops. I'm going to change answers. Okay. What is going... Oh, my gosh. Whoops. Yeah. I put it in the wrong spot. This is the data one. I knew something seemed wrong. 101163. I knew that seemed off. I was like, that does not seem right. There's an error. So... that's how you make errors. 101116.3. Cool. So it's 16.3. So, or negative 16.3. So, I was like, that did not seem right. Lack of food. Negative 16.3 right here. And so make sure you put in the right ones. Let me look. Did I change this? Oh, I did. Good. I can see which one it was. Negative 16.3. I like doing inside jump. That's how I usually check them. What is its residual? I think we did that properly. 26-year-old car. Nope. Extrapolation, because that's outside the X bounds of the model. No, because think it'll be negative. We could check. But it's an extrapolation. It's negative, so that's the one they want. But it's also an extrapolation of the model. What do I mean by extrapolation? When you look at the data right here, it does not have cars that are that old. So this is outside the X bounds of the model. Round to the nearest whole dollar. And you would trick me on that, my Pearson, wouldn't you? You wanted all those decimals. 100. I just went for it. I was like, I know we got that 100. So we've done it. We've done some of the hardest problems today, even conquering my Pearson. And I think we did this one right here, didn't we? It says we completed it? Wait. Oh, that's because we just completed it. Yay! I think we have now done it. We did every problem in Chapter 7 in this video. And only, I think, 3 of them, maybe 2, tricked us a little bit. Pretty good, pretty good. A little tricky stuff. Please tell me if you got tricked by them. But that's got it. Who all do we got watching? I'll say bye to everybody. I'm going to start doing some stuff. Relax for a moment here. Everyone doing good? Good yawn, Mike. 4 p.m. Kahoot. I'll send out a reminder real quick. And I'll send out a code for the Kahoot. So I'm going to get off here, and we will be back for 4 p.m. Kahoot. And I'll say bye to everybody. Goodbye. Anyone here in the chat? Maybe. Bye. Do you think we could do a little extra tonight review? Yeah, we'll do some. So, yeah, I think we can. 4 to 6, yeah. We'll do from 4. We'll try to go from 4 to 6, as long as I don't get my brain done. You got tricked? No, don't let my Pearson trick you. We'll try to go from 4 to 6 review tonight, and we'll go beyond the Kahoot. So ask questions during the Kahoot that go beyond, and it is tough. And then I'll be answering all the emails and everything, just because the reason I say that, Neeland, is if I do like more review tonight, then I'll probably have more emails. And so I'm going to go do emails now when I leave here, and I'm going to do the Kahoot, and I'll probably answer more emails. You got it, Neeland. So if you're stuck on anything, please email me. Ask all the questions you got. Thank you guys so much. We got this. Stats Nation. See you at 4 p.m. Bye, buddy.